Great inventions are rarely done in one go. Instead, they come in a string of small steps, and crediting a single person with creating an innovation as a modern audience would recognise it is hard to do, as is the case with the railways. The question of who created the tracks the trains would eventually run on heavily depends on how one defines tracks. As far back as ancient Egypt, pyramid builders recognised that a heavy load is easier to move along a smooth surface, and that it is easier to create two raised strips of smooth stone to support their loads than to smooth over the entire route. The first roadway, specially shaped to guide vehicles, was built around 600 BC in Dylakos in Greece. Grooves were cut in limestone blocks to guide trucks, which were used to transport ships across the Isthmus of Corinth. But the first recorded route, with raised wooden rails and specially built vehicles to run on it, was built in Germany in 1556. The carts ran on two central rails, with a spike between them to guide them along. In 1568, German miners created Britain's first known wagonway, as a means of helping them transport coal. The idea slowly spread all over Europe, wherever goods needed regularly transporting to the nearest market or dock, using a variety of methods to hold them on the wooden rails, and various combinations of horses, winches and gravity to guide them along. With rails to run on, the horses could pull 4 times the weight it was possible to pull on roads. With the Industrial Revolution, iron became easier to manufacture, and wagonways began covering their wooden rails with iron sheets in order to reduce wear as well as friction, allowing them to pull more weight still. In 1801, the Surrey Ironway opened between Wandsworth and Croydon, the first public railway, in that anyone who had a vehicle that could run on the tracks was allowed to do so for a certain fee. In 1807, the first properly organised passenger services began on the Swansea Wagonway in Wales. Benjamin French, one of the proprietors of the line, built the world's first station platform in Oystermouth as a means of transporting passengers to Swansea. However, for the passengers of these early wagonways, there was no clear advantage in speed over the roads and the canals. Indeed, the wagonway was soon replaced by a turnpike road that was built not long afterwards. To properly revolutionise society, the wagonways would need something to power the passengers along at a greater speed. That something was steam power. The history of the earliest steam engines is surprisingly almost as far back as the tracks they would eventually run on. The first working steam engine was built by Hero of Alexandria around AD 62. Hero built a copper ball mounted on 2 hollow casters, through which steam would be fed from a reservoir heated from the fires below. Pressure would build up until the steam would shoot out of 2 angled nozzles, causing the ball to spin at great speed. Sadly, Hero never thought to put this to practical use. Even if he had, any hope of kick-starting an industrial revolution 1,700 years early would require a quantity of strong material, fuel and specialisation that were not available at the time. Hero's engines, as they are now known, produced very little traction. To make use of it, the Romans would either have to gear it down a lot or use it to drive ships' propellers, and neither gears nor propellers existed at the time. Hero's engine was doomed to be no more than a novelty for more than 1,000 years. The first steam engine to be of practical use was built by a vicar called Thomas Newcomen in 1712. It was built to act as a pump to draw water out of a local tin mine. However, instead of using steam pressure to drive the cylinder, as one might expect, he did the opposite. A counterweight would be used to lift the cylinder, drawing steam into the boiler. The valve through which the steam entered would then be shut off, sealing the cylinder. Water would then be injected in, rapidly cooling the steam and causing it to contract, sucking the cylinder down, thus driving the machine. Newcomen built around 150 of these engines to serve as pumps in mines. They allowed miners to dig deeper than ever before, but they were also heavy coal guzzlers. Fortunately, most of the mines that bought them would mine in coal anyway. In 1763, a man called James Watt was tasked with repairing a Newcomen's engine. He noted several inefficiencies, which he began to improve upon. First, he saw that the cylinder was having to be heated and cooled with each stroke, causing much of the heat energy to be lost into the body of the cylinder. To get around this, he invented the condenser. Instead of water being injected into the cylinder, a valve would be opened, whereupon convection currents would draw the steam down into a low-pressure condenser, drawing the cylinder down with it. The steam would be cooled in the condenser and fed back into the boiler. The condenser was immersed in cooling water, and the cylinder encased in insulating material in order to keep each at a constant temperature. Watt also replaced the chains of Newcomen's engine with rods, allowing the cylinder to push as well as pull and allowing it to drive wheels. Watt also noted that Newcomen's engine used sucking force to draw the cylinder down, which meant that the driving force of the machine was never more than atmospheric pressure. He improved upon this by injecting low-pressure steam above the cylinder during downward strokes. In later years, he would develop a system that would allow the cylinder to be double-acting, with each side alternatively having steam injected and condensed. However, the steam pressure he could employ was barely above atmospheric due to safety concerns, and the suction from the condensing steam would remain the main driving force of the engine. Watt's engine could provide the same power output as a similarly sized Newcomen's engine, but required half the coal to run. After partnering with Matthew Boulton in 1775, they were able to sell his engines around the country, and soon the world, completely revolutionising many industries. Many wagonways employed these engines to act as winches, to help pull carts over tougher sections of track. Having devised a means of turning a wheel with a steam piston, the next obvious thing to do would be to use the wheel to drive a vehicle. A French engineer called Nicolas Joseph Cognot was granted funding from King Louis XV to do just that. In 1769, he built a test model, which he named the Fardier A Vapor. A year later, he built a full-size version, capable of carrying 4 passengers. This was the world's first self-propelled vehicle. However, it proved unstable and not as powerful as the king had hoped, and funding was soon withdrawn. An engineer working for Watt, known as William Murdoch, heard about Cognot's work and decided to build his own. In 1784, he built a 30cm high model to prove his concept, which he named the steam locomotive. His model worked pretty well, but he was never able to secure the funding to build a full-size version, few seeing the viability of the idea. The problem was, low-pressure steam engines tended to be bulky and produced barely enough power to move their own weight, nowhere near enough to be put to practical use. However, when the Napoleonic Wars began in 1792 and dragged on for the best part of 22 years, many horses were withdrawn from the country for the war effort. There was now a shortage of them, and suddenly a vehicle to run on the tracks seemed like a great idea if somebody could produce one. The challenge was to create a high-pressure engine of some kind, but to do so would require the whole system to contain the pressure without bursting. The solution came from Murdoch's next-door neighbour, Richard Trevithick. He replaced the square boiler with a round one. This allowed the pressure to spread more evenly, and the boiler could take more without bursting. Trevithick also had the idea to run a pipe through the boiler, carrying smoke from the fire. This brought the heat right to the heart of the tank, and boiled the water much more efficiently than just lighting a fire underneath. Finally, he modified the cylinder itself. Some of his engines could produce a pressure 10 times higher than any of Watt's engines. This meant that the cylinders could be much smaller and therefore lighter. As the high-pressure steam was now the main driving force, it was no longer necessary to condense the steam, and doing so was actually slowing down the rate at which the cylinder could be evacuated. Instead, in Trevithick's engines, the steam would be vented out into the atmosphere. Trevithick's first thought was to build a steam carriage with this technology. Unfortunately, the delicate balance of cylinders and flywheels made suspending the carriage impossible, and on the cobbles of London, it proved a very bumpy ride for the passengers. The next logical move was to run his vehicle on rails instead. In 1802, he installed one of his high-pressure engines in Penydarren Ironworks in Methotydril to drive a hammer. During a lull in installation, he experimented with building a vehicle to run on the mine's tracks. This impressed the owner, who made a bet with another ironworks owner that the machine could pull 10 imperial tons of iron from Penydarren to Abercynon, 16 kilometres away. Dyfryn managed it, pulling not only the iron, but also 70 passengers over the course of 4 hours and 5 minutes. This was the first ever run of a steam train. However, the weight of the engine caused so much damage to the wooden rails that it was never used for this purpose again. Dyfryn built at least 4 locomotives, which went to work on various wagonways. In 1808, he opened a steam fair in London to show off his invention to investors and the public. His train, known as Catch Me Who Can, ran round on a ring at speeds of 19 kilometres an hour, with the public invited to race against it. This time he used iron rails, which would be strong enough to support the train. Unfortunately, the ground beneath the sleepers was not. Some of the sleepers sank, putting strain on the rails and eventually bending them out of shape. After a bit of trial and error, the track was repaired and shored up, but by then the public excitement had died down, and few were willing to pay the shilling entry fee. Dyfryn had spent all of his savings on the fair, and its financial failure pretty much put an end to his railway schemes. What's more, Napoleon surrendered in 1814, and again in 1815. Now that workhorses were readily available again, and locomotives had yet to produce a clear advantage over them, the nation's wagonways simply returned to using them. Progress slowed for a while. Nonetheless, engineers continued to tinker with locomotives, in the hope that they could realise their potential. Among them was George Stephenson, who installed several locomotives on the Hetton Colliery Railway. The inland mines in County Durham were looking for an easy way of transporting coal to the markets in Darlington and the port of Stockton. Several canals had been proposed, but each ran into too many logistical issues. A final canal proposal in 1821 would have bypassed the main mining towns. A Welsh engineer called George Overton was called in to consult. He suggested building a wagonway instead. The line's main investor, Edward Peace, liked the idea, but doubted Overton's ability to realise it. He appointed George Stephenson as the chief engineer. Stephenson recommended the use of steam locomotives on the line. By now, some of his experimental locomotives had proved an ability to pull much more weight than horses ever could. He recommended that the route be built using malleable rolled iron rails to make them strong enough to take the extra weight. This despite the fact that he had shares in cast iron manufacturing. Early steam locomotives would struggle on all but the slightest hills and bends. To connect 2 points, a route would have to be created that was as straight and level as possible. A huge army of workmen, known as navigational engineers or navvies, was assembled to level the ground and create a smooth straight run. Fortunately, the navvies were well experienced in creating long level routes, having been digging canals for generations. The best teams could move more than 2,000 tons of rock and soil a day. Soil removed from a cutting in one section of the line was used to build up the ground in another. Where the valley was too deep, a viaduct was built. Health and safety being largely non-existent at the time, accidents and even fatalities were common among the workers. By 1825, the Stockton and Darlington Railway was complete. Stephenson's locomotion number 1 was positioned at Shildon Lane End for the first proper train journey. It pulled behind 12 wagons of coal and 21 wagons that had been fitted with seats enough to take 300 people, but 450 turned up for the inaugural journey, many of whom would cling to the outside of the trucks or climb on top of the coal. The train set off, with a huge crowd attempting to follow on both horse and foot. but the train soon picked up speeds of 19 kilometers an hour, leaving the crowds behind. Even those on horseback couldn't keep pace. On the uphill sections, it would slow to 4 kilometers an hour. The journey wasn't smooth, and the train would have to stop twice for repairs on the way. But after 3.5 hours, they reached Darlington, where a huge cheering crowd greeted them. The Stockton and Darlington Railway was the first to run passenger services under steam, but it was not a proper railway as we'd recognise it today. Though there were some passenger services, the line was run more like a public road. Anyone with a vehicle capable of running on the rails could do so for a reasonable price. Most of these vehicles were still horse-drawn. The first fully timetabled railway was still a few years away. Stephenson, meanwhile, was improving on the designs of his engines, trying to see if he could coax a bit more power out of them, assisted by his son Robert. First, he looked at the smoke running through the boiler, and replaced the single large pipe with lots of small ones, increasing the surface area in contact with the water, and allowing the water between the pipes to be superheated, thus speeding the rate at which it would boil. Next, he looked at the exhaust steam. Instead of venting it straight into the atmosphere, he piped it into the chimney. This had the effect of drawing smoke up the chimney faster and drawing more air into the fire, thus allowing it to burn much hotter and boil more water. Finally, he took the vertical cylinders of previous engines and placed them at an angle. This allowed a better balance when transferring force to the wheels. He dubbed his new creation the Rocket. The Rocket would soon get a chance to be seen in action. The Lancashire mills depended heavily on materials imported through Liverpool, but the roads used to transport them inland were of varying quality. There were several canals, but they were becoming congested by this time. It was said that it was faster to send goods from Liverpool to New York than to Manchester. What's more, the canal owners had gained a monopoly on the transport, and the prices they were charging were strangling the industry. With the population in need of an alternative, a railway was proposed. The founders of the new Liverpool and Manchester Railway knew from the start that it should be steam-powered, but they were undecided about whether to run locomotives or to install a series of steam winches along the line. To see if any engine would be up to the job, a trial was held at Rain Hill, where a 2.8 kilometre stretch of track was built. Entrants would have to make 10 trips back and forth to simulate the distance they would have to cover along the completed line. They would also have to average at least 16 kilometres an hour as they went. More than 10 trains were entered, but only 5 were able to turn up for the competition. But Stephenson's Rocket was the only one to complete the entire course, averaging 19 kilometres an hour and hitting a top speed of 48. Between Liverpool and Manchester were a series of hills, valleys, bogs and landowners, all of which would need to be overcome. After much debate and redesign, a route was planned and construction got underway. At Sankey Brook Valley, Stephenson designed one of the largest viaducts in the world at the time, 217 metres long, 18 metres high, and with arches 15 metres wide. To avoid smashing through Liverpool itself, a 2-kilometre tunnel was dug under the city, the first tunnel ever to run under a major city. Probably the biggest challenge faced was at the extensive bog at Chat Moss. Here, rock and soil was poured in from other parts of the line to create a causeway 3 kilometres long. Finally, in 1830, the railway was ready. The first fully timetabled steam passenger railway in the world. Its inaugural run saw the Prime Minister, the Duke of Wellington, in attendance. He had his own special train to carry him, with 6 other trains running in the inaugural procession. The trains set out from Liverpool. At the halfway point, the Duke's train had to stop at Parkside to take on water. At this time, many of the passengers ignored instructions from the crew and got out to stretch their legs. The MP for Liverpool, William Huskisson, was stood on the tracks talking to Wellington through his carriage window, when the passengers realised that the rocket was now making its way along the track they were stood on, and they quickly began scrambling out of the way. Huskisson tried to climb into the Duke's carriage, but as he tried to pull himself up by the door handle, the door came open and he fell under the wheels of the rocket. He would die from his injuries later that day. Huskisson was far from the first to die on the railways, not even the first passenger. A blind American beggar, whose name was never found out, had died on the Stockton and Darlington Railway in 1827, but Huskisson was the first to be widely reported. Wellington wanted to cancel the rest of the day's events and return to Liverpool, but was persuaded to carry on, as it was seen as important that his train arrive in Manchester to prove the concept. However, as they approached Manchester, they were stopped by an angry mob. Wellington was not popular among the factory workers of the city, and they relished the opportunity to show their disgust. The mob pelted his train with rubbish, and several of them stormed onto the track. The trains were quickly turned round and exited the scene, but in the confusion it wasn't possible to turn 4 of the locomotives around, and they had to be left behind while all the carriages were joined together and the remaining 3 engines towed them as one. The inaugural run hadn't gone as smoothly as had been hoped. Huskisson's death and the riot were widely reported in the papers, but this served as an example of the principle that all publicity is good publicity. Widespread reporting had helped make the concept of the railway known across the country. Crowds flocked to the new line, while many entrepreneurs and engineers looked into the potential of building their own locally. The great age of the railway had arrived.
Travelling on the first railways was an altogether different experience from what a modern audience would be used to. The seats lacked padding, and suspension in the carriages was advancing very slowly. There was also no lighting or heating. All in all, it would be a rather uncomfortable experience in the early years. The early carriages had no facilities in which to eat or to use the toilet. Instead, services would typically schedule in rest stops, in which the train would stop at a station in the middle of the route for 10 minutes or so, in order to allow the passengers to take care of these things. Often, these stops would happen at stations where there were no proper toilets. Instead, passengers would relieve themselves off the end of the platform, with ladies being directed down one end and the gents down the other. Even if the carriages did have facilities in which to eat or to use the toilet, passengers would have been unable to access them, as the early trains had no walkways. Once you had chosen a compartment, you were stuck in it for the rest of the journey until the train next arrived at a station, with whatever company you had. In early trains, the conductor would typically be seated on the roof and make their way along it during the journey, leaning down to check tickets through windows. As with everything else at the time, the railways were heavily segregated according to class. First and second class passengers had not only their own carriages, but usually their own separate trains, as well as separate waiting rooms and even separate ticket offices at entrances. Third class passengers, meanwhile, were rarely allowed in the stations at all. The only way they could travel was in open trucks pulled behind goods trains. Naturally, they would catch these trains in the goods yards, but this was actually pretty convenient for them, as the yards tended to be close to where most of them worked. Improvements in quality for the carriages would naturally start off in the first class and filter their way downwards. Luxuries like glass in the windows and padded seats were initially the exclusive domain of the first class. Third class transport rarely had roofs. Often, they even lacked walls or seats. Passengers just had to cling as best they could to a flatbed truck. The government were in no mood to change this arrangement. Many were opposed to the idea of poor people travelling on the railways at all, believing it would allow opportunities for vandals, allow criminals to escape justice, and for revolutionary ideas to spread. Following the success of the Liverpool and Manchester Railway, routes began to be built across the country. Stephenson was consulted and asked what width of track some of these services should build them to. He said, "All the same, they may be far apart now, but they'll be linked up one day." 1834 saw the opening of the first railway in Ireland, between Dublin and Kingston. It followed the standard gauge, but was the only Irish line to do so. In the early years, every company there would operate to a different gauge. The Newcastle and Carlisle Railway opened in 1839, allowing the two port towns to communicate without a trek over the hills or a long voyage around Scotland. London gained its first railway in 1836, with the opening of London Bridge Station. the terminus of the London and Greenwich Railway. The final 3 kilometres of the line are along a straight stretch of raised arches. It was designed this way to allow the trains to be winched along. The London Council were concerned about the noise, smoke and sparks an engine would produce as the train passed by, and wouldn't allow them to run close to the city until 1844. It was a similar story when Euston opened in 1837. Claims that the early trains to Euston and London Bridge were winched due to the tracks being too steep are not true. However, it is true that many early trains would struggle on all but the slightest gradient. In the early days, it was common for them to be assisted by winches or by horses along the more difficult parts of the route. The speed with which the railways advanced from a collection of localised lines into a national network is simply incredible. Only 3 years after completing the Liverpool and Manchester Railway, George Stephenson was called to plan out the much longer Grand Junction Railway, linking Liverpool with Birmingham. Son Robert, meanwhile, was working on the London and Birmingham Railway. Construction of this line would require the workers to dig a mass of rock equivalent to 1.5 Great Pyramids over the course of 5 years. The Kilsby Tunnel near Rugby delayed the line's completion by 2 years. The 2.2 kilometre tunnel would be the longest in the world. Its route went through a much greater quantity of quicksand than their surveys had suggested. A series of pumps were set up to essentially drain the whole hillside dry, while workers on a floating platform battled to shore up the walls of the tunnel, stuffing straw around to try and stop the water washing the fresh cement away. Finally, in 1838, the tunnel was opened and the line was complete. The two companies were merged to form the London and North Western Railway. From the new terminus at Euston, it was now possible to travel to Coventry, Birmingham, Manchester and Liverpool in a matter of hours instead of days. Seeing that their line would one day be linked into this network, most engineers took Stephenson's advice and built their track to the uniform gauge of 4 foot 8 3/4, or 1.435 metres. But one man chose to disregard this advice completely, and that was the legendary Isambard Kingdom Brunel. Brunel noted that Stephenson had built his line to the gauge he had simply because it was the width of the track for the coal mines he'd been working on early in his career, and this had been set as a convenient width for workhorses and trucks. Brunel saw this as arbitrary and believed he could build tracks that were better tailored for steam power. To this end, he built his tracks to a width of 7 feet and a quarter inch, or 2.134 metres. He dubbed this broad gauge. His reasoning was that wider trains would have a lower centre of gravity. They could be fitted with bigger, more powerful engines, capable of carrying more fuel and able to take bends at greater speeds. Perhaps most importantly, they could pull wider carriages, giving more space for passengers and freight, and also allowing for a smoother ride. Brunel was a brilliant mind, but he was often more concerned with seeing what was technically possible than what was commercially viable, and also struggled to listen to reason. Had he had the broad gauge idea just a few years earlier, it may have kicked off a trend. As it was, so much standard gauge track had been built by this time that it seemed unnecessary to rethink it. What's more, the trains Brunel designed to run on his lines, while they were superior in performance to most standard gauge trains, the difference was not enough to inspire other companies to change their designs, and so they continued with the standard gauge. In time, operating a different gauge to everybody else would put a severe strain on Great Western's business. Some of Brunel's other ideas would pay off a lot better. For instance, he designed the route with a large sweep to the north for no clear reason. He put it this way as it would allow the company to connect to cities in the north later. Where the route crossed the Thames at Maidenhead, Brunel designed 2 of the flattest brick arches in the world. So much so that Great Western were convinced they were going to collapse. Despite Brunel's meticulous calculations, they refused to remove the scaffolding from the arches upon completion, until a storm blew through in 1839 and blew away the scaffolding, but left the arches intact, vindicating Brunel. Brunel was nothing if not ambitious. His plan for the railway was not only to connect London to Bristol, but also to load the trains onto his new transatlantic steamers, then unload them in America and continue to locations there. This continuous service had to be abandoned when Bristol Council wouldn't give him permission to build through the city. The railway was completed in 1841, with the opening of the Box Tunnel near Bath. At almost 3 kilometres, It was now the longest tunnel in the world. Urban legend has it that the sun will shine straight through it at dawn on Brunel's birthday. This was confirmed by GWR in 2017, although 180 years of dust and grime stops the light travelling all the way through. The network was growing fast, but the railways were not always welcome. Whilst most agreed that the railways were a good thing, not everyone wanted one in their back garden. Rural regions didn't want to be disturbed by the noise and the smoke that the trains naturally brought with them. Farmers also feared the smoke would poison the crops and the sight would spook the animals. Meanwhile, urban areas were reluctant to demolish wealthy sections of town to make way for the railways. Railway companies would have to either build their stations outside the city limits or bulldoze through poor neighbourhoods instead, tossing a lot of people out of their home without a penny. Others were afraid that the railway would bring with it undesirable types. In Slough, though a line was built past the town, nearby Eton School was able to successfully campaign to stop a station being built there for a long time. The professors feared that the schoolboys would use it to go on to trips into London and visit the brothels there. Great Western got around this problem by simply having the train stop near a pub, where they'd done a deal with the owner who would sell tickets and people would just climb in. The Eton boys could go and indulge their debauchery after all. Other objectors were the owners of the canals, toll roads and coaching inns, who feared a loss of business. And they were probably right to do so, but they had a hard job holding back progress. Another concern was with strangers travelling together. With passengers in a particular compartment stuck there until the train reached the next station, it could provide great opportunities for thieves, murderers and rapists. The rail companies alleviated the latter issue somewhat by introducing women-only carriages, an idea which is surprisingly controversial nowadays. And of course there were the natural technophobic reactions. Stories spread of conditions of railway madness, in which the sounds and the shaking of the trains would slowly drive people insane. Others believed that the human body would be unable to handle the high speed for too long, or that the noise of the engine would lead to every lady the train passed fainting. A more legitimate concern was with accidents. Almost every week, the papers would be full of a news story of some trouble caused by the railways, people falling on the tracks, derailments, and even collisions. Relatively, train travel was still no more dangerous than any other mode of transport, but the trains were the first in which the passenger had no easy communication with the driver, and the lack of control naturally unnerved people. But engineers and train crews were learning from these accidents. This had begun almost as soon as the railways had got going. Some early engines had no brakes, and could only be stopped by throwing them into reverse, a process which took time, as Huskisson had found out the hard way. Following his death, Stephenson gave an order that all engines running on his lines must now be fitted with proper handbrakes. One problem which unnerved the Victorian public was the possibility of the boiler exploding. It was rare, barely once a decade on the rails, but scary when it did happen. Guidebooks often advised people to seek compartments as far back from the engine as possible, just in case. The engineers were well ahead of them. From the earliest days of steam engines, safety valves had been fitted, which would come open and safely evacuate the steam if the boiler reached a dangerous pressure. The early ones were held shut with a weight, which was all fine for a stationary engine, but on a moving vehicle it would shake and frequently pop open, wasting steam. Stephenson resolved this by replacing the weight with a spring. Unfortunately, many operators would screw down the safety valve to coax a bit more speed out of the engine, increasing the danger of the boiler exploding. Engineers repeatedly modified their valves to make them harder to screw down. In 1833, a train on the Leicester and Swannington Railway struck a cart on a level crossing. No one was hurt, but it led to drivers calling for a better means of warning people they were coming. Stephenson introduced steam whistles to all his trains. The first points were introduced in 1832. Mechanical signals were also introduced. Early on, each set was operated by individual levers. Later, complicated arrangements of rods and chains would be introduced, which allowed all points and signals to be operated from a raised platform. This would soon evolve into the signal box. Interlocking systems were built in order to prevent dangerous combinations of points and signals being created. In the early days, there was no means of communicating between these boxes. Instead, they would have a meticulous schedule worked out in advance, and would only allow trains down particular lines at precise intervals. If something went badly wrong along the line, it was up to the driver to keep an eye out for trouble ahead. Though the signal operators were referred to as signal men, it was actually one of the first railway jobs open to women, and there were a good number of them. The operators tended to live at the box, and hours were long, so it would usually become a family business. The coming of the railways had an impact on society comparable to the coming of digital communications in the modern age. Suddenly, it was possible to travel over great distances without dedicating whole days to it. At the same time, goods could be rapidly moved all over the country in bulk for the first time. Where possible, factories were connected directly to the railway lines, allowing them to bring in a rapid supply of raw materials and to load the finished goods straight onto freight trucks. Often they would reach the markets the day they'd left the factory, increasing turnover and accelerating the Industrial Revolution. National newspapers saw a massive growth too. Whilst they had existed before the railways, they would be several days out of date by the time they could reach the far ends of the country. Now they could be distributed everywhere the day they were printed. Food too was revolutionised. Up until now, it had only been possible to eat what was produced locally and in season. It was possible to transport by coach, but expensive. Now rapid transport, along with better preservation methods, allow consumers a much richer choice of diet. Even such iconic meals as fish and chips were largely exclusive to the coasts, until the railways allowed rapid transport inland. The railways also made it much easier to supply the inner cities with food and essentials, making urban living a lot more comfortable. And the railways seemed to stimulate growth wherever they went. Raw materials became cheaper for industries. It was possible to connect with new markets and new investors. The railways also brought in no shortage of customers for local businesses. The railways themselves provided no shortage of employment too, and employment opportunities were boosted further as it was now practical to commute to work for the first time, allowing families to seek work in another town without having to completely uproot themselves. When the Stockton and Darlington Railway was extended to Middlesbrough in 1830, the hamlet had a population of just 40. By 1851, it was a thriving port town with a population of 7,600. Not only did the railways boost the growth of towns, they also built some almost from scratch. Places like Swindon and Crewe were sleepy villages when the railways came through, but seemed like the perfect place to house the workers. The railway companies made sure to provide well for them, building not just housing, but also schools, hospitals, places of worship, and communal areas for the workers and their families. This kept the workers happy and meant that there was no alternate employer around if the workers did wish to quit. The railways also created whole new types of businesses. One such example revolves around a Quaker minister from Leicester called Thomas Cook. In 1841, he was planning on visiting a temperance rally near Loughborough. He wanted to bring as many of his congregation and fellow teetotalers with him as possible, but he knew that some would struggle with the rail fares. He was able to do a deal with the company for him to bulk book seats at a reduced rate. He then sold around 300 of them, organising a big party to bring along, and made a tidy profit for himself. This got him wondering if he could make a business doing this, and he rapidly began planning similar excursions to other parts of the country. In time, he would expand into arranging meals, entertainment, activities, and accommodation, and selling this all to the guests in one payment. He thus invented the package holiday, and the Thomas Cook Company would remain a staple of the travel industry until 2019. By 1841, what had once been a scattered collection of lines had now formed into what could properly be described as a network. It was clear that the railways were there to stay, but it was also clear that the companies could no longer operate in their own bubbles. Agreements would have to be reached between the owners to create a standardised service across the country.
The railway companies of the 19th century worked quite a bit differently from today's. Today, Network Rail own the tracks and sell contract to the train companies who own the trains to run services on them. But back in the 19th century, the companies owned the tracks, trains, stations and all. As the lines began to meet up, passengers would increasingly have to travel with multiple different companies in order to get to their destination. and the passengers didn't much enjoy having to change trains and buy new tickets every time they passed from one company to another. To make travel more attractive, one company's trains would have to run on the other's tracks. But that required a deal to be struck between the companies. This was done on an ad hoc basis and was becoming increasingly difficult to manage, especially as a journey could require 3 or 4 companies to come to an agreement before it could be run. It didn't help that systems varied wildly across companies. Each operated a different signal system, a different fee per kilometre, and often even their equipment was incompatible. If a train broke down in the wrong part of the country, there would be no spare parts available. It was clear that an independent body was needed to coordinate their efforts. It was to this end that 9 companies got together in 1842 to form the Railway Clearinghouse. The clearinghouse worked fast to create standardised systems and equipment across the companies, setting a manual for signalling and communications procedures, and standards for the engines and the carriages, which would allow each train to run anywhere in the country with a minimum of disruption. They had no legal power to enforce these decisions and could only recommend, but the rail companies knew it was in their best interest to follow them, since following a set of standards everyone can agree on greatly widens the available market for everybody, and is nothing but good for business. When it came to fares, the companies could handle tickets which ran only on their own lines. Through traffic was handled by the clearinghouse, where whole offices full of clerks would calculate what portion of the fee to allocate to each company, based on how much of each track the passenger had travelled along, as well as which company had provided the trains. In the case of goods services, the time spent processing and loading the goods by each company in their respective warehouses and goods yards also had to be factored in. One urgently needed piece of standardisation was the gauge of the tracks. Brunel's broad gauge lines were the main issue there, but there was also the Eastern Counties Railway and the London and Midland Railway, who'd each decided to build their lines 5 feet wide, or 1.524 metres. Meanwhile in Ireland, all 3 rail companies operating there had chosen to adopt a different gauge. This is all well and good when the lines were operating in isolation, but in 1844 the broad gauge met with the standard gauge for the first time in Gloucester. This created a problem known as the break of gauge. As through traffic was impossible at these stations, the passengers would have to switch trains en masse, a situation which could be quite chaotic. But while this was a nuisance for passengers, it was a nightmare for freight. Every single item had to be individually transloaded from one train to the next, a process which could take up to 7 hours. Brunel sorted things somewhat by doing a deal with the neighbouring company to have the line between Gloucester and Cheltenham converted to mixed gauge, which would allow it to run both types of engine. This relieved some of the pressure on Gloucester. But it was clear these breaks of gauge would come again, and a universal solution was needed. Several were proposed, such as roll blocks, transporter wagons, and even variable gauge engines and carriages. Brunel personally favoured designing carriages and containers to standardised dimensions, which could be lifted off the chassis and placed on another, similar to modern shipping containers. But each solution would likely have caused as many problems as it solved. A decision was needed whether the whole network should be broad gauge, standard gauge, or mixed gauge. The government appointed the Gauge Commission in 1845 to decide just that. In an attempt to sway them, Brunel organised a trial comparing the performance of the best of his own engines and the best of the standard gauge. His trial did indeed show that the broad gauge engines were faster, smoother, more reliable, and capable of pulling heavier loads than their standard gauge counterparts. But no performance advantage could overcome the fact that only 13% of the network was broad gauge at this time, and Brunel was essentially asking for thousands of kilometres of track to be rebuilt. And while broad gauge track was relatively simple to convert to standard or mixed gauge, the opposite was not the case. Rebuilding the standard gauge lines would require every track bed in the country to be widened, not to mention countless bridges and tunnels. It was clear from the start there was only one decision the Gauge Commission was going to make. On their recommendation, Parliament set it in law that all mainline services should be built to the Stephenson gauge without an Act of Parliament. But they made exceptions for those built by Great Western, an exception Brunel took as a green light to do whatever he wanted, and he would continue to build broad gauge services for the rest of his life, likely hoping people would come round to the idea eventually. Parliament also set a standard gauge in Ireland of 1.6 metres, or 5'3", an oddity since none of the rail companies there were using that width at the time. It would become known as the Irish gauge. Other standardisation attempts were less successful. In 1841, a goods train ran into a landslide in Sonning Cutting in Berkshire. The train contained several third-class passenger wagons in the middle, which ended up being crushed between the goods wagons, killing 8 passengers and injuring 17. This led to calls for improvements in third-class travel. In 1844, a minister called William Gladstone proposed a plan for the railways to be nationalised to allow for greater control, but this plan got nowhere. He was, however, able to get the Railway Regulation Act passed in Parliament. This stated that the rail companies must run services on all their routes every day that were open to all classes, charged no more than a penny a mile, averaged no less than 19 kilometres an hour, and provided proper seating and shelter for the third-class passengers. But the rail companies were still afraid that the working classes would trash the trains if allowed on regularly. The majority of companies took advantage of the wording of the Act and ran one third-class train a day in a dead hour. These became known as parliamentary trains. For the time being, poor people would have to stick to travelling by goods train. The Act was, however, successful in improving the quality of the third-class wagons. Keen to avoid another headline-grabbing scandal, the companies began providing more robust coaches with better protection against the elements, and attaching them at the back of goods trains so there was less chance of being crushed. Another accident from this era, which led to sweeping changes, happened at the Dee Bridge near Chester. The bridge had a wooden track bed laid on a series of cast iron beams. Cast iron being quite brittle, wrought iron joists were used to strengthen them, but they were insufficient for the task. Its designer, Robert Stephenson, upped the ante 6 months after completion by ordering a large increase in insulating material to prevent the wood catching fire. The extra load proved too much, and the next day a train passed over the bridge and the beams gave way. The engine itself was able to make it to the far side and race to the next town for help. But the carriages were thrown in the river. 5 passengers were killed and 9 injured. The accident made it clear that cast iron was not suitable for building rail bridges with. However, the standardisation effort which has probably had the most effect on our lives was the introduction of railway time. Ever since the first sundials, every town had its own local time, with midday set as the time when the sun was at its highest, which varies depending on longitude. This wasn't a problem in the days when it took hours to get anywhere. As a traveller reached each new town, they would set their watch, if they had one, to match the church clock, and just follow that time. But with the coming of the railways, travel between towns became much faster, and industrialisation meant that minutes suddenly began to matter. This made timetables especially hard to follow and to draw up. It was comparable to air travel in the modern age, but with a lot more variations. Trains travelling east also appeared to be travelling faster than those travelling west. For the Great Western Railway, which covered more longitude than most lines, the situation was especially complicated. To simplify the timetables, in 1840 Brunel ordered for every station to match its time up to Greenwich Mean Time. Most rail companies followed suit. In 1847, the Railway Clearinghouse endorsed the idea and recommended it across the board. Soon the whole network would be brought into line. For a while, many towns operated 2 separate times, with 2 minute hands on the town clock, but this led to a lot of confusion. And with so much of life beginning to revolve around the railways, towns and cities began adopting railway time as the town time as well. It was reported in 1855 that 98% of cities followed the railway time, but there were some exceptions. Though Exeter Council had voted to adopt railway time, the Dean of Exeter College, where the town clock was, refused to change the time on the clock for many years. In Oxford, though the town adopted railway time, the university did not for many years, much to the confusion of students. To this day, Big Tom Bell in Christchurch, which used to signal the 9 o'clock curfew each night, continues to ring at its traditional time of 9:05 GMT. Finally, in 1880, Parliament passed the Statutes of Time Act, which set Greenwich Mean Time as the standard across the country. Within a generation, the concept of local time had faded away. After the initial surge in railway building in the 1830s, the 1840s initially saw a lull. The economy was slipping, and the banks were reluctant to invest in schemes. But by 1844, the economy had recovered. What's more, the Bank of England had cut interest rates, making government bonds less attractive for investment. Looking for something else to invest in, investors turned to the railways, an industry with calls for expansion across the country, and there was plenty of wide open country for it to expand into. Values of railway shares shot up, and before long there was a mad scramble to invest in new lines. With the money now coming in, new lines began to be proposed more and more frequently, some by the existing companies, but others by new start-up businesses eager to get in on the market. Such was the scramble to claim parts of the country before anyone else, that many entrepreneurs would grab a ruler and draw a line on a map between two cities they wanted to connect, with the promise to work out a route later. And such was the rush for investors to get in on the market that many of these schemes got the green light anyway. Of course, Parliament had to approve the schemes, but many of the MPs there had railway shares themselves, and were only too happy to rubber stamp the schemes since it meant their own shares would increase in value. At the heart of this all was the MP for Southampton, George Hudson. Already the owner of the York and North Midland Railway, in 1844 he was able to organise a merger with 3 other companies to form the Midlands Railway, the first major rail empire. He rapidly began buying shares in other companies, expanding his interests and drawing in investors for every project he put his name to. What the investors didn't know was that Hudson was essentially running a pyramid scheme. He was paying dividends to shareholders in capital rather than revenue. He used backroom dealings in Parliament to delay the start of many projects, and then used the money invested in these new projects to fund previous ones. He operated plenty of other dodgy dealings, such as taking out loans to get the projects going with money he didn't really have, selling land he didn't really own, and using his various business acquisitions to buy shares in each other, fiddling with their market values for his own ends. Hudson could claim he was technically operating within the law, but this was only because the railways were growing faster than the government could regulate them. The financial bubble would collapse soon enough, but for the time being, the railways could ride the wave of investment and expand at their greatest rate ever. Oxford and Cambridge were each connected to the network around this time. This had the effect of putting the 2 universities on a par when it came to communications with London. Until then, Cambridge had had to rely on a roundabout system of waterways, while Oxford had been able to access travel directly down the Thames. London also gained speedy connections with the various ports along the south coast. Early lines in Scotland had been short and largely built around goods transport, but in 1842 the first direct link opened between Edinburgh and Glasgow, and it was a great success, proving there was a demand there. The next question was, could they link with England? 2 rival schemes were produced, the North British Railway along the coast of Berwick-upon-Tweed, and the Caledonian Railway, which went south to Carlisle. The North British Railway reached Berwick in 1846, but a bridge wouldn't be built across the river for several years. In 1848, the Caledonian Railway met up with the Lancashire and Carlisle Railway in Carlisle to form the completed West Coast Main Line. For the first time, it was possible to travel from London to Scotland without changing trains. At the same time, other companies were constructing lines extending the network north to Stirling, Perth and Dundee. The 1840s also saw experiments with the concept of atmospheric railways, an attempt to use air pressure to pull the carriages along rather than traction. Essentially, a long pipe would run between the rails, with a slit in the top, but 2 strips of leather and grease used to create an airtight seal. A plunger would be placed in the pipe and attached to a rail carriage overhead. Stationary engines would be used to pump air into the pipe behind and out of the pipe ahead, driving the carriages along. The concept was based on the sound principle that much of the power output of a steam train goes into moving the engine itself. By taking the engine out of the equation, it seemed that more power could be put into moving the carriages. Experimental lines around 1 kilometre long were built in London, Dublin and Kingston. These attracted the attention of some railway pioneers who began planning much longer routes. 8 kilometres of the London and Croydon Railway were converted to atmospheric, but most ambitious of all was Brunel's South Devon Railway, running 25 kilometres from Exeter to Newton. It is also generally agreed to be Brunel's biggest mistake. The engines were not as powerful as had been hoped, unable to pull more than a couple of carriages at a time, and each engine couldn't handle more than a couple of kilometres of track. It soon became clear that they actually required a lot more fuel and a lot more power than the mobile engines. The system also proved hard to control, and the carriages would frequently overshoot the stations. But the biggest problem by far was the seal. Try as they might, the engineers could not come up with a design and a type of grease which would maintain a proper airtight seal, and which was not affected by the weather and by trains disturbing it several times a day. Within a few months, pretty much everyone involved, including Brunel, had admitted failure, and the route was converted to standard traction. The London and Croydon Railway, which had much the same problems, followed suit soon afterwards. 1848 was the greatest ever year for track building, with around 1,800 kilometres built. It was also the year when the railway bubble finally burst. There was simply not enough capital to spread around too many projects. What's more, the Bank of England had raised interest rates again, and now government bonds were much more attractive for investment, and the investors started moving back towards them. Of the hundreds of schemes that had been approved by Parliament at the height of railway mania, around a third would never see the light of day, and many new rail companies were rapidly driven out of business, forced to sell their line to the bigger companies for a pittance. The biggest losers were many middle-class families who'd invested their life savings in this expanding market, only for it to collapse overnight. George Hudson's dodgy dealings were also brought to light. His investors deserted him, and his loans were called in. This forced him to sell his remaining railway assets. Still deeply in debt, he fled to France to avoid arrest. He would finally return in 1865 and be thrown in a debtor's prison. The capitalist boom and bust cycle will continue for the railways for the rest of the century, but greater regulations and smaller areas of open country meant that there would never again be such wild swings as there were in the 1840s. Unlike most financial bubbles, the railway mania left behind a lasting product in the form of the railways it had built. The markets would soon recover, and the railways would be stronger than ever. The 1850s was a period of continued growth for the railways, most prominent among which was the East Coast Main Line. 3 different companies were working on different sections of the line. The idea had been one of the last bankrolled by George Hudson before his railway empire collapsed. Despite the loss of his funding, the vast majority of the route had been completed by this time, and so the project continued unabated. In fact, by 1849, the only major breaks were across the Tyne and Tweed estuaries. For several years, passengers would have to disembark, cross by ferry, and then catch another train, since bridging the rivers proved a challenge. The Tyne proved a particular problem. The route went through the middle of Newcastle in order to service the city, but with Newcastle being a major port, the bridge would need to be high enough and with pillars space enough to allow sailing ships through. What's more, the bed of the Tyne is very soft and thick mud. In order to reach a stable base, Robert Stephenson had to design pillars that were 34 metres bottom to top, and wide enough to withstand currents and wind. The spans themselves were designed to the bowstring principle, in which an arch section is supported by a series of vertical buttresses in order to keep the track as rigid as possible. It was feared that too much vibration would destabilise the trains. The bridge was also designed to suspend a road bridge underneath. The bridge was opened by Queen Victoria in 1849, with the ceremony being followed by a large meal. According to some accounts, the Queen was upset about being handed the bill for the festivities, having not been consulted about it beforehand. She vowed never to look upon Newcastle again. For the rest of her life, whenever the royal train passed through the city, she would close her curtains until they'd passed. Only the Tweed now stood in the line's way. Here, Stephenson was busy building the Royal Border Bridge. The river ran through a steep valley, which required Stephenson to design one of the largest viaducts in the country. 659 metres long, sitting 34 metres above the water, with 28 arches. The construction took 3 years, used 227,000 cubic metres of stone, 2.5 million bricks, and 2,700 workers. The bridge was finally opened in 1850. From the new terminus at King's Cross, it was now possible to catch speedy direct trains to Peterborough, Doncaster, York, Newcastle and Edinburgh. Stephenson faced other challenges with bridge building. The Chester and Holyhead Railway required a bridge to be built linking Anglesey with the mainland. The Admiralty once more required the bridge to be built to a high level. As there was only one island to build off, the spans would have to be 140 metres long. Stephenson designed 2 long parallel tubes, walled by iron box sections, to maintain their rigidity, with the track running through the middle. A wooden roof was placed over the top to shield the iron from the weather. The bridge was the longest single-span iron bridge in the world at the time. Concerned about his own designs, Stephenson conducted extensive tests with scale models in order to ensure that the bridge would hold. Friendly rival Isambard Kingdom Brunel was there to watch its construction, and commented to him that if the bridge succeeded, all of his would be considered failures. But succeed it did. The bridge opened in 1850 and stayed in operation until some schoolchildren set fire to the roof in 1970. Brunel took inspiration from Stephenson for many of his own bridges. In 1849, his work on the Slough to Windsor branch line required a crossing of the Thames. He designed the Windsor Rail Bridge on the bowstring principle. The construction of the South Wales Railway allowed further innovation in Brunel's bridge designs. Where the line crossed the River Wye at Chepstow, he designed a tubular bridge, which may not look innovative by modern standards, but was revolutionary and widely praised at the time for its lightweight design, requiring a lot less material than Stephenson's almost solid-sided bridges. The main support came from 2 huge iron tubular sections supported on the pillars overhead. The main track was suspended below, with cross-bracing across the rods to keep flex to a minimum. Brunel's favourite bridge building material, however, was wood. At the Swansea Valley, he designed his largest wooden bridge, the Landor Viaduct, 536 metres long. Like most wooden bridges on the network, however, the bridge has since been rebuilt in various metals. But his most famous bridge from this era is the Royal Albert Bridge near Plymouth. Once more, the Admiralty set a minimum height and span width. Brunel expanded on the concept of the Chepstow Bridge and the Windsor Bridge and designed a double bowstring to sit across the pillars, cross-braced for added rigidity, with the main span suspended beneath. A solid construction, as well as an aesthetically pleasing one. Another of Brunel's projects, the Campden Tunnel, became notable for the wrong reasons. A part of the Oxford, Worcester and Wolverhampton Railway, the construction of the tunnel had been subcontracted to a company called Ackroyd's, owned by Robert Marchant. But Great Western were becoming exasperated by Ackroyd's slow progress. Their contract was cancelled, and Brunel was ordered to take direct charge of construction. Marchant took this badly, and he and his navvies barricaded themselves in around the site. Brunel responded by gathering navvies from elsewhere in the line to sort him out. Whether he was planning to take the place by force or simply make a show of strength is not clear. The local constables separated the two sides and read the riot act twice. Brunel's mob withdrew. Thinking that this was the end, the police went home. But both sides gathered reinforcements overnight, and returned the next day before the police could stop them. The local magistrate spoke to Brunel, who agreed to help hold his navvies back. Nonetheless, mob skirmishes still broke out, resulting in broken bones on both sides, but no fatalities. Eventually, Marchant realised that Brunel's 2,000-strong mob outnumbered his 20 to 1. Seeing how hopeless his position was, he agreed to give himself up. At the same time, Great Western agreed to compensate his company better. Brunel would resign as engineer on this line a year later due to disagreements with the Oxford, Worcester and Wolverhampton Company, who wanted to build the line to standard gauge rather than the Brunel gauge. And that was far from the only disagreement he was having on the subject. He continued to insist that broad gauge and standard gauge could coexist, but increasing numbers were disagreeing, and this was putting a strain on Great Western's business. While other companies could expand by buying existing lines of smaller companies and just running their services down them, Great Western would have to completely rebuild the track before they could do so. What's more, since most of the network was standard gauge, that was where most of the innovation in train design was happening, so now the broad gauge could no longer even claim to have the performance advantage. With their business suffering, Great Western's board of directors tried to unseat Brunel. Nonetheless, he still had enough supporters to allow him to continue his schemes until 1859. Despite the drawback of the broad gauge, Brunel's railways were a great success. By the end of his life, he had created a railway empire as far north as Wolverhampton, as far east as London, and as far west as Truro and Neyland. The 1850s also saw the first uses of railways in warfare. In 1854, British troops in the Crimea built a new railway for the purposes of rapidly moving supplies and reinforcements from the main supply port at Balaclava to their siege lines outside Sevastopol. The rapid supply proved a godsend for the troops stuck in the trenches. Later, in the Indian Rebellion, the British were able to make use of several railways to speed troops up from Calcutta to the main trouble spots and help put down the rebels. But it was not until the American Civil War that the full potential of railways in warfare would be revealed. Back home, the network was continuing to grow. England was becoming much more interconnected. In Scotland, numerous companies were constructing a string of lines, extending the network as far north as Aberdeen and Inverness. In Ireland, too, the network was shaping up, with lines built connecting Dublin with Belfast to the north, Galway to the west, and Cork to the south. As the network grew, so too did the amount of time the public would spend sitting on trains each week. This led for increasing need for something to do other than staring out the window. There were newspapers, of course, but longer journeys demanded something more substantial. There was clearly a market for selling books to passengers. Bookstalls had begun to spring up outside stations almost as soon as the railways had got going, but these stalls varied wildly in quality and pricing. Often, the stall owner would be the only one at a particular station, and would take full advantage of their captive market. What's more, many of these stalls were selling books whose contents featured many subjects that the conservative Victorian public found particularly shocking to read. This was a bit of a problem, as many travellers had insufficient time to inspect the books properly at the station, and didn't really know what they were buying until they were too far away to do anything about it. Struggling to regulate these stalls, the railway companies decided that it would be much simpler if they could contract a single company to run stalls at their stations and liaise with them directly. In 1850, this contract was awarded to a man called William Henry Smith. Smith had opened his first W. H. Smith bookstall outside Euston in 1848, selling books, newspapers and snacks to travellers. In 1850, he opened new stalls in Birmingham and Manchester as well. Before long, every major station in England and Wales had one of his bookstalls outside. As the business grew, the lease on many of the stalls would run out. It was soon found to be more cost-effective to buy permanent properties on nearby high streets. The increased space meant that the company could expand into things like stationery and games. Thus it was that the railways created Britain's first chain shop. The railways had a revolutionary effect on literature in general. At the start of the 19th century, the country's major publishers were all concentrated in London, Oxford, Cambridge and Edinburgh. and that was where the vast majority of books published were sold. An author's work would travel very slowly. Now, with the ability to transport materials and skills faster, it became easier for publishers to set up facilities to manufacture and to distribute the finished product. For the first time, an author could have their books sold throughout the country within days of being published. The railways also provided a great source of inspiration for writers. Readers read tales of communities devastated by railways tearing through their towns, characters hopping onto trains to seek their fortune elsewhere, romances springing up between people who'd happened to sit in the same compartment, murder mysteries and spy thrillers that revolved heavily around the trains and their operation, tragic accidents on the railways, and ghosts haunting the sites afterwards, railways used as a jumping off point, carrying characters off to adventures in far-flung parts of the country, or even into magical lands, and tales of dashing heroes rescuing screaming damsels that some nefarious villain had tied to the tracks, escaping together by train, being pursued and getting into close-quarter fights in the compartments, or epic fights on top of the train, and finally leaping away to safety, always surviving somehow. Of course, reality can be as strange as fiction. One case in point is the Great Gold Robbery of 1855. The South Eastern Railway would often carry consignments of gold from businesses in London down to Folkestone en route to Paris. The safe carrying it would be sealed with 2 locks, and kept shut until it reached the far end, where agents in Paris had identical keys. The safe would be periodically weighed and checked for tampering. No one was allowed to possess both keys at the same time, and if one key was lost, the locks would be immediately changed. But some thieves managed to bribe the man responsible for changing the locks, who gave them copies of the keys. They also recruited a guard who was disgruntled about having his pay cut. The guard signalled to them the next time the train was carrying gold. They put their bags, containing a quantity of lead, in the luggage coach. One of the thieves then hid there and broke into the safe as the train was moving. He replaced the gold with the equivalent weight of lead and reconstructed all the seals. The 2 of them then walked away with their bags, now containing 102 kilos of gold. The theft wasn't discovered until the safe was opened in Paris. Nonetheless, the conspirators were caught within 2 years and sentenced to hard labour. By 1859, almost every major city in the country was linked into the network, but transport in the inner cities was still largely horse-drawn. The 1860s would see the railways revolutionise inner-city transport in many ways. Even in the earliest days of the railways, the government was concerned about air pollution. They had passed a law early that any mobile steam engine must consume its own smoke, but the way the hot smoke would travel up the flues made this difficult to do. While engineers wrestled with the problem, operators burnt smokeless coke instead. But in 1860, a railway engineer called Matthew Kirtley devised a simple and cheap way to allow a furnace to consume the smoke using a deflector plate and a brick arch to draw air into a separate chamber above the firebox where the smoke would be burnt off. Trains can now safely burn coal, allowing the fires to burn hotter and thus the train to travel much longer and faster. Around the same time, engineers were constructing a means of allowing trains to pick up water without stopping. This was done by placing a trough between the tracks and a scoop under the engine to pick up water as the train went along. Faster trains and fewer stops provided a boost to services and allowed for the network to continue to expand, pushing further into the Highlands of Scotland and Wales and linking up the big towns and cities in England much more. But while the big towns and cities were linking up, for many rural communities there was a problem. Their low population meant that it would not be cost effective for the railways to link to their villages unless they were lucky enough to be between 2 population centres. With so much life now revolving around the railways, this was leaving the communities increasingly isolated. The Festiniog Railway in Wales provided a solution. The line serviced a local slate mine through horse-drawn trucks pulled along a narrow-gauge 0.597 metre track. In 1863, local engineers designed a steam engine to run on the tracks. This wasn't the first narrow-gauge line in Britain, but it was the first to take passengers. The idea quickly caught on, and many more lines were planned across the country, to handle the local traffic and goods. Narrow gauge trains were slower and less powerful than their mainline counterparts, but they were cheaper to build and to run, and could handle tighter bends, meaning that the lines could weave their way through the countryside much more easily. This helped resolve the local traffic in the countryside, but in the cities there existed an ongoing problem. Due to town councils' efforts to keep the noisy, smelly railways as far away from the rich parts of town as possible, many cities were primarily served by stations that were several kilometres from the city centre. Not only was this inconvenient for travellers, but it created traffic jams due to the large numbers all needing to go the same way. Where there was more than one station, the problem was compounded by the masses needing to transfer to a new train. In London, things were particularly bad. Numerous companies wanted to service the capital, and unwilling to share stations, they had built a ring of termini all around what was then the edge of the suburbs, often right next to each other. This meant that the city was full of people pushing past each other to reach their destination, or to change trains. It was easy for them to get lost, as they were often unfamiliar with London's street layout, and the train companies would rarely provide directions to other companies' stations. A solution was needed to allow the railways to shuttle people to the city centre without disturbing rich people. An idea came from America. New York in the 1830s had few paved roads, and the streets could turn into a quagmire in the winter. To help overcome the mud, in 1831 a railway was laid down the middle of 4th Avenue as far as 32nd Street, dug into the road to avoid inconveniencing other road users, and with horse-drawn carriages to keep noise to a minimum. This was the world's first tramway. The idea quickly spread in America, where the wide streets and grid layout were ideally suited for trams. But it was slower to catch on in Europe, where the older streets tended to be narrower and windier. Britain's first urban tramway was built in Birkenhead in 1860, introduced to the country by an American engineer appropriately named George Francis Train. Others had been proposed and were in negotiation at the time, but Train managed to get ahead of them by finding a loophole. The law required for Parliament to approve any permanent railway, and that included urban tramways. This being an untested concept in the country, the government were shuffling their feet on the matter. Train had neither the business skill nor the patience to get parliamentary approval for his schemes, but he noted that councils could approve short temporary routes without having to go through Parliament. He reasoned that he could build such a route and make it popular enough that businessmen would invest in the scheme and gain enough voice to get it through Parliament. After building his first route in Birkenhead, he wrote to as many councils as possible, mainly in London, reasoning that his plan only had to work once. 3 of his London schemes were approved, along with some in Darlington and the Potteries. They quickly became popular with residents, much faster, smoother, and more spacious than the omnibuses on the country's cobbled streets. But they failed to impress the businessmen he was hoping to get on his side. They tended to have their own carriages and found Train's trams to be a nuisance, especially since he built most of them in the posher areas of town and failed to segregate them into classes. He also faced opposition from the hackney carriages and the omnibuses, which feared a loss of business. Train didn't do himself a lot of favours by ignoring the standard practice of digging the rails into the road. He insisted on using his own patented step rails, which protruded above the ground, meaning his opponents could legitimately claim they posed a hazard to pedestrians and other road users. All of his tramways were torn up within a few months. Things got worse in 1862, when his opponents were able to convince the authorities that Train posed a public menace. Parliament retroactively decided that he actually did need their permission to build temporary routes, and had him arrested for not doing so. The public, who loved his trams, organised a petition with 11,000 signatures. Kington Crown Court ignored this petition, and Train was fined £500 and forced to shut down his tramway early. He left the country in humiliation. It has been argued by some that Train actually set back the introduction of tramways to the country. So urban tramways were out of the question for the time being, but there was still clearly a market for inner-city rail solutions. One idea that was proposed was to build trains on overhead viaducts above the streets, but that was dismissed as the residents of London wanted the trains to be as invisible as possible. The solution was to build tracks below the streets. The Metropolitan Railway began construction in 1860, connecting the termini at Paddington, Euston, King's Cross, and the under construction St Pancras, and then continuing down to Farringdon. Most of the early tunnels were actually simple to dig and required no new tools. They were done using the cut and cover method, in which a long trench would be dug into the street and track laid at the bottom. A roof would then be built over the top and covered over. The construction was not without its difficulties. One of the worker trains exploded, killing 2 people, and the Fleet sewer burst in 1862, flooding part of the tunnel and delaying construction by several months. Of course, running steam trains in a fully enclosed network brings with it a rather obvious problem. To reduce smoke, an engineer called John Fowler designed a system wherein the firebox would be loaded with hot bricks and the boiler brought up to pressure at the start of each journey, so there was no need to stoke the fires. Experiments were run, but the train was found to cool far too quickly to be of use. It became known as Fowler's Ghost. Instead, a system was designed in which coke would be burned to keep smoke to a minimum. The steam would be condensed and fed back into the boiler. The steam could then be vented by the driver pulling a lever when the train reached an open section in the tunnel. In some places, this opening took the form of a grate in the street, causing a nasty surprise for anyone unfortunate enough to be walking over them at the wrong time. In others, entire sections were open to the air, with false house fronts built around them to keep the railway out of sight. But when the line was opened in 1863, it was found there were simply not enough openings, and the drivers often had no choice but to open the vents in the tunnel as the pressure got too much, choking the passengers in the open trucks. Things got worse 6 months later. The line had originally been owned by Great Western, who had built it to mixed gauge in the hope of linking it directly to their main line. But the Metropolitan Railway broke away from Great Western in August 1863 and decided to switch to standard gauge only. They withdrew the broad gauge locomotives and replaced them with tank engines purchased from Great Northern, which turned out to be even worse at condensing steam. In time, the Underground Rail companies would make great improvements in the performances of these engines and build more ventilation into the tunnels, but it was a problem they were still wrestling with up to the point when the lines were electrified. Despite the smoke and the long staircases without escalators, the railway instantly became popular with Londoners and tourists, many of whom would ride the line back and forth all day in wonder. The line recorded 9.5 million passengers in its first year, expanding to 12 the year after. By the end of the decade, the Metropolitan had expanded to Moorgate, Kensington, Hammersmith, and Swiss Cottage. At the same time, the rival District line had opened between West Brompton and Blackfriars. Open trucks were used early, under the logic that there was no weather to shield the passengers from. This was quickly abandoned and replaced with more standard carriages for greater comfort. They lacked windows at first, since there was no view, but it was soon realised passengers would still need to see out, both for comfort and to know when they'd arrived at a station. Of course, even when they'd arrived, many passengers still had difficulty knowing where they were, since a large proportion of the population couldn't read, and they had no landmarks to go off. The solution was to create landmarks in the form of patterns of coloured tiles at each station. No 2 stations would have the same colour combinations, making it simple for passengers to know at a glance where they were. One of the ways the London Underground tried to limit smoke was to ban smoking on the network. But this was stumped by the Railway Clearing House in 1868, who passed an act requiring all trains to provide at least one smoking carriage. Tobacco smoking was soaring in popularity, and it wasn't unusual for trains to run with nothing but smoking carriages. Surprisingly, even non-smokers would frequently seek out the smoking carriages due to a mistaken belief that smoking would kill off microbes and miasmas in the air. The last smoking carriage would not be withdrawn from Britain's network until 2004. It is interesting that Great Western built the Metropolitan line in mixed gauge, as they had already taken the decision by now to phase it out. Brunel had died in 1859. After a reasonable period of mourning, the company set about reversing his policy on gauges. Significantly, in 1861, they converted their main line between Paddington and Reading to mixed gauge, so as to better link with another of other companies that Great Western had acquired in the southeast. But replacing all their track would take a great time and expense to complete. It would, however, leave Great Western with plenty of space and make it easier to widen the lines later. The London Underground lacked the space to separate classes fully, making it one of the first railways to be as accessible to the working classes as to the upper classes. This was a concept which would soon spill over to the rest of the network, creating a social revolution almost as vast as the initial coming of the railways. While the engines had been getting faster and more powerful over the decades, the humble carriages had seen few improvements, besides getting a bit bigger. But the 1870s would see many significant changes. Oil lamps were now becoming commonplace in carriages, which had previously been lit only by candles the passengers had brought with them. Gas lamps were also introduced around this time. In 1879, the first Pullman dining coaches were installed by Great Western, allowing passengers to enjoy a hot meal on the go. There were still no connections between carriages, so passengers who wished to eat would have to hurriedly change places at the stations. On the other end of proceedings, toilet stalls began to appear in coaches. One drawback was that passengers had to be in the right compartment in order to use them. Everyone else was limited to the chamber pots under their seats, the contents of which would be thrown out of the window, preferably in a sparsely populated area. Those with a bit more money, who wanted all of this in one place, could book a private carriage for themselves and their nearest and dearest, with luxury furniture, refreshments, and separate compartments for servants' quarters, toilets, beds, and occasionally baths. Where it was necessary to change trains, they could pay a bit more money to have their coach detached from the previous train and shunted onto the new one without themselves ever having to get out, though this could only be done where it wouldn't interrupt schedules. The private coaches had in fact been offered by Great Western as far back as 1838, but they had initially been unpopular. The rich preferred to ride in their own carriage, which would be loaded onto the back of a truck with them still inside. But as trains got faster, this arrangement had become increasingly precarious, and rich travellers had shifted to the private coaches instead. Officially, some companies offered the service as far as the First World War, but by the 1880s, accounts of it actually happening are few and far between. It wasn't only the rich who were seeing improvements. In the early days of the railways, third-class passengers were rarely allowed on the mainline services. The only way they could travel was in open wagons attached to goods trains, or in parliamentary trains which ran in dead hours. But as trains became cheaper to run, it became profitable to sell third-class tickets, and companies gradually came to realise what an untapped market they were missing out on, and so third-class services became increasingly common. What's more, old first-class carriages have been superseded by newer, nicer ones, which meant they can now be rebranded as third class at minimal cost. In 1872, the Midlands Railway became the first to offer third-class tickets to all its services. Profits soared, and all other companies soon followed suit. With first class becoming grander, and third class becoming more available, second class was rapidly waning in popularity. Among the middle classes, those with money who wanted a better experience typically chose first class, while those who wanted to get where they were going cheaply typically chose third. Second now seemed like an unnecessary middle ground. The rail companies initially tried to encourage people to spend a bit more and get a second class ticket by making third class seem as unattractive as they sensibly could. They would, for instance, hire chimney sweeps to sit in third class carriages to ensure that they would maintain a grubby appearance. Nonetheless, second class numbers continued to drop, and third class continued to rise. The law required companies to provide third class services, but there was no law requiring them to provide a second class. In 1875, the Midlands Railway took the decision to eliminate second class altogether due to a lack of demand. Almost every other company followed suit, leaving Britain's railways in the bizarre position where they offered only first and third class travel. The third class would eventually be rebranded as second class in 1956, and finally as standard class in 1980. Switching to a two-class model allowed the companies to up the price of third class nearer to what second class had used to cost, but still within reach of the working classes. This was a great boost to their mobility. Up until now, many of them would live their entire lives in their hometown, and the other end of the country may as well be the moon. Now that their travel was no longer limited to hitching rides on goods trains, they could explore more and seek new opportunities that had previously only been available to those who could afford them. For many families, the new low fares granted them the opportunity to take proper holidays away from home for the first time, taking a weekend trip to the seaside, or visiting friends and family in other parts of the country. The cheaper travel also had a revolutionary effect on sport. At the start of the 19th century, most sporting competitions were amateur in nature, a weekend hobby for people with other jobs. Most sports people would be limited to local cups and friendly games, with nationwide competitions being big events only available to those who could afford to travel to them. Even in the early years of the FA Cup, it was common for teams to have to drop out due to having been drawn away and being unable to afford the rail fares. But now with third-class travel being more available, it became possible for sports people to travel around the country regularly for fixtures, and for their fans to follow them. The later half of the 19th century would see an explosion in nationwide sporting competitions. The FA Cup began in 1872. Wimbledon saw its first tennis tournament in 1877. The Football League started in 1888. The first properly organised cricket league started in 1890. The Rugby League began in 1905. The third-class passengers weren't the only working-class people whose lives were improving on the railways. The workers too were making themselves heard. In 1872, the first properly organised railway workers' union was formed in Derby, with more than 17,000 members, known as the Amalgamated Society of Railway Servants, or ASRS. For its first 20 years or so, the ASRS existed as a friendly society, which deplored strikes, calling them an evil to masters and men. Nonetheless, the ASRS was working to bring changes, publishing the Railway Servants' Gazette as a means of spreading their experiences and ideas. One of their first major jobs was to collect accurate lists of railway worker injuries. The railway companies were required to keep similar lists, but were quite lax in actually doing so. In 1872, the Lancashire and Yorkshire Railway Company reported 73 workplace injuries. The ASRS reported 1,387 in the same company. The ASRS may have been exaggerating, but it is certainly true that the railways were a very dangerous place to work. The 1870s were a peak time for fatalities, averaging 700 a year. The companies had covered themselves nicely by putting statements into worker contracts that each worker was responsible for their own safety. The only time the company could be held accountable was if an accident involved a worker from another company, or a member of the public. While instructing the workers to just be careful is all well and good in theory, in practice it allows employers to force them to work in environments where accidents are inevitable. Most dangerous of all were the goods yards, which were a lot more active and varied than the modern day ones, which made the yards quite chaotic, a problem for the workers dodging between the trains. Harsh weather and darkness made the job even more deadly, not least because there was rarely any lighting in the yards. Workers would just be given a lantern to carry, which wasn't a lot of help for tasks requiring two hands. The shunters had it hardest of all. They were required to uncouple and couple the goods wagons as required, as the long trains were slowly pulled past. This required them to hop up between the wagons, operate all of the catches, and often apply the brakes, which would almost always be on only one side of the wagon. And all of this had to be done in the space of about 5 seconds, giving them little time for care. But with pressure from the ASRS, the companies gradually came to adopt better, safer practices, installing proper lighting in the yards, and introducing shunters poles, which allowed them to operate the catches without having to climb between the trucks. But all of this was handled on the local level and was not universally applied. Solid legislation on worker safety was slow in coming. The Liberal leader, William Gladstone, put forward several bills which would have brought in sweeping reforms, but was blocked by the Conservatives under Benjamin Disraeli, backed up by the owners of the companies who insisted that being responsible for the workers' lives would cripple business, and by extension the economy. Instead, change would have to be made through a series of baby steps, which would take decades to accomplish. The death rate would never reach the 700 a year figure again, but well into the 20th century it was common for yearly fatalities on the railways to number in triple figures. One successful move the government did make in 1870 was to formalise the conditions under which tramways could be built in the country. The Tramways Act required all tracks to be dug into the road, all vehicles to be silent and limited in speed, and for the companies that ran them to take responsibility for the road's maintenance, including, of course, picking up after the horses. The government dealt with objections from omnibus companies by encouraging them to invest in trams as well. That way they could structure their routes to complement each other and avoid direct competition. The trams could provide an improved service on the wider streets, while the omnibuses could service the narrower, windier roads, and stops could be positioned to allow the traffic from each to feed into the other. The Tramways Act also set some standards on steam trams. To avoid disturbing horses, they had to have all machinery covered and maintain the same speed and noise limits as the horse-drawn trams, and also emit no visible smoke. These limits made steam trams difficult to operate, and though they had their applications, they were never as popular as other types. This legislation allowed the popularity of trams in the country to explode after their false start in the 1860s. By 1879, more than 1,000 kilometres of tramway had been built across the country in all sorts of towns and cities. In London, a healthy network was shaping up, both north and south of the Thames. Even George Francis Train was able to return to the country and build his tramways properly this time. The main line services, too, were continuing to grow. In 1877, the St Ives branch line was extended, making it the last piece of broad gauge to be built in the country. At the other end of the country, Trousseau Station opened in 1874, Britain's northernmost rail station. The network was now as close as it ever would be to allowing a traveller to travel all the way from Land's End to John O'Groats by train. But travelling up the east coast of Scotland was still rather difficult. The main issue was the firths of Tay and Forth. A traveller from Edinburgh to Dundee would have to disembark and take a ferry twice, or else take a huge detour inland. Either option would add more than an hour to the journey. The North British Railway particularly disliked the latter option, as it required them to pass passengers over to the Caledonian Railway. The obvious solution was to bridge the firths, but to do so would require engineers to construct what would at the time be the longest bridges in the world. Parliament approved the scheme in 1871, and the task fell to an engineer called Thomas Bouch, who began with designing the Tay Bridge. Bouch had an extensive track record for designing railways and viaducts. Unfortunately, much of his good reputation had been gained by his ability to get a job done quickly and cheaply, not something which was needed here. His plan was to build a series of brick supports, which would be constructed on land, then carried into the river and sunk into the river bed, until they came to rest on bedrock. But after the first 10 had been put in place, it was discovered that the silt became a lot thicker and a lot more uneven towards the centre of the firth than the initial dredging survey had suggested. Bouch adjusted his design. A series of brick caissons would be placed in the river and dug into the bed, then filled with concrete to create a platform, on which a lightweight hexagonal iron frame would be built to support the spans above. He also reduced the number of spans from 89 to 85. The single-track railway would sit on top of the ironwork for the large part, but in the centre were a series of tubular spans, known as the high irons, built that way to allow ships to pass underneath. Unfortunately, whilst Bouch had calculated the bridge's ability to withstand axial loads, such as its own weight and that of the train, he hadn't factored in longitudinal loads, such as the shaking of the train, the currents in the river, or the winds which can reach 90 km an hour in the Tay. Bouch, to his credit, did inquire with the Board of Trade how best to do such calculations, but was told there was no formal process, and at any rate such analyses were not necessary on his bridge, as all the spans were of a sufficiently short distance, under the Board of Trade regulations of the time. The last-minute redesign wreaked havoc with construction, but Bouch would do little to change the deadlines. To make matters worse, Bouch went with the lowest bidder when it came to construction companies, namely Hopkins, Gilts and Company, who were in serious financial trouble themselves, and skimped over unimportant things like materials, buying their iron from highly questionable sources. Despite the ever-growing list of issues, the first trains ran over the completed bridge in 1877. In 1878, the Board of Trade inspected the bridge in calm weather and declared it safe, provided trains observe a 40 km an hour speed limit, a speed limit the drivers would frequently ignore. Surprisingly, the Tay Bridge was hailed as an engineering triumph at the time. Bouch was even knighted for his work. The North British Railway were also thrilled to see their profits up, with a more than 40% increase in traffic along the east coast. Such was the hubris that it led people to blank out clear signs that the bridge was shaking itself to pieces. Locals reported hearing the bridge rattling like mad every time a train went over it, or the wind was up. Meanwhile, workers found themselves constantly having to secure their paint pots and their tools as the bridge would shake so violently from side to side, even sending shockwaves ahead of the trains. They also noticed supports shifting and rivets elongating over time. Many of these comments were brought to Bouch, but he paid them little attention, having become absorbed in designing the fourth bridge. He insisted the Tay Bridge was just settling. Finally, on the 28th of December 1879, on a particularly stormy night, the signal box at the south end of the bridge let a train through. The signalman then went to make some tea, but a visiting friend watched the train go past. He observed sparks on the wheels as it was blown right up against the rails, and as it was travelling out over the bridge, he saw its rear light flare up for a moment and then disappear sooner than he was expecting, but he put this down to the weather. However, after half an hour, the signalmen had heard nothing from the signal box at the north end, and when they tried to raise them on telegraph, they found the line was down. The two of them went out onto the bridge to see what was happening, and they were shocked by what they discovered. Several iron columns had collapsed, throwing the high iron spans above into the Tay, with the entire train encased within, and killing everybody on board, an estimated 75 people. To date, it is the only British railway disaster to leave behind no survivors. The subsequent inquiries placed the blame firmly at Bouch's door, and similar flaws were found in many of his other viaducts, many of which would be subsequently rebuilt. Meanwhile, his plans for the fourth bridge were thrown out. Bouch always denied his guilt, insisting the train must have derailed, a concept which is possible but which there is no clear evidence. At any rate, Bouch was a ruined man, and the grief likely led to his death in 1881. In many ways, the Tay Bridge is the Titanic of bridge building, a once celebrated engineering triumph which was brought down to earth all too quickly, and taught some valuable lessons in the process. The Board of Trade created stricter procedures for ensuring that a structure must be able to withstand longitudinal loads, while structural engineers took on board the fact that a framework must be designed to withstand loads many times what it is likely to experience in its use, just in case something is to go wrong, or someone is to overload it. The Tay Bridge was the deadliest rail disaster to date, but it would have little effect on the growth of the network. passenger numbers will continue to grow, plans to bridge the firths will be renewed, and new technologies will be created to bring further boost to the railways. Though most of the cities in the country were connected to the rail network by 1880, much more remained to be built. Extensions and shortcuts, many of which had seemed impossible to the early rail pioneers. One barrier which needed to be crossed was the River Severn. Though the cities of Bristol and Cardiff were only a short distance apart as the crow flies, anyone wishing to travel between the two was faced with the choices of either taking a ferry or travelling upriver to Gloucester, for centuries assumed to be the lowest point that the Severn could be bridged. But with improved bridging and tunnelling technology, it became possible to build much lower on the Severn, and a bridge and a tunnel were soon under construction. The Severn Bridge was completed in 1879, built on the bowstring principle, high enough to clear most ships, though with one swing section for taller ones. But the strong and unpredictable tides in the Severn and the relatively short spans made a bad combination for navigation. Throughout the bridge's life, many vessels would collide with it. Finally, a barge collision in 1960 demolished several spans, and the rest of the bridge ended up being scrapped. The single-track Severn Bridge would never have been able to handle all the traffic between England and Wales in the first place, and at the same time it was being built, the Severn Tunnel was also underway. At the time, this was the longest tunnel under a river in the world. The concept of a tunnel under a river had first been thought up in 1825 with the Thames Tunnel, engineered by Mark Isambard Brunel, assisted by his 18-year-old son, Isambard. Mark developed a tunnelling shield in which 12 diggers would stand in a grid. Each would have 9 planks, which they could open in turn and dig to a certain depth. That way, the risk of collapse was minimal, and water could only trickle in slowly. Once it had been dug to a certain depth, the shield would be pushed forward, and the walls rapidly shored up. For the Brunels, the digging was a nightmare, beset with delays, financial difficulties, and floods. One particularly bad flood drowned 6 workers, with young Isambard very nearly joining them. The tunnel wasn't completed until 1843, and though it was initially a tourist attraction, it was a commercial failure for Mark. Though it was sold to the East London Railway in 1869, making it technically the oldest tube tunnel. But the concept had been refined over the years, and now it was ready for the task of digging under the Severn, presided over by Sir John Hackshaw. Despite a number of minor floods and accidents, the tunnel made good progress, and the two ends were less than 100 metres apart when diggers on the Welsh end accidentally opened up a large underwater spring. A shield was placed over the leak, and the pumps appeared to be getting ahead of the flooding. However, the main pump broke down one day, and the tunnel flooded rapidly. In their haste to escape, one of the miners had left a key watertight door open. It would need to be closed in order for the tunnel to be pumped dry. But to do so would require the divers to drag 300 metres of air hoses through the tunnel. They tried travelling in teams, but were unable to carry the pipes all the distance. Luckily, Hackshaw had heard of a Lieutenant Fluce in the Royal Navy, who had an experimental free diving suit. After several attempts, the divers were able to reach the door and seal off the spring, finally allowing the tunnel to be pumped dry. The tunnel was completed in 1886, providing a high-speed link across the lower Severn for the first time. At around the same time, the new Tay Bridge opened in Scotland, built on much wider, tougher supports. What was left of the original was demolished, leaving behind only the stumps alongside the new bridge. But the most spectacular bridge from this era was across the Firth of Forth. With Thomas Boucher's designs having been thrown out, the project was taken over by Sir John Fowler, who designed a cantilever bridge. From each of the 3 pillars, 4 main support arms extend on each side. The 2 at the top are in tension and form triangles with the 2 at the bottom, which are in compression. A similar arrangement on the far side keeps the column in equilibrium. A lightweight tubular span then connects each together. Fowler and two fellow engineers illustrated the concept to the press using chairs, bricks and broom handles. The bridge is 2,467 metres long, with the longest span being 520 metres, a world record at the time it was built. The bridge required 55,000 metric tons of steel and was held together by 6.5 million rivets. At peak construction, 4,600 people were employed in the bridge. 73 of them lost their lives in the construction, and 510 were injured. A monument was set up to them in 2005. The first trains ran over the bridge in 1889. A few months later, the bridge was opened by the Prince of Wales, who drove the last golden rivet. The bridge was now officially completed. But completed may not be the operative word. The steelwork was so vast that it took 4 years to paint, and the paint that was used would only last 4 years, meaning that once the painters were done, they would have to go back and start again. In Britain, painting the Forth Bridge has become a term for any unending task. But better paint was created which lasted longer, and the task of painting the Forth Bridge was finally completed in 2002. Not every innovative railway from this era captured the public imagination quite so well. In 1881, French engineer Charles Latrigue was struggling with the task of building a railway through the soft sands of Algeria. He hit upon the idea of building a single track raised on a series of A-frames so that the sand couldn't blow over it. Engines and carriages would hang off either side, balancing the train. He built a 50-kilometre stretch of this track in Algeria and was looking for funding to get it extended, so he put on fairs in several cities, including London. The British had no interest in helping the French to colonise Africa, but the MP for Kerry, whose constituents were asking for a light railway, commissioned Latrigue to build one there, reasoning that it would be cheaper than a conventional line. Thus it was that the towns of Listowel and Ballybunion gained the world's first public monorail. The line presented unique challenges. Simple things like points were very complicated, and traditional level crossings were virtually impossible. Elaborate drawbridge arrangements had to be built to allow road traffic to pass. But the main issue was the fact that the carriages had to be perfectly balanced in order for the line to work. Guards had to dictate at every station where every passenger and every piece of luggage would be placed in order to maintain the balance. This was made harder by the fact that there was no way to walk through the carriages, so half the passengers would have to climb over the roof. The idea never caught on. Nonetheless, the railway stayed in operation for more than 30 years, before it was destroyed in the Irish Civil War. But whilst monorails would never really catch on, another idea was starting to creep in which would provide the biggest shake-up to the railways since the rocket, and that was electricity. The first electric motors were built in the 18th century, as physicists discovered that an electric charge running through a bar will produce magnetic flux in a helical pattern around it. How this is harnessed into rotation varies, but at its most basic, the bar is bent into a rounded square and mounted on pivots between two stationary magnets. The magnetic forces on one side of the bar will attract the forces passing between the two poles of the stationary magnets and repulse on the other. This will cause the loop to spin. Specially designed connectors allow the current to change direction every half turn, thus keeping the rotation in the same direction. In 1837, Robert Davison of Aberdeen placed electric motors in a rail truck, which he named Galvani. He displayed it at the Scottish Society of Arts, but the batteries he used to power it ran down very quickly, and his machine was frequently unable to pull even a single carriage. He continued his experiments, boosting the power slowly, but was cut short by workers from the Edinburgh and Glasgow Railway who wrecked his machine in 1841, fearing it would threaten their jobs. However, experiments continued. The first successful electric railway was built outside St. Petersburg by Fyodor Pryotsky in 1875, using a brush attached to an electrified third rail to pick up power for the motor. In 1883, Magnus Volk built a 400-metre stretch of railway in Brighton, Britain's first successful electric railway, and the oldest surviving in the world. Just a few months later, the Giant's Causeway and Bromhill Railway opened in Ireland, the first long-distance electric railway. In 1885, Britain's first electric tramway opened in Blackpool. But electric railways still had some kinks to be worked out before they could see widespread use. The concept of boosting power through a series of substations was unheard of at the time, and most electric railways relied on a single generator, meaning that the power would drop as the train moved further away and the voltage bled out. For the time being, electricity was only suitable for short stretches of track and for trains of 1 or 2 coaches. One area where electricity did see widespread early application was in lighting. The first electric lights to be installed in a railway carriage were installed in 1885, powered by generators attached to the axles. Electric lighting was cleaner, smoother, and less prone to starting fires than oil or gas lighting. But it was also more expensive, and as an experimental concept could often be unreliable, as well as scary for passengers. The transition from oil and gas to electricity was a slow one. In fact, in the early days, there were many incidents of train companies ordering all the electric lighting stripped out of their coaches and replaced with gas. Gas-lit coaches were still being manufactured into the 1930s, and the last gas-lit coach wasn't removed from British Rail until 1961. The 1880s also saw the introduction of corridor trains, with a narrow corridor running the length of the carriages, separated from the compartments by interior doors, often with privacy curtains. This reduced the available seating, but was a great boost for passenger comfort, allowing them to move around during the journey, be more selective about their company, and to visit the toilets and the restaurant much more easily than before. As well as passenger comforts, the carriages were being equipped with bogies, rotating supports with 2 axles on each. This allowed the carriages to handle bends at speed with much less friction than the old 2-axle carriages had. This was a very useful development, as steam power was also seeing a number of improvements, the most significant of which was multi-stage expansion. It was noticed by engineers that the steam being vented out of the funnel still had a great deal of heat and pressure about it, which was going to waste. Trains were developed in which after the steam had left the first high-pressure cylinder, it would be fed into a secondary low-pressure cylinder to drive the axle further. The increased use of the steam allowed much more of the heat energy, or enthalpy, within the steam to be converted into useful work energy, with no increase to the heat applied through the boiler. The upshot of this was that a train could reach much higher speeds with less coal. This spurred the companies on to providing faster and faster express services. But often, this was done not out of necessity or demand, but in order to show up rival companies. Nowhere was this more clear than in the race to the north. The East Coast and West Coast main lines each ran services from neighbouring termini in London up to Edinburgh Waverley of approximately the same length. This created a lot of rivalry between the two of them. In November 1887, the partnering companies, which ran the East Coast Main Line, began running express services daily from King's Cross to Edinburgh in 9 hours, an hour faster than the West Coast could manage. This cost the West Coast some bookings. To combat this, in June 1888, the West Coast began running express services daily from Euston to Edinburgh in slightly under 9 hours. The East Coast quickly reduced their service to 8.5 hours. Both sides then dropped down to 8 hours a few months later. The East Coast then pushed down further to 7 hours and 45 minutes. The record during the race to the north was 7 hours and 38 minutes for the west coast and 7 hours and 27 minutes for the east coast. Both sides then met together and agreed not to push things further, settling on 8 hours for the west and 7 hours 45 for the east. Running trains at high speed for an extended period of time was already putting great strain on the engines and the wheels. It also forced slower commuter traffic to scurry out of the way to allow the express services through. Both companies now focused on how they could run expresses more efficiently at the speeds they'd set. While big business pushed some technology to the limit, it also held some back. The most pressing example was brakes. All engines had been equipped with handbrakes from the time that Huskisson had illustrated the need. The problem was there were none in the carriages, so stopping too abruptly would cause them to slam into the engine, bumping it forward and producing an uncomfortable ride for the passengers. To combat this, brakes were installed in the guard's van at the rear of the train. As there was no way for driver and guard to communicate directly, all sorts of signalling systems had to be introduced to allow both sets of brakes to be applied together. Later, chain brakes were installed, in which a chain was wrapped round a drum on the axle of the engine and then would run the length of the train. When a lever was pulled, the drum would engage and the chain would activate the brakes in every carriage. This had two major drawbacks. First, the braking force reduced significantly the further back from the engine one went. Secondly, a problem anywhere in the chain would leave everything behind it with no brakes. Vacuum brakes and air brakes solve these issues. In the former, a vacuum is created to hold the brake cylinders in place. When the brake lever is pulled, air is introduced to the cylinders and the brakes are applied. With air brakes, air is continuously added in to the system to hold a slider valve in place. When the lever is pulled, the air is evacuated, and the air from a pressurised cylinder moves the valve and subsequently applies the brakes. Not only are both systems more even than chain brakes, but the system is doing the job of holding the brakes off, so any damage in the system will cause them to apply automatically and bring the train to a halt. But companies were slow to adopt automatic brakes for reasons of cost. By 1889, 18% of rolling stock in England and Wales had no continuous brakes, and a further 22% had no automatic brakes. In Scotland, 40% of stock had no continuous brakes, and in Ireland, the figure was 84%. As so often happens, it took a major disaster to reveal what should have been done in the first place. In June 1889, a special excursion train was arranged setting off from Armagh in Ireland, bound for the seaside. The event had oversold, with 940 passengers turning up, requiring 15 carriages. The driver warned that the engine he was provided would not be able to handle the steep incline west of the town with so much load, but he was ignored. As predicted, the train stalled near the summit of the hill. The crew now had two choices. They could split the train in two and take each over the hill in turn before joining them up again, or they could wait for the following train and ask for a push. The crew selected the former option, but to do so would mean leaving the rear portion with no continuous brakes. The crew placed rocks under the wheels and screwed the handbrake down in the guard's van, before decoupling the rear portion. It stayed in place. But as the crew started the engine up again, it lurched back about a metre, which had the effect of bumping the rear coaches and dislodging the rocks. The handbrake was unable to handle the weight and the momentum, and it was already on full, leaving no more brakes that could be applied. The carriages began rolling back, picking up speed. The crew threw more rocks under the wheels to slow it down, and reversed the train in an effort to catch it. But by the time they could get the train reversed, the gap was too great, and their efforts with the rocks all proved futile. Before long, the carriages were moving faster than the crew could run, and they could now only watch helplessly as it sped away. The curved nature of the track allowed the driver of the following train to see the runaway train coming. He quickly threw his train into reverse and bailed out. It was too late to avoid a crash, but did at least lessen the impact. The trains collided at a speed witnesses estimated around 60 kilometers an hour, smashing the rear carriages to matchwood and derailing several more. 80 passengers were killed and 260 injured. Most tragically of all, 46 of the fatalities were children. To this day, it is Ireland's worst rail disaster. A government inquiry was held and placed the blame on two major factors. First, the lack of automatic brakes. Second, the insufficient gap between the two trains. Britain's railways at the time used two different signalling systems. The first was a time system, in which trains would be permitted through a certain interval of time after the last had passed. The other was a block signalling system, in which the track was divided into sections. A train would not be permitted through each signal until a communication was received that the entire section ahead was clear. The companies employed whichever system they thought was best for each section of track. The track outside Armagh used the time system, meaning there was no way for the signal box to know there was trouble ahead, and so they had sent the scheduled train through once the correct time interval had passed, sending it straight towards the runaway train. The government rushed through the Railways Act, which stated that block signalling must be employed across the network, and that all trains must be fitted with automatic brakes. They gave the companies a very tight deadline in which to make all the upgrades. The Act also marked a major shift in government attitudes. Up until this time, they had largely allowed the railway companies to run the lines as they saw fit. Any government decisions regarding the railways were done as recommendations rather than direct orders. But Armagh clearly showed the flaw in that system. From now on, the government would take a much firmer hand with the running of the railways. The promise that the Forth Bridge would allow speedy services through Scotland ran into a hefty snag soon after opening. Many of the routes leading to it had not planned for the extra traffic, and this created bottlenecks all over the lowlands. The most significant was Edinburgh Waverley Station. The station, in 1890, consisted of 4 platforms and 2 through lines. But now that the through traffic towards the bridge was added to the traffic running to the north of England and to Glasgow, the small platforms were simply not capable of handling everything, and long traffic jams built up of trains waiting for space. It was joked by guidebooks that travellers wishing to arrive on time ought to set off the previous day. Following appeals, the government provided funding to expand the station, and expand it they did. By 1895, the station had built up to 18 platforms and 6 through lines. Edinburgh Waverley was now, and still is, Britain's largest station outside of London. Now that the North British Railway could finally run speedy services up to Dundee and Aberdeen, this had the effect of reigniting the race to the north. Up until now, the West Coast Main Line had been the only means of travelling up to Aberdeen without changing trains. Their fastest was an overnight express, which left Euston at 8 p.m. and arrived at 7:40 a.m. But now, the Tay and Forth bridges allowed the East Coast Partnership to run their own direct services, and their route was 45 kilometres shorter. In 1895, they set up an overnight express, setting off at the same time as the West Coast Overnight Express, but arriving at 7:20 a.m. The West Coast rapidly set up a service arriving at 7 o'clock. Both soon pushed down further to 6:45. But shortening the timetables was only the start of it. All through the summer of 1895, the drivers began pushing the trains to the limit in an effort to reach Aberdeen before the other side. Having both set off at the same time made the racing element all the clearer. The final stretch of track was shared between the two sides, so the race would be won based on which side could reach the signal box at Kinnibar Junction first. Several times they arrived within sight of each other. Drivers would ignore the timetables and simply set off as soon as possible, much of the frustration of passengers who wished to board at intermediate stations but found their train had departed early in the hope of winning a race. The companies resolved this by running an additional service to follow along and make the scheduled stops at the correct times. Several of the companies who ran the routes voiced objections to these races, particularly the North British Railway, whose lines were some of the most windy, and attempting a mad rush to the end created a risk of a hideous accident. These concerns were brought to the East Coast Partnership, who spent a few months being conveniently on holiday. But finally they returned and were forced to acknowledge that the North British had a point. The races catered to too few passengers and cost money in service adjustments and in maintenance. The races were brought to an end, and many people breathed a sigh of relief. The problem is that whilst boosting high-speed rail is exciting and headline-grabbing, its application on a medium-sized island is limited. For the majority of actual journeys, the slower, local services are the most important. In this line of thinking, the government passed the Light Railways Act in 1896. Britain was suffering a bit of a recession at the time, and it was felt that this act would stimulate growth in rural areas where mainline railways were not profitable. An earlier act, in 1868, had allowed light railways to be built without having to acquire an Act of Parliament. But this was quite vague on what exactly constituted a light railway. The new Act of 1896 formalised the conditions. A light railway could forego expensive things like signals, crossing gates, and even stations, provided they maintained and enforced a speed limit of 40 km an hour, and had only one engine under steam at any given time. Engines tended to be small and usually narrow gauge, meaning that the track was easy to maintain, and features like bridges could be simple to construct. Several dozen lines were built under this act. They did their job of boosting the local economy, but were never a great commercial success. For a scattered population, using the light railway meant a decent walk to a station which could only take them a short hop to the next town. When motor transport came along, it would quickly prove more versatile for connecting up the rural communities, meaning that the light railways, which were some of the last to be built, would become some of the first to be shut down. It wasn't just the countryside where new light railways were being built. The Glasgow subway opened in 1896, a 10.5 kilometre loop running under the city. Britain's largest underground railway outside of London. It was one of the last cable-hauled railways built in Britain, though it was electrified in the 1930s. Every platform is of the island type, with track on either side, meaning that the public only ever sees one side of the train. For this reason, its carriages for many years had doors on one side only, to maximise seating. On the surface streets, the nation's tramways were facing a problem. The first great wave of tramways had been largely horse-drawn. Successful as they'd been, a rising urban population was causing the demand for horses to grow faster than the creatures could be bred. What's more, the sounds of thousands of hooves on the cobbled streets was deafening, and the waste the horses produced was becoming increasingly difficult to clean. There was a need for more self-propelled vehicles, but the restrictions placed on steam and cable trams meant that neither could really handle the load. The answer was electricity. Engineers were rapidly working out the kinks with electric transport, and at the same time, many of the 20-year leases on horse and steam trams, which had been set in the 1870s, were starting to run out, and the companies used this as an opportunity to upgrade their systems. Much of the older stock was nearing the end of its shelf life. The steam trams in particular were in a bad state of repair, and the operators were only too happy to see the back of them. though some steam trams stayed in operation until the 1950s. The electric trams proved more than capable of taking over, cheaper, quieter, and more spacious than previous types. Over the course of the 1890s, 34 electric tram networks were built or electrified in the country. Another great uptaker of electricity from this era were subterranean railways, where the advantage of electricity over steam is obvious. In 1890, London's first successful deep-level tube line opened, known as the City and South London Railway, running between Stockwell and King William Street. A tunnelling shield was used to dig deeper than previous lines. This allowed them much more freedom of where the line went, including under the Thames. However, the builders were quite pessimistic. The tunnels were significantly narrower than later deep-level tube lines due to fears of collapse. The line would ultimately have to be rebuilt in order to allow wider trains through. The Central London Railway was completed in 1900, running from Shepherd's Bush to Bank, with trains as long and wide as modern tube travellers would be familiar with. Like many early electric railways, the Central London followed the locomotive system, in which a single powered engine pulls an unpowered string of carriages. It was pulling more weight than previous electric railways had, so some pretty hefty locomotives were installed. But the giant electric motors soon proved a problem. Despite their best efforts to muffle it, the loud and sustained whine from the electric motor would echo through the tunnels, irritating passengers, even travelling through the earth and creating complaints from houses and offices above. After some experimentation, engineers suggested replacing the single large motor with lots of smaller ones, arrayed throughout the train. Not only did this reduce noise, but it revealed further advantages. Multiple unit trains allow for more traction to be applied and more evenly throughout the train. Also, it was possible to be driven from a small cab in the front. With a similar cab in the back, the train could be run in either direction, without having to spend ages turning the locomotive around. The multiple unit arrangement would soon become the standard in Britain's electric railways. Meanwhile, Magnus Volk, who'd introduced electric railways to the country, was looking to expand his line in Brighton all the way to Rottingdean, but some cliffs were blocking his way. Volk's solution was bizarre. He laid two 82cm gauge tracks on concrete slabs along the beach, 5.486 metres apart. To run on these tracks, he designed a wheeled platform, driven by two 19kW motors running through drive shafts along the legs, all powered by electric cables overhead. To onlookers, it appeared as if a section of the pier had decided to abscond along the beach. Most bizarre of all, his tracks were between the tide marks, so at high tide his contraption would wade. He named this machine Pioneer, though visitors named it Daddy Longlegs. The Pioneer first ran in 1896. 6 days later, it was derailed in a storm. Nobody was hurt and the damage was repaired and service resumed. Though it proved popular as a tourist attraction, the Pioneer was never a practical mode of transport. The lines had to be constantly cleared of sand and debris that the sea would wash in, and at high tide it could barely manage 5 kilometres an hour, and it wasn't exactly nippy at the best of times. What's more, it could only run when the weather was relatively calm. In 1901, Brighton Council had coastal defences built along the beach, which required the line to be shut down. Despite Volk's setback, electric railways were rapidly coming into their own. However, another form of railway was coming to an end, and that was the broad gauge. The 7-foot Brunel gauge had once dominated southwest England and South Wales, but over the years had been rebuilt a bit at a time to better integrate with the rest of the network. And fewer broad gauge services were being run from the main terminus in Paddington. By 1892, only the main artery from Paddington to Penzance, and a few branch lines out west, could handle broad gauge. The only thing stopping Great Western doing away with it altogether were a number of independent subsidiary companies who owned sections of track and refused to rebuild it. But in 1892, the management structure changed, bringing these sections directly under Great Western's control. They wasted no time, gathering materials and workers in trucks in sidings all along the line in preparation for a rapid operation. In May 1892, the last broad gauge service left Paddington with a great deal of ceremony. The main line was then shut down for a weekend as more than 40,000 workers set about the task of converting the track in its entirety. It was gruelling work, for which the workers were rewarded with an extra ration of tobacco. Nonetheless, the pace caused several mental breakdowns, including one man who ran into the sea and was never seen again. In the space of 2 days, they converted 679 kilometres of broad or mixed gauge track into standard gauge. Finally, Britain's mainline network was running to a single gauge. The engines and the carriages were parked in Swindon, where 21 kilometres of extra sidings had been built to accommodate them. Over the next year, the engineers there converted 132 locomotives and 426 coaches to run on standard gauge. While the lines were modernising, passenger numbers were growing all the time. In 1896, the number of annual passenger journeys passed 1 billion for the first time. Passenger numbers comparable to modern day figures with a much lower population. At the turn of the century, the railways were running through almost every part of British life. Such diverse areas as travel, work, leisure, sport, culture, social breakdowns, food, economics, politics and industry had all been completely transformed as the railways spread their way across the country. And the nation that left the 19th century was a far cry from the one that had ended it. This dominance will continue into the 20th century, but just how long it could last remained to be seen. The early 20th century was the high age of the railways. 70 years of tweaks had made rail travel cheaper, more comfortable and more available than ever before. Canal and long-range coach traffic, which had once dominated transport, were now a fraction of what they had once been. And though aeroplanes and cars were beginning to make an appearance, they were for the large part toys for the super rich. The overwhelming majority of transport was handled by trains. The railways at the start of the 20th century moved as much freight traffic as they did passengers, with almost every industry in some way depending on the railways for supply and distribution. Goods-only branch lines fanned out from the main lines, carrying goods all the way from the producers to the factories, the markets and the docks. And there was barely a town in the country that wasn't connected to the network in some way, shape or form. And still the network was growing, pushing into areas the railway revolution had previously passed by. The Western Highlands were one example. The low population and rough ground made them unattractive to railway companies, which had caused the fishing villages along the coast to stagnate. In the 1890s, the government put forward funding to fix the issue, which was now finally seeing fruit. Extensive use of concrete made building in the soft highland soil much easier, and a number of towns were finally connected in this era, allowing the locals to finally take advantage of the railways for selling their goods. Some of these lines could be very picturesque. Where the Mallaig Extension Railway passed over Glenfinnan, the Glenfinnan Viaduct was constructed, largely out of concrete. 381 metres long, 30 high, and with 21 arches, one of the last rail bridges to capture the imagination of the British public. The Edwardian era was also the peak time for tramway building in the country. Trams were getting bigger and more reliable all the time, thanks to the miracle of electricity. Between 1900 and 1914, more than 160 networks were built or upgraded across the country. And at the start of the First World War, around 4,000 kilometres of track was in operation in more than 200 networks in various towns and cities across the British Isles, almost 10 times the number that exists today. In London, 2 huge networks were built up on either side of the Thames. London Council wished to link the two up, but they were repeatedly blocked by residents of the inner city who believed that the cables would spoil the historic streets and the trams would draw poor people to the area. But the construction of Kingsway in 1905 allowed a tram route to be built into the plan. topped off with Britain's only purpose-built tram tunnel, dipping under the Strand and emerging beneath Waterloo Bridge, where the route ran down the embankment and crossed the river at Westminster and Blackfriars bridges. With the two halves now connected, London could boast the biggest tram network in Europe. Electric railways were growing in general. In 1903, the Mersey Railway, which ran through a tunnel between Liverpool and Birkenhead, became the first steam line to be converted to run on electricity. In 1905, the Metropolitan and District Railways followed suit, electrifying the inner circle in its entirety. Not only was this more comfortable for passengers, but with no need to worry about overpressuring the engines, the trains could run much faster, covering the inner circle in 50 minutes, whereas the steam engines could only manage 70. Nonetheless, the steam engines would continue running on overground sections until 1970. In fact, one of the original engines was never officially withdrawn, and is still run along the lines on special occasions. In 1908, most of the various subterranean railways in London were amalgamated into a single network, known as the London Electric Railway, later renamed the London Underground. Mainline electric services were also on the grow. In the Edwardian era, the length of electric lines built or electrified was comparable to new steam lines. Electric trains were not nearly as fast or as powerful as their steam counterparts, but they were much cheaper to run on a small scale, particularly on lines with light passenger numbers which would only require one or two carriages. For lines like this, an entire steam engine would have been excessive. But in some regions, companies wished to run similar railcars but could not scrape together the funding to electrify their lines. On one line in Teesside, the North Eastern Railway turned to a new idea known as the internal combustion engine. An internal combustion engine operates through a series of cylinders driving a shaft, which go through 4 phases, known as intake, compression, power and exhaust, colloquially referred to as suck, squeeze, bang, blow. In the first phase, the cylinder travels down. A camshaft opens up an intake valve, drawing air into the system. The valve is then closed, and the cylinder travels up, compressing the air and making it very hot and volatile. Fuel is then injected in. In a petrol engine, it is ignited with a spark from a spark plug. In a diesel engine, the air compression alone is enough to ignite it. In either case, the fuel rapidly combusts and expands, driving the cylinder down. Cylinders are typically arranged so that at least one will be in the power phase at any given time, driving the others along. Finally, the exhaust valve is opened and the cylinder travels up. Exhaust gas is ejected from the system. The petrol-powered internal combustion engine was invented by Nicolas Otto in 1876. In 1897, Rudolf Diesel built the first diesel engine. Early experiments applying these engines to trains tended to use diesel or petrol traction, in which the engine drives the wheels directly. A system which would in time prove useful for heavy freight services, but which had a very low power-to-weight ratio when pulling the lighter passenger trains. The North Eastern Railway's new railcars were different. They used a smaller petrol engine to turn a generator, powering electric motors, the world's first petrol-electric trains. This system allowed a much better power-to-weight ratio than any petrol traction system would have allowed. The North Eastern Railway built 2 petrol-electric autocars, and they were successful in their job, staying in operation until 1931. A handful of similar machines were built in the country, but these were isolated cases. Internal combustion was still something of an experimental concept, and coal was much more readily available in the country than oil. The high days of the diesel train were still to come. While new motor powers were being experimented on, steam trains were getting faster, more powerful and more efficient all the time. In 1904, the Great Western Railway introduced Britain's first long-distance non-stopping service between London and Penzance. After holding a competition to name the service, it was dubbed the Cornish Riviera Express. Like many companies on their most famous routes, Great Western would schedule in speed runs for the excitement of important guests. In 1904, one particular run on a train known as City of Truro was attended by well-known rail journalist Charles Rouse Martin. He took timings during the run and claimed to have measured a gap of 8.8 seconds between two quarter-mile posts. A postal worker, who had been tasked with measuring the train's progress, made the same measurement. This gives City of Truro a strong claim to have been the first steam train to surpass 100 miles an hour in transport, or 161 kilometres an hour. And this was at a time when no car or aeroplane had achieved such speeds. Due to the lack of official recording equipment, the record can never be verified, nor did City of Truro ever repeat it. But Great Western chose to treat it as true, and City of Truro became their poster child. City of Truro managed its feat even without a new revolution in steam power which came a few years later, and that revolution was superheating. The steam which comes out of a kettle is not so much a gas as a vapour, with lots of little water droplets suspended within. To convert it to superheated or dry steam, it must either be pressurised beyond anything practical for motive power, or further heat energy must be applied to the vapour. But in traditional boilers, the fluid was being boiled and then just sent on its way. German engineer Wilhelm Schmidt was the first to apply proper thermodynamic principles to design, rather than just using trial and error. He correctly calculated several advantages to dry steam, and so designed a system where the steam, instead of being fed straight to the cylinders, would first be run through several narrow pipes running through the flues. This allowed the steam to be heated up into the superheated region as it travelled. The advantages of this system soon manifested themselves. In an idealised steam cycle, the entropy of the fluid will remain constant as it travels through the cylinders. The useful work energy produced by the fluid in this stage is equal to the drop in heat energy, or enthalpy. And the drop in heat energy along a line of constant entropy is much sharper in the superheated region, so the energy output of the engine could be greatly boosted. In trains with multi-stage expansion, the steam could be fed through a second stage of superheating in between the cylinders, reheating it and allowing the work output to further increase. Of course, a cycle is never idealised. Entropy always increases as energy is lost to things like noise, friction and waste heat. But dry steam could help further there. The wet vapour will condense and collect around the edges of pipes and cylinders, creating friction and losing heat energy in the process. The dry steam meant that there were no water droplets to worry about, significantly increasing the efficiency of the cylinders. The efficiency of the boiler was increased too, since much of the heat energy, which would otherwise have been vented into the atmosphere, was instead put to use heating up the superheaters. Schmidt built his first superheated steam train in 1898. In 1906, Great Western introduced the first such trains to Britain. The greater thermal efficiency meant that steam trains could run faster and longer with a minimal increase in fuel, and with passenger numbers at an all-time high, profits for the companies soared, but not everybody benefited from this. The late 19th century had seen a string of boom and bust cycles, with the cost of living increasing during the bust phases, but staying the same during boom phases. At the same time, there was no nationwide standard of wages. So though Britain was prospering, the working classes in many areas were badly underpaid by their employers and struggling to make ends meet. The early 1910s were a time of great unrest, with mass movements in many industries calling for stronger pay and better working conditions, allied with groups calling for political reforms. Throughout this, there were many acts of violence and sabotage on both sides. The railways were no exception. The unions had been peacefully campaigning for fairer pay and better working conditions since their formation in the 1870s. But whilst conditions had improved, progress was painfully slow. The government had a lot of wealthy backers in the rail companies, and thus a lot of incentive to block any serious attempt to bring in national policies on worker rights. With no regulation, these things were left up to the generosity of the employer, and many of the workers lacked a means to relocate. Not only were they underpaid, they were also regularly working exhausting 12-hour shifts, with the company regularly forcing them to work longer at short notice. One newspaper article reported the story of a brakeman who'd been kept on duty for 43 hours without a break. When it was seen that he was nodding off, porters were sent to prod him awake on a regular basis. In 1907, the government set up the Consolation Board as a body wherein the workers could report their grievances. But the workers soon came to see the board as an empty gesture, where their issues could be unofficially ignored. In 1911, workers in Liverpool decided they'd had enough and went on strike. The sentiment soon spread to surrounding companies and cities where the workers were in similar situations. In August, the railway's four main unions met in Liverpool to combine their efforts: the Amalgamated Society of Railway Servants, the Associated Society of Locomotive Engineers and Firemen, the General Railway Workers' Union, and the United Pointsmen and Signalmen Society. They believed nationwide action was needed to make the government listen. The Prime Minister, Herbert Asquith, met with the rail bosses to assure them that the lines would keep running. He then met with the union leaders separately and offered to set up a royal commission to examine the workings of the 1907 Consolation Board. The unions feared another empty gesture and rejected his offer, declaring the first nationwide rail strike. Calling it a nationwide strike may be a bit of a misnomer. It was up to the individual whether they walked out or not, and only a third of Britain's rail workers chose to do so. Some of the more generous employers had earned a certain level of loyalty from their workers. In the London and South Western Railway, for instance, only 2 of their workers walked out. The more affluent areas in the south of England may have seen little strike action, but it was an altogether different story in the north of England and in Wales. Here, mass strike action brought the country to a grinding halt. Many workers even worked to sabotage lines that were still running during the strike. The Home Secretary, Winston Churchill, took the controversial decision to deploy 58,000 troops against the strikers, with the express purpose of keeping the railways running. This had the effect of inflaming tensions further, and violent clashes broke out, in which several of the strikers were shot dead. But shooting them only swung public opinion further in favour of the strikes. In many regions, the protests blossomed into full-on riots, which would continue for days after the strike was officially over. After 2 days of strikes, Asquith was able to get union leaders and company bosses round the same table to hash out a deal. In many ways, it was the same deal he had offered the unions already: a royal commission to examine the workings of the 1907 Consolation Board. But now that the unions had established their power and sway, they felt confident the commission would be taken seriously and not treated as an empty gesture. They also felt they could confidently negotiate from a position of strength. By the end of the year, pressure from the unions had already driven Parliament to pass laws legally requiring brake levers to be placed on both sides of goods trucks, so that shunters would no longer have to climb between them to apply the brakes, something they had been campaigning for since the 1870s. In 1913, the unions were merged into the much more powerful National Union of Railwaymen. How events would have played out from here can never be known, as the disputes were soon overshadowed by much bigger events. In 1914, Archduke Franz Ferdinand of Austria-Hungary was assassinated by a Serbian gang. Through a chain of alliances and ultimatums, every major power in Europe, and soon the world, was plunged into war, and Britain's railways would have a key role to play in the conflict. The possibility of war in Europe had long been foreseen, and Britain, like every major power, had a carefully thought out plan for rapid mobilisation and victory. The 130,000 strong British Expeditionary Force would need to be rapidly transported to intercept the German advance, and every single part of it would have to go by train. To do so, the hundreds of rail companies which ran the network would need to be made to operate as a cohesive unit. To achieve this, the network was placed under the control of the Railway Executive Committee, consisting of representatives from the 11 largest rail companies, overseen by the Board of Trade. In reality, though, it was run by the London and South Western Railway, who were handling most of the traffic, given that their lines ran between London and the main embarkation ports. The companies were promised compensation for any loss of business they may incur from their stock being used for war work. The War Office gave the committee 60 hours in which to amass the 711 engines and all the rolling stock required to transport the BEF to the main embarkation dock at Southampton. They managed it in 48. All across the country, troop trains set off from stations, with a great deal of ceremony and cheering from those left behind. The first troop ships departed Southampton on the 9th of August, only 5 days after Britain had declared war. By the 31st, the operation was complete. 130,177 troops had been shuttled to the coast and ferried onto the ships, along with 38,805 horses, 344 artillery pieces, 277 motor vehicles, 1,802 motorbikes, and 5,811 metric tons of supplies. The BEF's rapid arrival in Belgium took the Germans completely by surprise. The railways continued supplying the army throughout the war. For troops on their way to the front, the rail journey would continue on the far side of the Channel, where the French government gave the British priority on all the routes leading to their sections of the Western Front. A single division could consume an entire trainload of provisions every 2 days, so regular supplies were needed. And as new recruits came on the scene, 5,400,000 fresh troops were transported to the front over the course of the war, every one of them brought by train. Inevitably, the railways were also tasked with carrying the wounded out of the battle zones. Following the disastrous first day of the Battle of the Somme, 29 full hospital trains were required to handle the number of casualties. In the following week, 151 further such trains would run from the region. For many of the soldiers travelling to replace their comrades, the rail journey will not even end upon reaching the war zone. Throughout the war, around 1,100 kilometres of narrow gauge lines were built by the British, crisscrossing the Western Front, carrying supplies and reinforcements right to the front lines. Often, the lines would have their own trenches dug to protect them from enemy fire. They lacked the flexibility of supply trucks, but were much more efficient and could handle much bigger loads in one go. The tracks were simple to lay and could be quickly rebuilt if destroyed by shell fire, or moved if the front line shifted. Throughout the war, Britain's railways operated as a well-oiled machine, bringing troops and supplies to where they were needed. But there was a sinister aspect to this. The German railways were operating at much the same efficiency, which meant that both sides could pour in reinforcements faster than the enemy could destroy them, and it all ended up contributing to the endless meat grinder that was the Western Front. It was one of many aspects helping to ensure that the war could not end until one side had nothing more to give. For one Scottish regiment, the carnage came before they'd even left Scotland. On the 22nd of May 1915, 2 express trains bound for Glasgow were late arriving in Carlisle. It was decided to send a local stopping train out ahead of them, which the expresses would catch up with, whereupon the local train would park in a passing loop outside Quintin's Hill's signal box, for the expresses to overtake. This was convenient for signalman James Tinsley, who could ride the train to work, saving himself a bike ride. However, upon arriving at Quintin's Hill, it was found that a goods train was parked in the northbound passing loop, so the local train was instead parked on the southbound main line, with the intention of moving it once the expresses had passed. Tinsley left the train and went to the signal box. He had an informal arrangement with his superiors and the night signalman George Meakin. Though his shift began at 6 in the morning, Tinsley would arrive half an hour late to allow himself a bit more sleep. Meakin would write the last half hour of logs on scrap paper. Upon arriving, Tinsley sat down to copy them into the logbook so they would be in his own handwriting. Meakin, having finished his shift, went to read the paper and chat to the staff from the goods trains who come into the box to take their break. Thus, neither signalman was paying close attention to the line. At 6:34, a coal train arrived to be parked in the southbound passing loop. Once it was parked, one of the signalmen, each later claimed it was the other, pulled the lever to reset the points. Through force of habit, he also pulled the lever, setting the signal on that line to clear. At 6:38, the first of the express trains passed through without incident. At 6:42, Tinsley received 2 messages. One, that the second express from Carlisle would be with them shortly, but the more significant informed him that a special troop train was passing through from Glasgow and asked him to accept it through. The line it needed to use was blocked by the local train, but the two signalmen, by their own accounts, forgot it was there, particularly glaring for Tinsley, who just stepped off it. Some historians now believe Tinsley may have suffered from a form of epilepsy which causes memory blackouts, which would explain how he forgot the very train he'd arrived on. He thus sent a clear signal. With the signalmen having missed their opportunity to set a danger signal, the troop train arrived at speed, slamming into the local train and spilling its own carriages out. Soldiers began climbing out of the wreckage, but many stayed to help comrades who'd been injured or trapped. But the worst was to come, as the carriages were now blocking the northbound line, which the express from Carlisle was due to use any second. The signalmen rushed to set a danger signal for the express, but it was too late. The express ploughed into the wreckage, smashing it into an even greater tangle than before. In the midst of all this, the gas lights in the carriages came open, setting the carriages on fire, with many still trapped within the wreckage and unable to escape. Coal which spilled from the engines fueled the flames further, and there was no steady water supply with which to fight the inferno. It would still be burning the next day. The signalmen rushed to give aid, together with survivors from the trains, locals, and anyone else who could be called in. They fought the flames with the limited resources available, and tried their hardest to free those still trapped within the wreckage. But they found all too many who they simply couldn't help, either because the flames were too intense, or because the wreckage was just too entangled to move them. Many begged to be shot rather than wait for the flames to consume them, and several officers were spotted walking among the wreckage doing just that. 226 people died at Quintin's Hill, and 246 were injured, making it the bloodiest rail disaster ever to occur on British soil. The overwhelming majority of the casualties were on the troop train. 215 dead and 191 injured. Of the 500 or so who'd set out, only 58 were able to report for duty the following day. Shell-shocked and under strength, the entire regiment was declared unfit for duty and the survivors returned home. The signalmen were charged and convicted with culpable homicide and breach of duty. Tinsley was sentenced to 3 years hard labour, and Meakin to 18 months imprisonment. Because the railways were so crucial to the war effort, workers were always exempt from conscription. Despite this, many rushed to sign up anyway. Entire yards would clear out in an afternoon. Their workers formed into pals battalions, the theory being that going into war in a unit with friends would aid in the camaraderie, but which in reality meant that those same groups of friends would be frequently wiped out by a single burst of machine gun fire. So many rail workers signed up, in fact, that the government had to officially ban any more from doing so, for fear of leaving the railways short-staffed. To stop rail workers being handed the white feather of cowardice, companies took to issuing them with badges saying "on active service." By the time the ban came in, whole swathes of jobs were already left empty on the railways, and there were few young men left in the country to fill them. To fill in the gap, the railways, like all industries, were forced to open up many jobs to women for the first time. Throughout the war, women were employed as mechanics, conductors, and even the lower levels of management. In fact, by the end of the war, they had earned the right to every position other than driver or fireman. Women were not allowed to drive trains until 1975. In 1914, the railways employed 5,000 women. By 1918, the number had risen to 61,000. Many were forced to give up their jobs at the war's end, but they had proved for all the world to see that they were just as capable of doing these jobs as the men. And many more of them were able to hold on to their jobs. The companies saw it as in their interest to keep them on, since they were paid less than half of what their male counterparts earned. With women playing such an important role in the war effort, it gave women's rights movements much more sway politically. Women were finally allowed to join the same workers' unions as men in 1915, meaning industrial action could follow if they were not listened to. It was never directly threatened, but the possibility loomed over men's heads. Over the course of the war, women were able to bring about a number of social and political changes they had never enjoyed before. They could visit pubs and cinemas without a male escort. They began to wear short skirts, short hair, makeup and bras freely. Some even took to wearing their work trousers off duty. Women's football saw a boost, with many railways and factories forming teams to replace their absent men's teams. Most importantly, in 1918, women over 30 were able to vote for the first time, though the voting age would not be equalised until 1928. Though the railways dominated transport throughout the war, supply trucks and personal transporters would play an increasing role as the war went on. They could carry less than the trains, but they were more flexible, could cover rougher terrain, and made less of a target for enemy aircraft and artillery. By the end of the war, the army had amassed 66,000 of these trucks. When the war ended, they were returned to Britain, where they would help set off a drastic change in the country's transport infrastructure. The armed forces employed 66,000 supply trucks for the war effort. When hostilities ceased, they were sold as military surplus and converted for civilian use. For the first time, road haulage became a major industry, cheaper and more flexible than goods trains, and capable of delivering directly from door to door without having to be processed through goods yards. This was bad news for the rail companies, whose business model required that half their services should carry freight. At the same time, cars and buses were growing in number and were sapping passengers away. Together with providing such a great boost for the roads, the war had left the railways in a very weak position. Though the companies had been compensated for the stock which had been given in war work, the war had disrupted much of their infrastructure and delayed many upgrades in their stock. Many of their engines were now 20 years out of date, and the subsequent recession, together with the influenza pandemic, caused their business to suffer, making it very hard to recover. At the same time, Ireland splitting away from the UK was a further blow to rail companies and investors who owned sections of their network. One way the companies attempted to balance the books was to announce wage cuts and increased hours for their workers. Naturally, the unions did not take kindly to the announcement and organised a nationwide strike as a protest. The strike lasted 9 days, during which the country came to a grinding halt. The strike finally came to an end when the government and the companies agreed to maintain wages as they were for another year. Further negotiation led to the government passing laws setting a nationwide standard in rail workers' wages and limiting their working time to 8 hours a day. The government also agreed amongst themselves that it should be their policy to work with the unions rather than against them. Unfortunately, they did not take the same approach with coal miners. The coal industry was also suffering in the fallout of the First World War. In 1926, it was recommended that a 13% reduction in wage be levelled against the miners. The Miners' Federation of Great Britain began to organise a strike. But the General Council of the Trades Union Congress believed that more extreme action was needed, as similar issues were hitting many industries. In May 1926, they organised a general strike, the biggest ever to hit Britain, with 1.7 million workers walking out. Though the rail workers had no grievances of their own, they joined the strike in sympathy, together with transport workers, dock workers, iron workers and steel workers. Unfortunately, the government had been planning for this eventuality. They organised ways to work around the strikers and encouraged the companies to offer special privileges to those willing to cross the picket line so that the industries could continue running, albeit at a reduced level. These workers were commended by their employers, but permanently despised by the working classes, who shut them out of all social functions and labelled them blackleg workers. Armed militia were deployed to protect those still at work, which naturally meant there were acts of violence on both sides. Chancellor of the Exchequer, Winston Churchill, was narrowly dissuaded from ordering the soldiers to use live ammunition if necessary. After 9 days, the unions were forced to call off the strike. The rail workers were able to return without too much trouble, but the miners were forced to accept great wage reductions. The leaders of the general strike came to regard it as a mistake, which hurt their cause rather than helping. The government passed legislation outlawing general strikes and sympathy strikes. They did, however, look into the possibility of a nationwide minimum wage, and a recommendation that workers' wage reductions should be mirrored by a proportional reduction in corporate profits. The general strike also served to show how quickly the railways were losing ground to the roads. While the 1919 strike had brought everything to a halt, This time, the country had been able to work around the absence of the railways with relatively little trouble, now that buses and lorries were more readily available for their transport needs. The strikes didn't exactly help in that regard, as many turned to alternatives during the strikes and didn't always come back. It was clear that serious reorganisation was required to help the railways rebuild after the war. The Executive Committee, which had run the network during the conflict, highlighted a number of advantages to having a more central authority over the railways. This led to renewed calls to nationalise the network, but these were blocked by the company owners. Eventually, a compromise was reached. A series of mergers would be overseen by the government, amalgamating 120 small companies into 4 big ones, colloquially known as the Big Four. Each company would oversee a given region of the country. After some debate about how best to arrange these regions, it was decided to divide mainland Britain up into wedges like cake, with London at the centre. That way, each company could run direct services from the capital to the far reaches of the country. On the 1st of January 1923, the mergers were finalised and the Big Four came into being. The London and North Eastern Railway, the London, Midland and Scottish Railway, the Great Western Railway, and the Southern Railway. Because the regions were organised along company lines rather than geographically, it led to a lot of quirks in the outcome, with many overlaps, shared lines, panhandles and enclaves. Though Northern Ireland was not part of the grouping plans, LMS inherited a third of the network there. Even more bizarrely, they inherited 2 short routes in the Irish Free State. Despite an uneven appearance, the grouping was a very successful system. The Big Four could take advantage of the tools and talent of their constituent companies, the whole being greater than the sum of its parts. The government could bring in nationwide changes more easily, as 4 big companies were easier to deal with than hundreds of small ones. And the grouping allowed for just the right level of rivalry between the companies to spur themselves on without ending up working against each other. To compete with the roads, the companies endeavoured to use their newfound power to modernise the network. Not only would they replace their worn-out stock, they would push ahead and become world-leading in innovation. For the Southern Railway, modernisation took the form of widespread electrification. Their network was the shortest of the Big Four and largely consisted of slower commuter routes, making it ideal for widespread electrification. In 1923, less than 40 kilometres of their track was electrified. By the time of the Second World War, that number had risen to over 300. A faster rate of electrification than ever managed under British Rail. The government had set the 1,500 volt overhead cable as the standard for electrification in 1921, but Southern chose to ignore this and electrified everything using a 660 volt third rail, creating a divide which exists in the country to this very day. Great Western, meanwhile, were experimenting with the emerging field of diesel power. In 1923, they introduced their first diesel railcar between London and Reading, the first long-distance diesel service in the world, capable of hitting 130 km an hour in service and carrying 104 passengers. By the time of nationalisation, they would introduce 36 more of these railcars, running light passenger and parcel services all over their network. But the main focus of each company was in building better steam engines. Their amalgamation of talent allowed them to produce engines which represented the pinnacle of steam technology. The engineers made many improvements to the boilers, furnaces and feed pipes, but one of the most notable advances was the widespread adoption of the Walschaerts valve gear. Steam engines rarely use gearboxes. Instead, the torque output is adjusted by varying how often steam is injected into the cylinder. When it is moving slowly, steam is injected throughout the stroke, as all the power is required to get the engine up to speed. But at higher speeds, momentum does much of the work, and constantly feeding steam in causes the boiler to rapidly depressurise. And so, a complicated arrangement of cranks and levers is used, which can be adjusted from the driver's cab, so that feed is closed off entirely in mid-stroke, saving steam. Robert Stephenson introduced the first valve gears in 1841, but the Walschaerts valve gear represented a dramatic improvement, as it could be adjusted to much finer increments, and at its highest setting, steam would only be fed in for around 60% of the stroke, compared to 80% for the Stephenson valve gear. What's more, it was on the outside of the wheel, which meant it could be adjusted quite easily at the track side, without having to take the engine back to the sheds. These improvements meant the trains could be run at high speeds for longer without wearing out the engine, as had happened with previous speed runs. Pre-grouping services rarely exceeded 80 kilometres an hour. In 1923, Great Western began pushing the boundary with the Cheltenham Spa Express, which ran from Swindon to Paddington, averaging nearly 100 kilometres an hour start to stop. Whereas the pre-grouping companies had used hundreds of different types of engine between themselves, the Big Four could use relatively few classes in big numbers. Not only did this make it easier to supply spare parts, it also made publicity more impactful. Each company quickly developed a flagship high-speed express class featured on posters and tours everywhere. LNER had their A1 Pacific class, LMS had their Royal Scot class, Great Western had their Castle class, and Southern had their King Arthur class. Not only did the classes become famous, but so did many individual engines. Giving each a distinctive name gave each a distinctive character, just like ships. For instance, schoolchildren and commuters would become familiar with the engine that would carry them each way every day, almost seeming like another co-worker. But none would capture the public imagination more than the A1 Pacific class locomotive LNER assigned to pull their daily express service between London and Edinburgh. Both the engine and the service were known as the Flying Scotsman. In 1928, the service was modified to a non-stop service. At 632 kilometres, it was the longest non-stop service in the world at the time. Water was regularly replenished through troughs in the track, and a special tender was designed which could hold over 9 metric tons of coal. A non-stop service also meant that the crew would need to be changed over on the move, and so a special corridor was built into the tender. Chief Engineer Nigel Gresley reportedly calculated how large to make this passageway by arranging chairs in his dining room and finding the smallest gap he could comfortably squeeze through. He was a large man, and he reasoned that if he could fit, so could his crews. Existing arrangements, following the races to the north, legally set the fastest time at which an East Coast mainline train could run between London and Edinburgh as 8.5 hours, which meant that in the early days, the Flying Scotsman had to average just 75 kilometres an hour, less than half of what it was capable of. The speed would be increased later, but in the early days, it served to make the service smooth and comfortable for both driver and passenger. But the Flying Scotsman's main attraction was not just in speed, but in luxury. The Big Four each endeavoured to make their long-distance services feel more like luxury liners than simple forms of transport. The Flying Scotsman featured not only seating and dining carriages, but a cocktail bar, a ladies' retiring room, and even a barber shop. Not every company was affected by grouping. Many of the small local services stayed independent. London's subterranean railways were a major example. The Metropolitan Railway, which did not become part of the London Underground until 1933, had been expanding into rural Buckinghamshire over the years to link up with other lines, extending as far as Verney Junction, 80 kilometres from central London. The law required for companies building lines to buy not only the land within the track bed, but also within a certain distance to either side. Normally, this would be sold back after the line was complete, but a clause allowed the Metropolitan to keep it for future development. In 1919, they enacted a scheme they had been discussing since before the war to develop housing in these areas. It was advertised to offer Londoners an opportunity to live in the pleasant countryside, but with convenient train access to central London. The scheme was a great success, and the London Underground partnered with housing developers to conduct similar schemes all round the city. The lines expanded out into the home counties, using much cheaper above-ground track, and the city expanded with them, creating hectares and hectares of leafy suburbs with similar-looking Art Deco and Mock Tudor styles in a ring around the city. The area became known as Metroland. The rate at which the city expanded soon came back to bite. Home counties commuters will move into these new developments to be close to the country, but then more housing estates would build up around them. The railway would extend further into the country, and more housing would build up around that. Before long, the countryside they had moved to be close to was nowhere to be seen. In 1928, mainland Britain's rail network reached its greatest extent ever, with 34,000 kilometres of track. But even at the time, it was clear that this was not to last. Passenger numbers, which had risen steadily through the 19th century, were now fluctuating badly. Meanwhile, goods traffic was steadily dropping. And for all the grandeur and innovation of the Big Four, they were not financially successful. Only LNER were turning over a profit, and then barely. The companies relied on government subsidies to function. The world was changing, and the railways would need to reinvent themselves for this new age. When a new technology emerges which threatens the business of those providing an existing one, there are two approaches they can take. One is to try and hold back progress. The other is to see this new field as an opportunity to expand. As the railways were facing increasing competition on several fronts, they attempted to follow the latter approach. The companies believed at the time that in order to turn over a profit, half their traffic would need to consist of goods services. With so much of this being lost to road haulage, the companies began to buy lorries of their own, giving them a stake in their main rivals. The Big Four had an advantage over the road-bound haulage services, as they could organise journeys which combined the trains and the lorries together, providing a speedy long-distance delivery. But even they were increasingly often finding that it was cheaper and faster to deliver directly by road rather than go through the goods yards. And though the rail companies had the advantage of a hybrid transport network, they had a distinct disadvantage over the haulage companies due to a long-standing regulation which required them to take all cargo at a nationally regulated rate on a first-come, first-served basis. This had been necessary when the railways controlled virtually all goods transport, as it kept the market open to all businesses and prevented the companies from cherry-picking the most profitable cargoes. The road companies, though, had no such regulations. They could negotiate prices privately, and since the rail companies were required to publish all their rates, the road companies could easily set a price that was slightly lower. The Salter Report of 1933 helped level the market somewhat. First, it introduced licensing and safety regulations on road vehicles, as well as raising vehicle taxes, reining the lorries in somewhat. Secondly, it eased pricing regulations on the railways, but it failed to remove the first-come, first-served obligations, which were forcing the companies to subsidise unprofitable loads with profitable ones. As well as lorries, the companies were also buying aircraft, looking to expand into the emerging market of air travel. The Railway Air Service was formed in 1934, flying passengers between the big cities of the UK and even abroad. Trains at either end would shuttle passengers to the city centre. But once time spent shuttling was taken into account, air travel between major cities was not much faster than going directly by train. If the aircraft could fly directly between the larger stations, it would boost their business greatly. The problem was, the main stations tended to be in the middle of built-up areas, with no room for an airstrip. Architect Charles Glover believed he had a solution. He would build an airfield on the roof of King's Cross Station, an ambitious idea which would have featured 8 runways branching out with a taxiway round the outside. The scheme never got off the ground, as it would have required every building in the area to agree to make up the foundations. A simpler vehicle companies could use to cater to passengers was the motor bus. A law change in 1927 allowed rail companies to run motor bus routes for the first time. In sparsely populated areas, light railways had previously been used to shuttle passengers to the station. Buses served the same purpose more cheaply and more flexibly. They could pick people up from right outside their houses. The ability to run bus routes meant that rail companies can now replace unprofitable lines with cheaper bus services without affecting their income. This accelerated the rate at which lines were being closed. At the same time, the Big Four had inherited many parallel routes which had existed to allow rival companies to service the same area. Now that they owned both lines, there was no need to keep both of them open. All of this meant that from 1929, Britain's rail network began to shrink consistently year on year. Not everywhere was downsizing though. The London Underground was growing rapidly, both in terms of size and passenger numbers, largely due to the growth of Metroland. But the growth of the network created a problem for those trying to create a clear map for travellers. The maps of the time included all the twists and turns of the tunnels and could be quite hard to read. Getting the whole network to a single scale was a problem, since it left the central zone, where the vast majority of journeys were made, awkwardly squashed in the middle. It didn't help that early maps included extra details such as surface lines, streets, parks, tourist attractions, and even army barracks. In 1926, a man called Frederick Stingemore designed a simplified map, removing all surface features besides the River Thames, giving each line a bright and clear colour, and compressing, stretching and distorting many of the lines to make it easier to read. An electrical engineer called Harry Beck questioned why they should stop there. Taking inspiration from schematic drawings, he designed a map in which the geography of the stations was ignored completely, focusing only on the connections between them, with all lines drawn at 90 or 45 degree angles, all stations equispaced where possible, different symbols for interchange and standalone stations, and a uniform typeface on all the labels. In 1931, he submitted his design for the tube map, possibly the most iconic rail map in the world. Frank Pick of London Transport was apprehensive about the concept, but agreed to give it a trial run. The map instantly proved popular with the public, allowing travellers to work out at a glance where to go and where to change trains, with a single map covering the whole network. The map itself became a design icon, featured in artworks and tacky souvenirs the world over. Sadly, Beck never copyrighted his work, and barely received any payment for it in his lifetime. While the Underground was going strong, up on the surface, the nation's tramways were in serious jeopardy. For them, the growth in road traffic posed a more immediate problem. The lines had been designed to flow seamlessly with slower horse-drawn traffic. For faster-moving cars, these large, unmanoeuvrable bulks in the street were an increasing source of frustration. It didn't help that passengers would embark and disembark in the middle of the road, making the streets very chaotic indeed. With hindsight, it can be seen that when trams were removed from the streets, it had no serious effect on traffic flow. But to motoring organisations at the time, it seemed that getting rid of them could only be a good thing. In 1931, a parliamentary commission convened to agree on a uniform policy for the inner city's public transport networks. It featured many emphatic arguments both for and against the trams, but ultimately concluded that the trams were standing in the way of efforts to modernise the streets. However, there was one saving grace. Trams were bigger and could handle almost twice the passenger numbers of even the largest motor buses. For the busiest routes, the motor buses simply could not handle the load. Instead, the government advocated for a third option known as the trolleybus. Electric buses powered directly from overhead cables, thus experiencing none of the charging problems of later electric vehicles. A best of both worlds approach, combining the size and low running costs of trams with the manoeuvrability and low maintenance of motor buses. But even with the trolleybuses, the number of tram and tram-like networks in Britain saw a severe decline in the interwar years. The trolleybuses represented a successful attempt to reinvent the railway concept for the 20th century. Others were less successful. Experiments were done in various locations to create a bus which could run on both road and rail, using various methods of switching between the two. Though interesting in concept, they were outperformed by buses on the roads and by trains on the rails. Added to that was the limited applicability, and so the concept got nowhere. But the most ambitious attempt to reinvent the railway from this era came from a man called George Benny. Inspired by the propeller-driven rail Zeppelin from Germany, he designed the Benny railplane, a propeller-driven monorail which could carry 48 passengers or light goods loads and be suspended over existing lines, providing light high-speed services on the track above, while the heavier, slower commuter and goods trains continued unabated on the track below. In 1930, he constructed a prototype 120-metre section of his track at Millingrave in Scotland. He claimed the railplane would be able to reach 200 km an hour. On the short track, it could barely manage a fraction of that, though testers said it accelerated and braked extraordinarily well. Benny took this as a success and looked for investors to expand the scheme, but he struggled to find any. Building his suspension poles over long-distance railways would be very expensive, and it wasn't clear if there was enough demand to make the money back, nor was it clear how Benny planned to handle bridges and tunnels. Meanwhile, the Big Four were looking to more conventional ways to win back the crowds. Increasingly, they turned to their greatest weapon, speed. The roads may have the edge in small local journeys, but in a world without motorways, they were badly outclassed at cross-country journeys. To sweeten the deal further, the companies began running car trains, where motorists could drive to the station, have their car loaded on the train, have a quick relaxing run to their destination, and then have a car to drive around in once they got there. In 1932, the government drastically relaxed speed regulations on the railways in light of a number of improvements to railway design, allowing trains to run at high speeds for longer and more safely than ever before. Now they could really open up the taps, and companies made every effort to show off their speed. They organised elaborate Top Gear-style races, pitting their trains against sports cars, speedboats and light aircraft, or simply conducting location-to-location races against other forms of transport. And when the trains weren't racing against things that weren't trains, they were racing against each other, as the Big Four all sought to outdo each other in high-speed services and publicity pieces. In 1932, a GWR Castle class, known as the Cheltenham Flyer, made a speed run between London and Swindon, covering the 124 kilometres in 56 minutes and 47 seconds, hitting a top speed of 149 kilometres an hour and averaging 131 across the run, the fastest average speed in the world at the time. LNER, meanwhile, reduced the running time of the Flying Scotsman service from 8 hours 15 to 7.5 hours, later 7 hours and 20 minutes. In 1934, equipped with a dynamometer on board to measure speed accurately, the Flying Scotsman became the first steam train confirmed to have surpassed 100 miles an hour, or 161 kilometres an hour. Previous claimants had relied on anecdotal evidence. The Flying Scotsman was chosen to make this run due to its fame rather than its ability. By this time, the A1 Pacific class had already been superseded by the A3 Pacific class. Within a few months of the Scotsman's record-breaking run, an A3 class on the same route, known as Papyrus, was able to hit 174 kilometres an hour. The A3s too were soon superseded by Sir Nigel Gresley's new design, the A4. It was a model designed with speed in mind. The most obvious change was the streamlining. Inspired by recent developments in race car design, in which cars were built to cut through the air smoothly, engineers around the world looked into how the principle could be applied to trains. But streamlining steam trains had an additional problem compared to other systems, as the shape had to not only cut through the air, but also avoid creating a slipstream that would blow smoke in the drivers' faces. This required extensive testing in wind tunnels. During one test, a technician carrying the plasticine model accidentally left a thumbprint on it just behind the smokestack, but it turned out that was the perfect shape to create an updraft that would drive smoke away, and so it was incorporated into the design. The streamlining reduced drag at top speed by 40%, but it also increased the weight. Gresley himself regarded it as a gimmick, since the most important changes happened under the surface, such as streamlined supply pipes, and a boiler that could handle an extra 2 bar of steam pressure. On their first run in 1935, the A4 class Silverlink was able to hit 180 km an hour and covered the distance from London to Newcastle in 4 hours. In 1936, another A4 known as Silver Fox pushed the speed further, hitting 182 km an hour. Not only were the A4s fast, they were also reliable. In 1,510 runs of the Silver Jubilee service, only 10 ever suffered mechanical problems. Rivals LMS, meanwhile, had been lagging behind in terms of innovation. They had continued the Midland Railway's small engines policy, which favoured low running costs over high-speed performance. It was a sensible decision financially, but unfortunately, LMS's network had a lot of overlap with the other companies, and in the more competitive regions, they were losing business to their flashier rivals. In 1932, their policy was reversed, and a new chief designer brought in, known as William Stanier. He introduced many innovative new designs, most notable of which was the Princess Coronation class, designed to run on their West Coast main line, with many of the same improvements in streamlining and mechanical efficiency, along with larger cylinders and greater surface areas in the flues. This allowed the Coronation class to produce 1,872 kilowatts of power, or 2,511 horsepower, a figure not matched until well into the diesel era. On their inaugural run in 1937, their engine, known simply as Coronation, was able to break LNER's record with a speed of 183 km an hour. But the run almost ended in disaster. The brakes Coronation had been fitted with were insufficient to slow it down at high speeds, and they were heading for a curve outside of Crewe with a speed limit of 32 km an hour. Coronation hit it at around 87. Passengers and luggage were thrown to the floor, but by some miracle the train stayed on the tracks. In light of this, the two companies called an informal truce while they each fitted more powerful brakes to their expresses. Gresley also used the time to work on the Mallard. It would be an A4 with special modifications just for making a speed run. All the valves and fittings were tuned up to the maximum extent, and a double blast pipe fitted to draw air to the furnace faster. In 1938, the Mallard set off, officially to test the brakes. Gresley waited until it was moving to announce to the press that he intended to take it up to full speed, too late for LNER or LMS to do anything about it. On a downhill section at Stoke Bank, between Grantham and Peterborough, the Mallard hit a top speed of 203 km an hour, or 126 miles an hour, a land speed record for steam trains which still stands to this very day. An observer watching the Mallard speed past would be forgiven for believing that the high age of the railways was alive and well. Sadly, it was not the case. Attention-grabbing publicity stunts were simply not translating into consistent business growth. Every year, the roads were getting stronger and the railways were getting weaker. But questions about the network's future would have to wait. In 1939, the Nazis invaded Poland, kicking off the European section of the Second World War. And Britain's railways would have a key role to play in the conflict once more. Though Chamberlain tried to claim otherwise, it was increasingly clear throughout the 1930s that another war was fast approaching, and many were drawing up plans. The Railway Executive Committee reconvened in September 1938, consisting of a representative from each of the Big Four and one from London Transport. Officially, they were overseen by the Ministry of Transport, but in practice, they were run by LNER, the most powerful of the companies. Their headquarters was in a bunker built into the side of Down Street Station on the Piccadilly line, now closed. A dividing wall was built into the end of the platform to allow high-profile visitors to enter without being noticed. They would ride to and from the station in the driver's cab. The committee spent the year drawing up careful action plans. As soon as the invasion of Poland began, they sprang into action, not even waiting for Britain to declare war. First on the agenda was to implement air raid precautions. Tape was placed across train windows to prevent the glass from shattering in a blast wave, and the stations were blacked out to make a tougher target for the German bombers. Lights were also removed from carriages at first. Later, blackout curtains were placed across the windows to allow passengers to have lights on in the train. Within the same day, the committee implemented Operation Pied Piper, a scheme to evacuate the nation's children from the inner cities out into the relative safety of the countryside. And this was primarily handled by the railways. More than 1 million children were evacuated in the opening weeks of the war. Most children were sent off alone. They were lined up outside stations for local families to inspect and decide if there were any they wished to take in for the duration of the war. Not only were the children evacuated, but valuable artworks were moved to safe locations, and even the animals were evacuated from London Zoo. During the First World War, the rail companies had attempted to continue their peacetime services alongside the extra wartime traffic. This had created a very chaotic situation which had likely contributed to the disaster at Quintin's Hill. Learning from this, the committee drew up clear plans for adjusting themselves for a wartime service. With extra traffic taking up space on the lines, average speeds would have to be reduced. This meant that the beloved high-speed expresses would have to take a back seat to the slower but heavier mixed traffic engines. Civilian passenger services were also reduced, with adjustments made to the carriages so that more people could fit on a single train. As with the First World War, troops gathered in their thousands at the stations for the railways to carry them off to war. But all too soon, they found themselves carrying the troops the other way. In June 1940, the main British and French force was surrounded at Dunkirk. 338,000 of them were evacuated to sea in Operation Dynamo. This left them awkwardly stranded on the south coast of England and in need of returning to their barracks. The Big Four, between themselves, mobilised 327 engines to run thousands of special trains. Over the course of the evacuation, they moved 181,000 troops out of Kent and Sussex. Many of the troops had not eaten in several days, and so Southern organised rest stops along the tracks, where the trains would stop for 8 minutes, while food and drink were passed up to the soldiers. With France now under occupation, it seemed to all that Britain would be next. The army rapidly sprung into gear, building defensive stop lines across the country, but particularly concentrated in the south of England. Due to its geographic location, Southern found themselves intricately involved in the invasion preparations, and this caused a dramatic change in their traffic. Before the war, freight trains had made up just 25% of their services. Now the figure rose to 60%. This left them badly short of specialised goods trains, and more would need to be developed fast. Southern's locomotive superintendent, Oliver Bullade, was in his element, pushing out designs for new or repurposed goods engines, most notable of which was the Merchant Navy class, a mixed traffic engine capable of pulling 600 metric tons at 110 kilometers an hour. It was not without its flaws, however. Bullade installed his patented chain valve gear on the engine, which was kept in a special oil bath for lubrication. A fine design in theory, but the oil bath would often leak onto the tracks, creating wheel slips and even fires. But these problems were manageable, and the Merchant Navy's pulling power was invaluable for the military in setting up defences, and later in assembling troops for D-Day. As well as providing materials, the railways often formed a key component in many of the stop lines. Many of them were set up with railways to their back to allow for rapid resupply and redeployment, and heavy railguns were deployed around the country. A series of special sidings were built into the tracks to act as firing positions, with the plan to move the gun to another position once the enemy had got a fix on it. Another measure that was taken to prepare for invasion was to remove or blank out road signs across the country, in the hope that invading armies would get lost, and rail signs were no exception. To aid confused travellers, the companies instructed anyone who knew where they were to inform anyone else in the carriage, but the invasion would never come. The only attack came from the air. Those sheltering from the Blitz could build an Anderson shelter in their back garden, or a Morrison shelter in their dining room. Either was free to pick up from the government, but to many the shelters did not seem secure enough, and people took it upon themselves to create communal shelters in more secure locations. For Londoners, the Tube represented a collection of tunnels deep beneath the surface, with convenient access points all over the city. They seemed ideal as shelters. Churchill, like many in the government, was resistant to the idea, believing that communal shelters would become communities in themselves, filled with people refusing to leave for work, as had happened in China. He also feared that the shelters would be recruiting grounds for subversive ideas. But Londoners took things into their own hands. They bought halfpenny tickets en masse, legally crowded into the stations before closing, and then refused to leave. And it was not worth the authorities' time to move them out. After 3 nights of this, the government made it official, allowing carefully regulated numbers into the stations every night. Over the course of the Blitz, the tube stations became increasingly elaborate, with bunk beds, toilets, catering, libraries, schools, entertainments, and even a limited train service to allow people to travel between shelters. At their height in September 1940, over 150,000 people a night were sleeping in the stations. The military too saw the value of the tube. Many of the command bunkers that were built in London were constructed with entrances leading into tube stations so that communications could be easily maintained even in an air raid. Of course, the tube was not always secure. In October 1940, a stray bomb hit the road above Balham Station and penetrated deep into the ground before exploding. Not only did this bring part of the roof down, but it also burst a water pipe, causing the station to rapidly flood. 68 people were killed. Nor did the danger always come from the bombs. In June 1943, a crowd was making its way into Bethnal Green Station when an explosion went off not far away. This caused a mad rush to get underground. In the midst of this, somebody tripped in the escalators, and others tripped over them, but the panicking people above continued to press in, unaware of what was happening. In the end, 173 people were crushed to death. While people were sheltering in the tubes, the service lines were drawing up their own procedures for dealing with air raids. As soon as the siren sounded, trains would stop at the next station and allow anyone off who wished to seek shelter. They would then proceed at no more than 50 kilometers an hour. The railways would also be used to fight back, rapidly deploying heavy flak guns to where they were needed. Once the raid was over, the railways would need to deal with damages. Around 10,000 bombs hit parts of the network throughout the war. Extra connections were built between lines, so that trains could be diverted where necessary. In particular, connections were built between rival companies, so they could share track where they needed to. Where trains couldn't be diverted, the track would be repaired as quickly and efficiently as possible, while replacement bus services were put in to fill the gap. The railways contributed to the war in some unexpected ways. When the government set up their main code-breaking station in 1939, one of the main reasons Bletchley Park was chosen as the site was due to it being roughly halfway along the main railway between Oxford and Cambridge, allowing the code-breakers good access to the intellectual talents of both cities. Throughout the war, the public were encouraged to dig for victory, setting up allotments on any free space they could find to compensate for the supplies lost to U-boats. It was pointed out that railway banks represented thousands of kilometres of unused land, and so terraces were built into many of them where food could be farmed, invaluable for many. As the war swung into the Allies' favour, defence turned to attack. As the Allies advanced across Western Europe, much of the rail infrastructure was devastated and needed to be rebuilt. The Allies imported tools and materials to rebuild the railways, along with a lot of their engines and rolling stock to replace the devastated French stock. In the final year of the war, exactly 1,000 locomotives were shipped across the Channel, with the 1,000th arriving on VE Day. The railways did surprisingly well out of the war. With petrol strictly rationed, much of the traffic the railways had lost in the previous decades came flooding back. For 3 of the Big Four, this was the only time they turned over a steady profit. And this was in addition to the subsidies paid by the government for the stock being used for war work. As the war went on, the government took a more and more direct role in the running of the railways. The needs of the war effort required them to ensure that the Big Four would work closely together and pool their resources for victory. By the war's end, they felt less like 4 rival companies and more like a single entity with the government at the head. After the war, this will present them with an interesting opportunity. The issue of how to rebuild after the war was a primary focus of the 1945 general election. Conservative Winston Churchill aimed to minimise government spending, importing as little and exporting as much as possible, believing the state didn't have enough to fund rebuilding work. This idea was not popular with the public, as it meant that rationing was increasing rather than decreasing after the war. Labour leader Clement Attlee proposed almost the opposite, a programme of mass nationalisation and investment to get the economy turning over again. Nationalisation meant that the income from an industry could be put back into investment rather than being gobbled up by shareholders, and a centralised authority would allow this investment to be directed where it was needed without having to negotiate with individual companies. Labour won the election with a 145-seat majority, and the welfare state came into being. For the railways, this meant the creation of the fully nationalised British Railways. While the Big Four had done well out of the war financially, they had suffered heavy damage to their infrastructure, and development had stagnated due to the war. It was clear that none of the individual companies were up to the challenge of rebuilding. Only a centralised authority could do so. And this was the perfect time. The companies had got used to working together for the common good over the course of the war, and the increasing role the government had taken in their running meant that much of the management structuring was already in place. On the 1st of January 1948, the Big Four were formally dissolved, and British Railways took over the whole network. Not all railways fell under BR's authority. Many minor industrial lines were left as they were. Several other lines with no connection to the network were also unaffected. The London Underground had been publicly owned since 1933. The London Transport Executive was created to manage it. Northern Ireland's railways, meanwhile, were merged into the Ulster Transport Authority. The management was divided into 6 zones, based mostly on the Big Four's main domains to make the transition smoother. Alongside patching up the wartime damage, BR faced a challenge in reforming the network for a changing world. The problem was, the network had not been built as a single unified system, but as a patchwork of systems built for individual companies, cooperating on an ad hoc basis. BR aimed to use their newfound power to update the railways, introducing new technology and ideas, and reforming the network into an efficient and well-oiled machine. But the execution of this vision would meet with mixed success. The first key decision they had to make was what motive power their future should lie in: steam, diesel, or electricity. Many countries were using the post-war recovery as an opportunity to upgrade to more modern systems. In France, for instance, the devastation of the war meant that the network was being rebuilt from the ground up. The rebuilding was taken as a great opportunity to install electric cables while they were at it. BR aimed to do the same, but unlike France, the network in Britain had taken relatively light damage, and most in the government simply wanted the network patched up and returned to service as simply as possible. Meanwhile, funding could be directed into more pressing matters. Electrifying everything would take time and investment that was simply not forthcoming. Full electrification was still some way off. BR could have filled the gap with diesel, but they initially chose not to for 2 reasons. The first problem was they had too few diesels to start from. Besides railcars and shunters, BR had just 2 mainline diesels in 1948, compared to 20,000 steam engines. Switching between the two would require a long transition period, in which fuel and support would have to be provided for both systems, which would be expensive, and it was something BR were keen to avoid. The second problem was that oil needed to be imported, and Britain lacked the currencies required to purchase it en masse. Coal, on the other hand, could be mined within the country. Plus, keeping coal miners in employment was considered crucial to the economy. And so, BR chose to stick with steam, at least until the lines could be electrified in full, whereupon coal would naturally be used to produce the electricity. Nonetheless, something would need to be done about their locomotives. There were more than 400 classes of steam engine running on the main lines in 1948, some dating back as far as the 1870s, and they were becoming increasingly complicated to maintain. Engineer Robert Riddles was assigned the task of streamlining the system down to a smaller number of classes. He decided what was needed was a new range of steam engines, designed to keep steam running up until the end of the 20th century, thus providing time for electrification. Riddles performed trials with the best of the Big Four stock all over the country, and selected the best features from each to go in his new engines. As there were no rival companies to compete with, BR would have no need of the flair of the Big Four's engines. This new range of machines would be built with simplicity and practicality in mind. Features such as streamlining and multi-stage expansion were done away with, effectively sacrificing high-speed performance in favour of ease of maintenance. As much as possible, these new designs will be built from a standardised set of interchangeable parts to make it easier to provide spares. However, many question the wisdom of this, as BR's new line did not supplant the earlier engines, so workshops now needed to supply yet another set of parts. Riddles' tests had shown that the Big Four designs were capable of doing the job anywhere in the country, so it may have been more practical to simply expand on the best of them. Some have suggested that Riddles, as a steam enthusiast, simply wanted to get his own designs out there before steam inevitably came to an end. Nonetheless, this new set of standardised classes produced were very successful designs. Efficient, powerful, and reliable. These engines were perfect for their time, even if that time would be tragically short. With so many classes of engine in service, the railways were becoming an exciting place, and this gave rise to a new hobby known as train spotting. The first train spotter manual had been published in 1942, with information about all of Southern's engines, but it saw its peak in the 1950s as more nationwide manuals were published. Children across the country would gather by the lines after school to tick off each engine they saw and compare notes afterwards. For its first few years, British Railways was a great success, turning over a steady profit. Continuing fuel shortages were straining the roads, allowing the railways to hold on to their business. Whilst passenger numbers were growing, freight was seeing an even bigger boost. It had risen during the war and continued to rise for almost a decade afterwards. BR believed the trend had permanently reversed and began to invest in new goods yards. Most of these new yards were designed to the hump arrangement. The various goods wagons would be uncoupled and pushed over a man-made hill, whereupon gravity would do the rest of the work. Points would be used to direct each truck into the correct siding, where it would be coupled together for the rest of the trucks, ready to be towed away by a goods train. This system greatly simplified the job of sorting the wagons, which had previously required a lot of shunting and reversing from the yard engines. But it was delicate to operate, as it required several sets of points to be adjusted to direct each wagon to the correct siding, and the gap between each one could be mere seconds. Pulling every lever in this time and always getting it right was a tall order for the signal operators. To make their job easier, an automated system was introduced, operated by some of the first computers to be employed on the railways. All the signalman had to do was feed in the correct punch cards. Alongside upgrading their engines and their yards, BR were attempting to adjust their tracks into a more coordinated system. While the network looked nicely joined up on a nationwide map, a closer look revealed a network which had not been built with joined up thinking in mind. In the 19th century, a company would build a line to service a particular area. Another who wanted to service that area would then build a line right next to it, resulting in two separate stations within a stone's throw of each other. Often, the companies would even build track with the specific intention of blocking their rivals. It would have made more sense to share space, but to do so required a lot of negotiation between the companies. This haphazard arrangement had made sense under the pre-grouping companies, but had made increasingly little sense under the Big Four, and even less under BR. They had now inherited a network with many awkward breaks and duplicate lines. In order to reform the system, these duplicate lines would need to be shut, and new connections built in order to make everything run more smoothly. Duplicate lines were not the only reason lines were shutting. The nation's light railways were also declining. Few had ever been profitable, and many had existed mostly to service local industries, which were now either gone or taking their light goods traffic by road instead. As a result of this, in the 1950s, line closures began to happen in earnest. An early example was the narrow gauge Tallinn Railway in Wales. It had been built in 1863 primarily to service a local slate quarry, which shut in 1946, and passenger traffic was just too low for the line to be sustainable. The line was announced for closure in 1951, but locals were sad to see it go, and organised a big fundraiser which allowed them to buy the line and some of the engines. They began to run infrequent services, staffed entirely by volunteers, during the holiday-making seasons, where tourists could take a ride on the train. This was the first of Britain's heritage railways. In the decades to follow, many of Britain's branch lines would be saved from demolition in the same way. This era also saw two of the worst rail disasters in British history, eclipsed only by Quinton's Hill in terms of body count. In 1952, a commuter train was waiting in the platform at Harrow and Wiltston when a delayed express train came speeding up to the station. On the approach, the express had passed through 3 sets of signals set to danger, but they had not even slowed down. As neither driver nor fireman survived the crash, we will never know why they did not stop. The express smashed into the back of the local train, smashing several carriages to pieces and derailing several more, and this was just as another express was passing through along the neighbouring line. This created a multi-train pile-up and threw wreckage all over the station. 13 carriages in total were crushed into a pile of wreckage. In the end, 112 people died and 340 were injured. 1957 saw the Lewisham crash. An electric train was stopped at a signal under a bridge, but due to thick fog, the following train did not spot the signals further up the line and smashed into the rear of it. This destroyed several coaches and threw out wreckage which knocked out a key support column in the bridge, bringing it down on top of them. 90 people were killed and 173 injured. The common factor in both these disasters was missed signals, and it led to a widespread implementation of automatic signalling, made easier by the nationalised network. An electromagnet was placed between the tracks, which would be activated on a danger signal. As a train passed over, it would activate a similar magnet on the underside, activating a system that would switch on a light in the driver's cab and sound a bell to alert them further. If the driver took no action, the brakes would apply automatically. BR's honeymoon period came to an abrupt end in 1954, when a cheap source of imported oil was found. Road traffic began to rise sharply, sapping business away from the railways once more. The welfare state had also boosted the prospects of Britain's lower classes. Now everyone could afford to buy their own car, and increasing numbers chose to do so. It also provided workers with the opportunity to seek more meaningful employment. Heavy industry was no longer attractive to them, in particular filthy, exhausting jobs such as coal mining. This caused the price of coal to rise sharply as the price of oil was dropping. But more alarming was a shortage of recruits willing to work on steam engines. And steam engines were very labour intensive. Proposals were drawn up for systems and technology to ease the workload, such as designs for automatic coal feeders, which would eliminate the need for stokers. But a thorough analysis showed that this would not fill the employment gap, nor cut the running costs sufficiently. Steam had become unsustainable, and full electrification was still decades away. BR needed diesels fast. Diesels showed many advantages over steam. Whereas a steam train needed preparation time in the morning to heat up the boilers, diesels could be started with the turn of a key. They could be driven by a single driver and were much simpler to operate. Diesels were cheaper and simpler to build and maintain. They were also faster and more energy efficient than similar steam classes. Romance surrounding steam aside, there was no longer any reason to hold on to steam power. The 1955 modernisation plan aimed to revive BR's fortunes with an investment of £1.2 billion to upgrade their infrastructure into a profit-making industry. The plan had 6 main points: widespread electrification of principal lines in the eastern region, Kent, Birmingham and central Scotland, new coaches and freight wagons to make the experience more attractive to passengers, widespread replacement of steam engines with diesel, upgrades to signalling equipment to allow for smoother running, closure of unnecessary duplicate lines, and the construction of new goods marshalling yards. In some of these aims, BR were largely successful, but all of this was overshadowed by their failures where it came to dieselisation. For largely political reasons, it was decided that the diesels should be wholly homegrown, designed, supplied, tested and manufactured all within the country. While this was done with the aim of boosting Britain's industry, it meant that a crucial job was being given to people with no experience in the field, and forced to start from scratch, rather than building off tried and tested designs from abroad. Their other unfortunate decision was to give each region the responsibility of developing their own line of diesels. This was intended to act as a pilot scheme. The design teams in each region would design 5 classes of diesel, which varied depending on power output. Small numbers would be built and trialled in service. The best design in each category would be selected for mass production. But as BR's annual losses mounted, the management became impatient and ordered that all the designs should be put into mass production straight away. This despite the fact that many of them had not even reached their prototype stage. The net result was 26 new classes of diesel engine, all of which had been rushed through development. Their flaws soon became apparent, and the maintenance teams struggled to handle so many new classes at once. The British public got used to the sight of these brand new diesels breaking down and having to be towed back to the repair yards by the steam engines they were supposed to be replacing. Far from simplifying BR's infrastructure, the diesels only added to the chaos and the cost, and the aim of phasing out the steam engines was made more difficult by the fact that they continued rolling off the production lines for another 5 years after the dieselisation plan was announced. In a further blow to BR's fortunes, road haulage was growing once more, and rail freight was still choked by the Common Carriers Act, which required them to take anything on a first-come, first-served basis, regardless of profitability. Before long, many of their expensive new goods yards were sitting empty. All in all, the modernisation plan was an expensive failure. It led the Treasury to distrust BR's financial planning and reluctant to invest, a problem that would strain BR for the rest of its existence. In 1960, steam train production was finally halted, with the BR 9F class set up as the last to roll off the production lines. BR Western Region Staff magazine held a competition to name this engine. 3 different readers won the competition, suggesting the name Evening Star. It was the only 9F class to receive a unique name. The question now was what to do with the over 20,000 steam trains in service on British railways. It was all perfectly good stock and could have kept running for several decades if they so wished, but to do so would require BR to maintain all the labour-intensive infrastructure surrounding the steam engines along with that of the diesels. To do so would be expensive, particularly if the steam engines wound down gradually. By the end of the run, coal supplies and water towers would have to be kept in place all across the country to service a very limited number of engines. And so it was decided that steam trains would have to be withdrawn in one fell swoop. Diesels were overcoming their initial teething problems. As soon as they were available in sufficient numbers in each region, the steam trains would be retired. Over the next few years, each region in turn made the switch. The very last holdout of steam was the North West region. On the 11th of August 1968, the last timetabled steam service in mainline Britain ran from Liverpool to Carlisle and back, nicknamed the 15-guinea special due to the high price travellers had to pay to be part of history, and tickets sold out quickly, with hundreds paying for the opportunity to be part of the final chapter of 160 years of steam locomotion on the railways. The next day saw a 2-year ban on steam running on the main lines, just to make it clear that it would not be back. Tens of thousands of steam engines were unceremoniously shuttled off to the scrap heap. Some were relics, around 90 years old and long overdue for retirement, but others were brand new and intended to keep running into the 90s. It was a tragic end for them. Not every engine suffered this fate. BR produced a short list of engines considered historically significant for preservation. Others were bought by private collectors. At Woodham Scrapyard on Barry Island, owner Di Woodham acquired 297 engines in the scrappage, but he worked out that it would be more profitable to focus on scrapping the wagons they had also acquired. He ordered his team to work on them, while offering the engines for sale. This gave steam preservation societies time to get the necessary funds together. Between 1968 and 1990, 213 engines were saved from this yard, estimated to make up 80% of the preserved steam engines in the country. Diesels, as it turned out, did not fare much better than their steam counterparts. The modernisation plan had produced more classes of diesels than anyone knew what to do with, many of which suffered from fundamental flaws. BR had determined 5 main classes, and had identified the best example in each. Mass production of the others was stopped, and the remainders were sent to the scrap heap as soon as they could be replaced. Ironically, many classes of diesels were scrapped before the steam counterparts they had been intended to replace, and few were interested in preserving them. BR had now finally streamlined their engines into a small number of diesel power classes, but it had come at great expense. A whole generation of steam engines had been rapidly developed, followed by a whole generation of diesels, each of which had been sent straight to the scrap heap. This had torn a serious hole in BR's funding. Meanwhile, passenger and freight traffic was flagging. By 1961, BR were losing £300,000 a day. To make matters worse, the government's transport policies were becoming increasingly road-centric. In 1959, a new Minister for Transport was appointed known as Ernest Marples. Marples was a keen advocate for the roads, seeing the car as a symbol of personal freedom. He also owned majority shares in a major tarmacking company and stood to make a lot of money from major road building projects. Recognising the conflict of interest this presented, he agreed to sell all his shares upon coming to power, but not before he'd awarded his company several major contracts, and according to many accounts, he sold most of his shares to his wife. Marples and his predecessors in the Macmillan government instigated several schemes to boost the power of the roads. In 1959, the M1 opened, Britain's first motorway in what would soon become an extensive network. Now long-distance road traffic could compete with the railways in terms of speed. 1959 also saw the introduction of the Routemaster bus, a double-decker design capable of taking on the task of road transport on a scale previous motorbuses could only have dreamed of. Each route master could carry enough passengers to replace trams and trolleybuses on a one-for-one basis. Marples sought to make Britain's cities more car-friendly, largely by widening the streets. And there was no room for trams in this vision. Widening the streets also meant tearing down trolleybus cables, so now they needed to go too. Of course, these systems had been in rapid decline for a while, but Marples delivered the killing blow. Many cities, which had previously aimed to keep their networks going, now had no choice but to close them down, since there was no support coming from the government. From 1962, Blackpool was the only British city running year-round tram services, and the last permanent trolleybus shut in 1972. But this was far from the most controversial move made by this government. In 1963, Marples appointed Dr. Richard Beeching as head of BR, a chemist with no previous experience working on railways, but he had a strong analytical mind, which Marples felt was what was needed to revive BR's fortunes. Just like him, Beeching felt the railways should be run as a profit-making exercise rather than a public service. Some of Beeching's ideas were successful and almost universally welcomed, in particular his reforming of rail freight. In 1962, the government finally repealed the Common Carriers Policy, which had required railways to carry absolutely anything they were asked on a first-come, first-served basis. This was a major burden on time and resources. Often, entire locomotives would have to be dedicated to carrying a single wagon. Even larger services would be run more like passenger trains, continuously stopping en route to drop off and add on wagons. A very slow, complicated and expensive process. With the Common Carriers Policy repealed, freight operators could be more selective, with the focus being on long-distance bulk cargo. Entire train loads would be carried directly from location to location without having to make pickups and drop-offs along the way. In particular, focusing on industries which required a continuous supply of raw materials, or a continuous supply of their product to the docks for export. Small fiddly loads would only be taken where it was convenient, otherwise they would be turned away and told to take it by road instead, which saved money for all concerned. This new model moved away from the traditional wagons and towards the shipping container. The entire container could be filled at the start of the journey, and at each stage it could be sorted, stacked and transferred with ease. Beeching correctly calculated the minimum distance that different quantities of freight would need to be moved to be profitable. Traditional wagons would need to go almost to the other end of the country before they would be worth their while to transport. By 1970, the number of freight services in Britain was at 29% of what it had been 10 years earlier, but the volume of goods carried was 86%. This approach to rail freight was pioneering and copied across the world. The higher-ups at BR would later be instrumental in creating an international agreement for the standard dimensions of shipping containers, greatly streamlining trade worldwide. But Beeching's success with freight is massively overshadowed by his highly divisive policy when it came to passenger services. His plan was to close down any lines which were operating at a financial loss, believing it would leave behind a profit-making core. In April 1961, he organised a covert survey. Workers with clipboards spent a week monitoring how many were travelling on every line, and the results were startling. 95% of passengers were travelling on just 50% of services. Many have criticised the validity of this survey. Those who worked on the lines that will be shut claim to have spotted the surveyors standing around with clipboards, but only in dead hours, never at rush hour. From this, it was easy for people to spin conspiracy theories. While it is unlikely that the survey was deliberately rigged, it provided a limited amount of data, surveying a single week during the school holidays. Beeching refused any suggestion that the survey should be repeated to gain information about a full spectrum of circumstances, or just to ensure that they hadn't surveyed the lines on a bad week. And surveying passengers alone didn't account for other factors, such as the importance of the line to local infrastructure. With these flawed results, Beeching published his report, entitled The Reshaping of British Railways. The full publication was mass-produced and distributed throughout the country, with full statistics and pull-out maps for the public to review. It recommended closing a third of Britain's lines, taking 2,363 stations with them. Beeching argued that those who'd lost their local stations could take the bus instead. Most of the country was already covered by buses. Where it wasn't, replacement services would be set up. The public was used to line closures by this point, but now it was out in the open that line closures would be happening at a greatly accelerated rate. And so there was a public outcry. Line closures were a major issue at the 1964 general election, with Labour leader Harold Wilson promising to fight to protect the condemned lines. Wilson won the election and moved into number 10. Straight away, he announced that he'd changed his mind and would be following Beeching's recommendations after all. Clearly, campaigns to save lines would have to be done at a local level. In many cases, these campaigns were successful, and lines were saved from closure, most often happening in marginal constituencies. However, it seems this may have moved the problem elsewhere, as many lines were shut which hadn't originally been singled out in the Beeching report. Whilst it may be tempting to imagine Beeching as a sort of cartoon villain cruelly slashing away at a beloved network, the story is far more complicated. While his survey may have been flawed, there were genuinely whole swathes of the network which are being built to cater for a demographic which no longer existed. In the 19th century, many lines were primarily aimed at servicing goods trade to local businesses that had since shut down or moved all their goods to road instead. Since they were primarily goods lines, passengers had always been limited, and maintaining a full service for a small number of passengers was simply not sustainable. At the extreme end, the Thetford to Swaffham line ran 5 trains every day, but the survey had recorded just 9 passengers. Hindsight being 2020, it can be seen that the coming decades would see a railway revival, and the lines that were being shut would be badly needed. But to most at the time, it seemed as though the trend could only go one way. Just as the railways had supplanted the canals and the stagecoaches, now they too were being supplanted by the roads. Many were even drawing up plans for an eventuality where the railways died out altogether. In these circumstances, the Beeching report would have seemed like a reasonable compromise to allow the railways to continue on in this new world, but in a limited capacity. Harold Wilson once criticised Beeching for being too pro-rail and too anti-road. And while Beeching cuts is often used as an umbrella term for closed lines, he was far from the only instigator. Arguably, he was more of a middleman, since his report was only a recommendation after all. Line closures had been happening long before he came on the scene, they continued after he was gone, and they happened independently in Ireland and all across the world. Beeching insisted that while he was seen as the axeman chopping away at the network, he saw himself more as the surgeon, carefully cutting away rotten material to preserve what he could, making hard and necessary decisions. But while few would argue that the network could have been preserved in its full glory, it is still fair to dispute whether the closures had to be as extreme as they were. Alternatives were proposed in which the running costs could be reduced but the line kept open. The East Suffolk line showed just how a line could be reformed. Initially marked for closure, many jobs were automated, such as the signals and the crossing gates to reduce staff. Meanwhile, the stations became unstaffed, barring those at each end of the line. Instead, tickets were bought on the train, and the ongoing dieselisation efforts were reducing running costs nationwide. The line was able to turn over a profit, and so was spared the axe. But suggestions that similar schemes could be applied elsewhere were shot down by those in charge. These schemes would require investment, and few were interested in investing in what they saw as a dying industry. The failure of the modernisation plans confirmed their views as far as they were concerned. This was likely short-sighted, since in many of the lines marked for closure, the loss margin was quite small, and a quick investment could have revitalised them. Beeching insisted on going all in with his scheme, even rejecting such compromises as simply preserving the track bed, along with the bridges and tunnels at a minimal cost, just in case an occasion came for the line to be reopened later. A strategy successfully employed in much of the continent. Instead, the bridges were broken up for scrap, and no uniform policy was put in place for the beds. Some were left as they were, albeit overgrown, some became walking and cycling routes, some roads, and others built over in housing and retail developments. All this served to create a greater challenge for future generations who did indeed wish to reopen many of the lines. Beeching's belief that closing the least profitable lines would create a network that would turn over a steady profit were proved badly wrong. Savings made in running costs were accompanied by a severe drop in passenger numbers. The reduction of the network shattered much of the public confidence in trains, not to mention removing a number of crosslinks made many people's journeys much longer and less attractive. It also cost the network much of its inflow traffic. Beeching had assumed that a passenger who had lost their local station would drive to the nearest railhead and take the train from there. In reality, once a traveller is on the road, they normally prefer to go straight to their destination that way. Critics of Beeching, even at the time, pointed out that if the roads were surveyed in the same way the rails were, it would produce similar results, with the bulk of traffic happening on a relatively small number of roads. But if the least used roads were ripped up, it would render the network useless. Continuously cutting off the least useful routes is a good way to kill the tree. The overall financial savings for British Rail are hard to quantify, but the general estimation is that their annual net loss was reduced by around 30 million over the period of the closures. But this was a drop in the bucket when their annual loss before had been around 100 million. Furthermore, Beeching's arguments focus too much on the railways as a profit-making exercise and not as a public service. Even if a line only caters to 9 people, it can be vitally important to those 9, as well as the surrounding community. While some transport needs could be filled by buses, many could not, particularly in rural communities. The town of Chwick on the Scottish borders, for instance, upon losing their line, found themselves in the unenviable position of being the British town furthest from the nearest train station. By train, they could get to Edinburgh in around an hour. By bus, it took 3 times as long. While this is an extreme case, similar stories were happening across the country. Many of the replacement bus services the government had set up had to shut within a few years, since too few people were willing to travel on them every day. This left whole regions with very little public transport, and areas that had once been thriving became sleepy backwaters. On the north coast of Devon and Cornwall, the railways have fared poorly in Beeching's survey as it was not done in the busy season. In the summer, the trains would bring a wealth of tourist traffic. When the lines were shut down, the roads proved insufficient for the task. As a result, the local economy slumped. In 1968, the new Minister for Transport, Barbara Castle, passed the Transport Act, setting stricter conditions under which a line could be shut, requiring several stages of public consultations and parliamentary acts. As a result, the rate of line closures slowed significantly. Since the network's peak in 1928, more than 14,000 kilometres of track had been closed. Though the closures had been curtailed, the issue of shrinking importance of the railways was still in place. Work was needed to inspire confidence once more and draw the crowds back. Removing steam trains from the railways had a curious knock-on effect, namely the danger posed to trespassers. Trespassing had never been particularly encouraged on the railways. Huskisson had established early on that trains and pedestrians made a bad combination. Fines had been put in place for those who were caught, and workers instructed to apprehend trespassers where practical. But this was a law few paid attention to. For too many, the railways served as a useful shortcut, and steam trains could be heard coming from a long distance away. But diesels were much quieter and lacked the column of smoke to announce their presence. Electric trains were quieter still, and brought the additional risk of electrocution. With fatalities climbing, British Rail decided what was needed was a public information film to scare people off. What they produced was called the finish line, in which a child who's been told not to play on the railway begins to fantasise about what would happen if they held school sports day there, resulting in a lot of children getting hit by trains. The film was so shocking to the British public that it was quietly pulled from circulation after 2 weeks. Nonetheless, it, and others like it, did the trick of getting the message across, and trespassing is much less accepted on the tracks today. Some accidents are much worse than others. 1976 saw the worst ever peacetime disaster on the London Underground. On the morning of the 28th of February, a train was pulling into Moorgate Station at the end of the Northern City line, but the train was not slowing down, with no sound from the brakes. Some eyewitnesses even claimed it was accelerating. The driver, Leslie Newson, was spotted in his cab, hands on the controls and staring straight ahead. The train shot through into a runoff tunnel where sand traps had been placed to slow trains down, but the momentum was great enough to break through all of them and smash into the wall at the end, telescoping the first carriage into a crumpled heap and mangling 2 more behind. It took 14 hours for workers to recover the final survivor, and 4 days to find the final body, that of Newson himself. In all, 43 people were killed and 73 injured. The cause of the accident remains a mystery. Thorough analysis of the train ruled out mechanical or electrical error. Newson was a very experienced driver, and simply taking his hands off the controls would have engaged the dead man's handle and applied the brakes. Suicide is a possibility, but friends agreed that he had been in a happy mood that morning. He had £270 in his bag, with plans to buy his daughter her first car after work. The official inquest simply concluded accidental death. Accidents were an issue, but British Rail was facing a more fundamental problem. The importance of the railways was shrinking. Passenger numbers were continuing to decline, their finances were suffering, and though line closures had slowed in Beeching's absence, they had not stopped altogether. The problem was, the public had lost confidence in the future of the railways. To many, they represented a relic of a bygone era, and attention was increasingly shifting to other forms of transport. It was decided that new technology and new ideas were needed to inspire the imagination once more, and show that far from hanging on, British Rail were looking to the future. First, they announced plans for further electrification of key routes, electricity being a more clean and exciting system than diesel. By 1974, the West Coast Main Line had been electrified in full, along with several local routes. To simplify operations, British Rail brought in the TOPS computer system as a tool to aid the organisation of the network, replacing a nightmarish system of logbooks. This allowed them to run more services more efficiently. Not every new idea was a success. In 1970, British Rail looked once more into the possibility of expanding into air travel. This time, they would focus on a method which would allow them to run services directly between their main stations without having to build an airstrip on the roof, namely the helicopter. Engineer Charles Osmond Frederick was assigned the task of designing a special British Rail helicopter. For reasons best known to himself, Frederick took the brief and designed a spaceship, featuring a laser-driven fusion generator which would create energy pulses at 1,000 Hz or less to avoid damaging the craft. The pulses would be transferred out of a nozzle into a series of radial electrodes running along the underside of the craft, which would convert the energy into electricity that would then pass into a ring of powerful electromagnets using superconductors to carry the charge better. The magnets would accelerate subatomic particles produced by the fusion reactor, creating lift and thrust. He admitted that the main drawback was that none of this technology actually existed, but he was confident that it would eventually. Despite the overall insanity of the idea, legal technicalities at British Rail required them to submit a patent application for any design their researchers drew up. Thus, for 3 years, British Rail owned the patent for a flying saucer. Obviously, it was never followed through. Even commercial helicopter travel proved a non-starter, as most who can afford to regularly travel by helicopter can also afford to just buy their own. Back on Earth, British Rail were rethinking their attitude to coaches. The replacement of steam with diesel had initially continued with the locomotive model, in which one big engine would pull along a string of unpowered coaches. Now they began to look to the carriage as an integral part of the train, following the multiple unit model which had proved successful with electric services. A small diesel generator, powering an electric motor in each carriage, allowed traction to be applied throughout the train, making starting and stopping much more efficient. In the busier commuter services, several multiple units could be attached together with minimal difficulty. High-speed express services also began to be treated as a whole unit, with a locomotive at each end in a push-me-pull-you arrangement, with the carriages unpowered to create a smoother ride for passengers. Just like the multiple unit trains, they could be run in either direction equally well, eliminating the need to turn the engine round at the end of the run, as had been the case with steam trains. This new focus gave a great boost to British Rail's plan to improve high-speed travel. Studies of what was happening in places like Japan had drawn the conclusion that every increase of 1 mile an hour in running speed correlated with a 1% increase in passenger numbers. The problem was, most of the network had been built to handle trains which would rarely exceed 80 km an hour. Trains were now capable of running much faster, but were restrained by the need to constantly slow down for bends. Partially this was to avoid the risk of tipping over, but also to avoid the more immediate problem of lateral g-forces throwing passengers around. Engineers decided to adopt the same approach as a high-speed motorcyclist, leaning into the bend so that the lateral g-forces forcing them outwards will be compensated for by the gravity pulling them over. To this end, they designed the Advanced Passenger Train, or APT. Each carriage would be equipped with hydraulic rams, which would tilt the carriages into the bends at a precisely calculated angle. The project was held up by British Rail as the saviour of rail travel that would revolutionise people's journeys everywhere. But from its inception in 1972, the project was hit by one delay after another, not helped by a management which kept adjusting the scope, most notably changing the power system from diesel to electric midway through development. It was not until December 1979 that the first prototype was ready for a run. In these tests, the APT set the still-standing British speed record of 259 km an hour, or 161 miles an hour, but even then, the APT was far from ready for commercial use. Fortunately, British Rail were working on another project at the same time, initially intended to fill the gap until the APT was complete, but soon to become the main focus of their attention. It was a project to develop a much more conventional express engine known as the High Speed Train, or HST. Many new engines will be produced from this research, but easily the most famous was the Intercity 125. The Intercity 125 was designed to incorporate the best systems available, clever suspension systems to handle bends and provide a smoother ride for passengers, AC generators in place of DC to produce more power, and disc brakes used in place of clasp brakes so they could brake later before the bends. The result was a train which could easily cruise along at the desired speed of 125 miles an hour or 200 kilometers an hour, speeds which the fastest steam train in the world had struggled to reach just once. On one of the first runs of the prototype, it set a world speed record for diesel trains at 230 kilometers an hour, or 143 miles an hour. The Intercity 125 made its first run between London and Cardiff in 1976, and proved an instant success. Travel time between the two cities was reduced by 25 minutes, and places like Reading and Swindon came within an hour's travel of central London, almost becoming commuter towns for the capital. Buoyed by this success, British Rail introduced the Intercity to other high-speed express routes. Passenger numbers climbed rapidly everywhere it was introduced. The Intercity 125 was one of the great success stories of British Rail. But passenger numbers climbing in intercity routes were accompanied by a decline in passengers elsewhere, nor was Intercity filling the financial hole British Rail was suffering from. Nonetheless, there was evidence that attitudes were shifting in the right direction. Though passenger numbers were not rising steadily, they were holding steady and could rise soon. Cars take up a lot of space, and this was space the country was rapidly running out of. The standard solution for much of the 20th century was to build more roads to relieve pressure, but it was becoming increasingly clear that this was not a permanent solution. Work expands to fill the time to do it. Focusing on more road building sets the precedent that everyone should have a car. More people take to the roads, and traffic becomes just as bad as it was before, if not worse. And there was little room left for new roads, with protests against them on the rise. In this background, people began to look towards alternatives to the roads, and once more, the railways were beginning to look attractive. The next decade or so would define the future of British Rail, and indeed the railways in general. By the early 80s, British Rail were in a bad state. Their finances had been in freefall for the bulk of their existence, and services were suffering very badly. Calls for privatisation were growing rapidly, even within their own management. What's more, Britain had a new Prime Minister known as Margaret Thatcher. She was a determined and vocal opponent of nationalisations, and began selling off Britain's industries one by one. But despite her disdain for public transport, she was opposed to the idea of privatising the railways. To her, a private enterprise was no more likely to turn over a profit than a public system. She was hoping to foster growth in Britain's financial sector, and believed burdening them with the railways would only stunt this growth. But few in her government shared her views, and though British Rail were safe for the time being, their fringe properties were being sold off, such as the transport hotels and the Sea-Link ferries. In 1983, the Serpell Report was published by Sir David Serpell, a protégé of the infamous Dr. Beeching. He recommended an even more extreme set of line closures, reducing the network down to just the main routes between London and the biggest cities in the UK, even shutting down the East Coast Main Line beyond Newcastle. The report was never given serious consideration due to backlash, but the fact that it was published at all shows how little faith many had in the railways. Nonetheless, efforts were ongoing to resuscitate the organisation. In 1982, reforms were brought in for the management structure. Instead of being flatly divided into regions of the country, it would be divided into 7 types of services. Intercity managed the high-speed express traffic, Network South East handled the commuter traffic in the London area, Regional Railways handled commuter traffic elsewhere, Trainload Freight took trainload freight, Rail Freight Distribution took non-trainload freight, Freightliner took intermodal traffic, and Rail Express Systems took parcels traffic. Specialising in their own relevant industries allowed each to be given more focus. British Rail continued to look into new technology. By 1991, the East Coast Main Line had been electrified in full, together with many routes in the south of England and East Anglia. With the electrified network growing, a new fully electric version of the Intercity 125 was produced, known as the Intercity 225, due to its theoretical ability to hit 225 km an hour in service. In fact, in an early speed run, it was able to hit 261 km an hour, a new British record. Meanwhile, the Intercity 125 did a speed run of its own, hitting 238 km an hour, the still standing world speed record for diesel trains. But while the HSTs were going from strength to strength, the tilting APT, intended to be the saviour of British Rail, had been in development since 1970 and was still yet to carry a single passenger. By 1981, Thatcher was threatening to cut funding for the project unless results were seen soon, and so a working model was rushed out for a special press release. But instead of reporting on the APT's great speed and technological prowess, the press reported the unusual problem of seasickness. Theoretically, a tilting train should allow the byproduct of the downwards force of gravity to compensate for the lateral g-forces pulling a person outwards, so the ride should be smoother than an ordinary train. But this depends on the angle being just right with every curve, something which is very complicated to achieve, and which the developers had not yet worked out all the kinks of. The tilting was too uneven and unpredictable for the body to anticipate. the APT was taken back to the workshops. By 1984, the tilting mechanism had been fine-tuned, and it was finally put into service. But it would only run at a greatly reduced speed, which rather defeated the purpose. What's more, the disastrous press run had done its damage. The APT was treated with a sense of dread by the British public whenever it appeared. By 1987, it had quietly been removed from the network. The network had been steadily shrinking in size since its peak in 1928. 1983 saw it at its smallest length. From here, it began to grow once more, not at a great speed at first, but it was creeping up. The redevelopment of the Docklands presented an opportunity to construct a new community with rail links built in. There were plenty of wealthy business owners who wished for a strong link from the City of London to the Docklands. The area was crisscrossed with disused lines which had once serviced the docks. They could be reopened with minimum difficulty, and links between them could be built in the brownfield sites in the area. The Docklands Light Railway opened in 1987, running from Tower Gateway to Stratford and Island Gardens. Initially run with individual rail cars, the service proved popular enough that full-length trains were installed, and the lines expanded over the years, sprawling all over East London. In 1988, the Snow Hill Tunnel was reopened and linked into the termini on either side of it, creating the Thameslink, the first direct mainline service from one side of London to the other. But London wasn't getting all the big projects. In 1992, the Manchester Metrolink opened, the first year-round tramway outside of Blackpool in 30 years. Today, it is the longest tram network in Britain. Unfortunately, grand new building projects could not overcome British Rail's most fundamental problem. The lack of funding and faith had long been manifesting itself in a network which was badly run down. Travelling by train was an experience of moving through trains and stations which were poorly maintained, strewn with litter and graffiti, and frequent hangouts for muggers and other unsavoury types. In 1987, an incident in King's Cross showed just how bad things had got. Smoking had been banned on the London Underground in 1985, but workers would frequently turn a blind eye to passengers lighting up, especially on the escalators on their way out. One evening at 7:25, an unidentified passenger on the Piccadilly line escalator dropped a still-lit match. It fell down the side of the wooden escalator and got lodged in the runners. The space was rarely cleaned and packed with grease and hair and litter. At 7:30, the fire became noticeable to passengers. They hit the emergency stop and hurried to warn staff. One member ignored them because he couldn't see the smoke from the ticket hall. Another investigated the Northern Line escalators by mistake, wasting crucial time. By the time they found the fire, it was too big to tackle with extinguishers. A fog suppression system was available, but the staff did not know how to use it. They had to go up top to report everything to their superiors. The fire brigade were not contacted until 7:36, and an evacuation was not ordered until 7:39. Passengers below were diverted to the Victoria Line escalators, which happened to come up in the ticket hall near the burning escalators. By 7:45, the fire brigade had arrived and sent some people underground to scout the fire, while those up top threaded their hoses through the corridors. 20 minutes in, not a single drop of water had been applied to the fire. The intense heat given off was trapped against the ceiling of the shaft, which was covered in several layers of old paint. The paint began rapidly absorbing the heat. At 7:45, this created a flashover effect, in which the heat in a confined space reaches a sufficient intensity to ignite everything flammable in the area at once. The resultant fireball engulfed not only the escalator shaft, but also the ticket hall beyond in seconds. It would be over 5 hours before the fire would be put out. 31 people died and 100 were injured. The fire was a result of poor maintenance, poor management and poor training. The London Underground looked into fixing these things. Alongside phasing out wooden escalators, they cleaned up their stations and implemented clearer standards for their staff to follow. British Rail followed suit, determined to clean up the image of train travel. Another incident which forced through changes happened outside Clapham Junction in 1988. The task of repairing a key signal had been given to a junior worker, who was not only inexperienced, but also overworked, having been doing overtime shifts all week. He requested for a supervisor to check his work, but none was available, so his boss just marked the job as done. The danger signal failed to function, and a crowded commuter train ran into the back of a stationary train. 35 people were killed and 69 seriously injured. The incident led British Rail to bring in stricter standards of maintenance and health and safety, never just assuming everything was okay. They also brought in stricter limits for overtime work to ensure full concentration from staff. Investigations also criticised the integrity of the coaching stock involved in the accident, and this sped up British Rail's efforts to update it. Much of the stock they were working with dated back to the early days of British Rail and was badly in need of overhaul. Unfortunately, much of this was done with cost in mind. The Pacer coach was a multiple unit carriage designed to replace outdated stock cheaply. It consisted of a modified bus body mounted on a 2-axle freight wagon chassis. Its lack of bogies made it very slow, noisy and uncomfortable, but it did save many minor lines a lot in running costs, arguably saving some of them from closure. More successful were the Sprinter and Networker coaches, smoother and more powerful than previous multiple unit trains, and incorporating features like air conditioning and sliding doors, which made them much easier to board and allowed the doors to be electronically locked when the train was moving. At the same time, onboard catering services began to move away from the dining coach in favour of the buffet coach, which allowed passengers to buy sandwiches and snacks to eat in their own seat, allowing more people to eat at once since they didn't need an extra seat. But the most notable change in the interiors was the rapid move away from the compartment structure and towards the open plan structure. Open plan carriages had been around since the start of the century, but they had never been particularly popular. A compartment could be a private space for a travelling group. Couples could use them for romantic liaisons. Introverts loved the opportunity to find a compartment to themselves, while extroverts loved the opportunity to strike a conversation with strangers who happened to sit in the same compartment. But crime was increasing on the railways, and the compartment structure created a lot of quiet corners which were useful for vandals, thieves, rapists and murderers. Open plan carriages gave them nowhere to hide. In addition, open plan carriages were much lighter and airier. At crowded times, they created more standing room, and they made life easier for disabled people and those with heavy luggage. It seems that British Rail's efforts to clean themselves up were paying off, and by the end of the decade, passenger numbers were steadily climbing for the first time since the 1950s. Unfortunately, it was too little too late to save British Rail. Thatcher resigned in 1990, with John Major taking over. 2 years later, he called a general election. Amongst other election promises, he promised to sell off British Rail, the Tory voters having lost patience with them long ago. To his surprise, he won the election and began the privatisation process. British Rail have something of a mixed reputation amongst rail enthusiasts. To some, they were a failed experiment in nationalisation, financially inept and incapable of managing the country's entire rail system. They were losing money and passengers for most of their existence, and they would argue that British Rail were well overdue for privatisation by the time Major finally put them out of their misery. To others, they were a necessary and useful organisation with the misfortune of existing throughout a very difficult period for railways worldwide, with little interest from a public more obsessed with the roads, and sociological changes happening so regularly that few would have been able to anticipate them, considering which they arguably weathered the storm pretty well. While they made a good number of bad decisions, there were also many great success stories, such as widespread electrification and high-speed travel. They may have been losing money for most of their existence, but so had the Big Four before them, and so were many of the private companies to follow. British Rail was stuck in a vicious circle, in which successive governments would deny them the funding they badly needed, quality of services would slip, and the government would use this as justification for cutting funding further. And just as they were finally beginning to get on top of things, they were privatised out of existence, never able to live up to their full potential. But for better or for worse, the British rail era was at an end, and a new era was about to begin. When Major made an election promise to privatise the railways, he did so with no actual plan of how to do it. Upon winning the election, he had to rapidly put a plan together. There were differing ideas of what to do. The management of British Rail wanted the organisation to be privatised as an intact entity, effectively creating a British Rail plc. Major himself wanted to return to the grouping system, effectively reviving the Big Four. The Treasury, however, wanted the network to be carved up into 7 franchises, which would be sold to the highest bidder. The Treasury won out. Throughout the mid-90s, services were sold off piece by piece, given to whichever company promised the most. It was a chaotic process, and 7 franchises rapidly became 25, with more than 100 companies running services on the railways. Theoretically, franchises were awarded to those who had the best plan of what they aimed to do with it. In practice, they were often awarded to those who could promise the most, irrespective of whether or not they could deliver. The new franchises owned virtually nothing. Everything was leased to them for operation. The trains and rolling stock were placed under the command of 3 rolling stock leasing companies. The tracks and infrastructure were handed over to the newly formed Railtrack. The Office of the Rail Regulator was created to oversee everything, performing much the same function as the Railway Clearinghouse had once done. The level of authority it posed would fluctuate a lot with legislation changes over the years. The impact of privatisation is a hotly debated topic, with many fierce arguments on both sides. By most measurable qualities, the railways have seen a significant improvement since privatisation. Passenger numbers have been climbing steadily every year there has not been a pandemic. In proportion, it has risen more strongly than many European countries which maintain their nationalised networks. Frequency of services has increased across the country, and overall satisfaction with services has improved markedly. Opponents, however, say there is no causal link between improved performance and privatisation. The mid-90s coincided with many sociological changes, with climate change beginning to seep more into the public consciousness and road traffic well ahead of saturation point. Government policy was increasingly shifting away from building more roads and towards policies to discourage people from driving altogether, together with stronger public transport links. Rail travel rapidly became fashionable once again, particularly with young people. Many of the service improvements, policy changes and fresh new technology first began to be implemented under British Rail, with critics arguing that their impact was only just becoming widespread when privatisation happened, allowing the franchises to take credit. In fact, many improvements stalled under privatisation. Much of the coaching stock used now, for instance, has been around since the days of British Rail. The promise that privatisation would encourage long-term investment, free from short-term politics, has failed to materialise. The franchises still depend heavily on government subsidies, and they operate with the threat of being shut down should they be incapable of running services, meaning that politics now arguably plays an even closer role in how the railways are run. Another promise of the franchising system was that it would lead to stronger competition driving services forward. This has had mixed results. For competition to work, customers must have a choice. But for many, there is only one company that they can use, and this company will take full advantage of this monopoly. It is no accident that the most popular operators run in areas where there are many rivals to compete with. But even then, government subsidies eliminate much of the pressure to perform. Perhaps the biggest criticism with the franchising system is that it is too complicated, creating too many parties to be negotiated with and regulated. Whether due to privatisation or in spite of it, the 1990s was the start of a period that has been called a new golden age of rail travel. No longer an outdated relic, rail travel rapidly became exciting and fashionable once more, interest and footfall rapidly growing. The network itself was growing in size, both with reopenings and with new lines. The Robin Hood line between Nottingham and Worksop reopened in stages between 1993 and 1998, along the way linking up with Mansfield, up until then the biggest town in Britain without a train station. At the same time, new lines were being built. In London, the Jubilee line was extended to Greenwich and Stratford in 1999, greatly boosting the revitalisation of East London. Out in the suburbs, the Croydon Tramlink opened in 2000, bringing trams back to the capital after 48 years. The tramlink connected Croydon to Wimbledon, boosting an area with no tube links. At the same time, a great tramway revival has been happening all across the country in recent years. But easily the biggest rail project of this era was the Channel Tunnel, connecting Britain and France under 50 kilometres of English Channel. The first proposal for a Channel Tunnel was brought before Napoleon in 1802. Napoleon gave it the go-ahead, believing it may be a means of invading Britain whilst bypassing the Royal Navy. Had it actually gone ahead, it would have been a truly spectacular undertaking. The longest tunnel in the world by more than 40 kilometres, and the first ever dug beneath a body of water. Over the years, several more proposals were put forward. Proposals of bridges, tunnels, and even submerged tubes suspended from floating platforms. In the 1860s, a layer of stable chalk marl was discovered beneath the channel, boosting the possibility of a tunnel. In 1880, a joint Anglo-French venture even got as far as digging experimental shafts totalling over 5 kilometres. But the unstable political situation between the two countries brought this project to a halt. Practical and political issues were shutting down all proposals for more than a century. But with better technology available and the EEC on hand to mediate and smooth over bureaucracy, the two governments were able to agree on a deal in 1987. Initial plans favoured a road tunnel, but questions arose about ventilation, traffic management, emergency response, and driver fatigue. With this in mind, a rail tunnel was agreed upon. The project cost £4.65 billion, making it the most expensive rail project ever done at this time. Construction got underway in 1988, with 5 British and 5 French companies digging from their own sides of the channel. Digging was done with huge tunnel boring machines, 8.36 metres in diameter and weighing up to 1,300 tonnes. The cutting head would cut through the rock, while systems behind automatically added in reinforcing materials and carried away all the spoilage. The French detected unstable fissures in the chalk and designed special boring machines which could work through them. The British, however, anticipated drier conditions and fought ahead with ordinary tunnelling machines. This proved a problem within a few months when the tunnel sprang a leak. The breach was rapidly sealed with grout, as were future breaches, and the British took to digging pilot shafts ahead of the main one to detect problems in advance and shore them up. At its peak, the project hired 15,000 workers, 10 of whom would die in the construction. Navigating 2 long tunnels so that they will meet within centimetres of each other is no mean feat. Careful analysis was required to keep on course, making use of satellites, sonar, and even consultations with paleontologists to ensure they were in the correct regions. Towards the end of 1990, the 2 tunnels came within a few metres of each other. On the 1st of December that year, Englishman Graham Fagg and Frenchman Philippe Cosette broke through the rock, creating the first land link between Britain and France since the Ice Age. 3 tunnels were dug in total, 2 rail tunnels with a service tunnel between them, and many connecting passages and ventilation ducts. In May 1994, the tunnel was officially opened, with the first freight services running through it 2 weeks later. In November, the first Eurostar trains left Waterloo, running the first direct service between London and Paris, soon to expand all over Western Europe. While this was going on, the franchising system was running into problems. Railtrack had been formed as a public-owned body, but in 1996, the management convinced the government that they could achieve more as a private enterprise, and so it was sold off. This was a controversial move, even among supporters of privatisation, as it gave them a monopoly over the whole network, with very little in the way of profit or competition to motivate them to greater performance. To prove their worth, they instituted an upgrade programme on the West Coast Main Line, aimed to deliver regular 225 km/h services by 2005, with innovations such as tilting trains and moving block signalling at the cost of $2 billion. In fact, the project cost $10 billion, was not complete until 2008, and could not deliver services much faster than were already running. At first, Railtrack were able to turn over a steady profit, but much of this was achieved through cost-cutting measures. Maintenance was outsourced to a number of private contractors with very little oversight. They created a hideously complex system for reporting faults and financing, supplying and scheduling repair work. Before long, maintenance and upgrades were well behind the targets agreed with the government. The Labour Party were deeply opposed to privatisation, vowing to reverse it upon return to power. But when the more centrist Tony Blair was elected in 1997, he shied away from full nationalisation. The government did, however, rein in the power of the private company somewhat. In 2000, the Office of the Rail Regulator was replaced by the Strategic Rail Authority, with more direct authority over the railways. In the same year, the public-owned Transport for London was formed to directly oversee the vast complex spiderweb of roads, buses, trains, tubes, trams, bikes and boats that ran through the capital. In particular, they took to shifting the balance of policy away from the cars and towards public transport. But the biggest shift the government made was with Railtrack. This was a direct response to a string of disasters which happened around this time. At Southall in 1997, an intercity driver missed a signal. The train collided with a freight train which was crossing its path, derailing it and killing 7 people. The signal had been installed in 1994. Many drivers had reported that it was hard to see, but nothing had been done. 2 years later at Ladbroke Grove, another intercity driver missed a danger signal. The train collided head-on with a commuter train, killing both drivers and 29 other people and injuring 417 more. Once more, the difficulty of spotting the signal was well on record, but nothing had been done. At Hatfield in 2000, inspectors on the line reported signs of fatigue in a particular rail. A replacement was ordered, but somewhere amongst the bureaucracy, the order to replace it was lost. The faulty rail was still in place 10 months later when a high-speed train went that way and the rail finally shattered, overturning the train, killing 4 people and injuring 70. These incidents brought the disorganisation of Railtrack to the forefront. When asked how many other key maintenance tasks were being similarly deferred, they had to admit they simply didn't know. Their only choice was to conduct a thorough inspection of their entire network, ordering 1,800 temporary speed limits to be brought in while the work was carried out. In many places, this was as low as 32 km an hour on main lines, crippling services. This debacle bankrupted Railtrack, and they were forced to go cap in hand to the government. Controversially, upon being bailed out, Railtrack awarded their shareholders $137 million in bonuses. A few months later, Railtrack were bankrupt once more. This time the government refused to bail them out. The company was liquidated and their assets were transferred to the newly formed public-owned Network Rail. It was hoped that a not-for-profit enterprise could succeed where Railtrack had failed. At the time of privatisation, Railtrack were created to manage the network and oversee all the maintenance and the upgrades. But having a private company with a monopoly over a public safety body soon presented problems. After a series of accidents, Railtrack were bankrupt, and this created an opportunity for reform. Network Rail were created in 2002, with all of Railtrack's assets transferred to them. They would be government-run and not-for-profit, thus allowing for more funding to be put directly into improvements and maintenance, and eliminating much of the bureaucracy which had blighted Railtrack. As well as renationalising the network, other changes were also brought in. Network Rail were granted a more direct authority over the strategic planning of operations, helping to streamline services and taking away many duties from the Strategic Rail Authority. In 2005, the SRA was formally dissolved, with its duties split between the Department for Transport and the Office of Rail Regulation. For the large part, Network Rail have been a success. They brought all the engineering systems back in-house, replacing an incomprehensible system of contractors. Under their tutelage, safety improved dramatically, with some of the longest periods with no fatal accidents on the network at all. Since 2002, the majority of fatalities there have consisted of passengers or vehicles falling onto the tracks. In 2005, their new safety and response standards were put to the test. On the 7th of July that year, suicide bombers detonated bombs on 3 London Underground trains and 1 bus. The trains were well into the tunnels, and debris littered the way, making rescue efforts doubly difficult. 56 people died in total, including the bombers, and 784 were injured, making it the worst terrorist incident ever to happen on Britain's railways. But alongside the tragedy, the British public celebrated many acts of individual heroism from those involved, together with a strong emergency response. As soon as the bombs went off, the underground staff sprang into action like a well-oiled machine. They coordinated evacuations and cleared the way for the emergency services. It was a great contrast from the comedy of errors which had led to the King's Cross fire 20 years earlier, and it highlighted how much standards had improved since then. Meanwhile, improvement works were happening at a great rate. In 2006, the government launched the Access for All scheme, which has brought disabled access to hundreds of stations all across the country, with the aim to bring it to all. In 2007, the government discussed plans to bring the network closer to a net zero. Solar panels were installed on station canopies and other unused spaces, while diesel services switched to using more environmentally friendly biodiesel. However, they rejected plans for whole-scale electrification due to practical issues. Electrification had proceeded steadily under British Rail, but had stalled under Railtrack. But it resumed once more in 2011, with widespread plans across the country. By 2020, the Great Western Main Line was electrified all the way from London to Cardiff. However, the work proceeded a lot slower and costlier than planned, and many promised electrifications were cancelled. At the current time, only 37% of Britain's rail network has been electrified. New trains were added to the network in this era. Most notably, the Class 390 Pendolinos were introduced on the West Coast Main Line in 2002, with a finely tuned tilting mechanism which allowed for smoother rides for passengers and for services to handle bends better. Even new steam trains were introduced. In 2008, the A1 Steam Locomotive Trust completed the A1 Peppercorn class Tornado, the first new steam train to be built in Britain since 1960. It was built through donations from steam enthusiasts who were upset that no one had thought to preserve one of the original peppercorns. Since construction, it has gone on tours across the country, which have proved very popular. Meanwhile, the network was continuing to build, with lines being opened or reopened across the country. The London Overground opened in stages between 2002 and 2015, reopening many disused lines, many of them former goods lines, and linking them up to create a loop around the suburbs. In fact, the Overground became so vast and complex that it is due to be split into 6 different lines in August this year. In 2015, the Borders Railway reopened from Edinburgh to Tweedbank, restoring rail services to a region of the country which had previously been furthest from the nearest railhead. With public support growing for the railways, it was also becoming harder and harder to shut services down, even dead services that nobody would seriously miss. Operators were rarely willing to go through the maze of bureaucracy required to shut a line down. This has given rise to a phenomenon known as ghost trains or parliamentary trains, services run infrequently and often unadvertised to satisfy contracts. At the extreme end of this, Northern service between Stockport and Stalybridge runs a single train back and forth once a week. Barlston Station remains open despite not having seen a train since 2004. Midland Railways have run a temporary rail replacement bus service ever since. Newhaven Marine had already had its services reduced to 1 a day by 2006, when the station was fenced off due to structural issues. In 2017, the station was fully demolished, but it remained officially open until 2020, with the ghost train stopping in the spot where it used to be each day. Alongside reopening closed lines and preventing existing ones being shut, new routes were being built. When the Eurostar first opened, it soon became clear that Waterloo was poorly positioned to act as the London terminus. High-speed Eurostar trains had to follow winding tracks not designed for high-speed travel. What's more, they had to share space with commuter trains, creating a lot of frustration for both parties. Services took almost as long to cover the relatively short distance from London to the tunnel as they did from the tunnel to Paris. For the first time, Britain's railways would adopt a policy long followed in many countries in Europe, in which specialised tracks are built for high-speed services. The new line, known as High Speed 1 or HS1, would run from St Pancras to link into the Channel Tunnel, using tunnels and viaducts for most of its length to avoid disruption to the surrounding area. In fact, the cumulative length of all the tunnels built for HS1 was greater than the Channel Tunnel itself. The track was straighter and more level than traditional tracks, allowing trains to maintain full speed for longer periods. It also provided segregation between the high-speed services and the local stopping services, so neither interferes with the other schedules and more local trains can be run. HS1 opened in stages between 2003 and 2007. An early service in 2003 set the still-standing British speed record of 335 km an hour, or 208 miles an hour. The only time a British train has exceeded 200 miles an hour. Paris soon came within 2 hours train travel of London. Today, the Eurostar takes more passengers between the two capitals than all of the airlines combined. International freight too saw a boost thanks to this new link running close to the marshalling yards at Tilbury. In 2017, the first direct train from China arrived in London, having left China 18 days earlier. Along the way, it travelled through 9 countries, having to stop and have its bogies replaced twice to account for the break of gauge. But while all this was going on, the franchising system was showing increasing flaws. Fares were skyrocketing, and despite this and the rapidly growing passenger numbers, operators were unable to turn over a steady profit, depending on government subsidies to function. This left Britain's railways in the unenviable position of having some of the highest level of government spending in Europe, along with the highest fares. And because many of the franchises were registered overseas, much of the money was being funneled out of the country. Meanwhile, quality of service showed no clear advantage over that of countries with fully nationalised network. The lack of regulation in the operators and the monopoly they had over several areas left them with no pressure to perform. The franchising system, which allowed operators to bid on services they wanted to run, usually awarded services to the company that promised the most. This led many companies to overpromise and underdeliver. In 2009, First East Coast went into administration. The government refused to bail it out, but no buyer could be found, and so the service was placed under public ownership. During this time, services improved and the line was able to turn over a profit. But the government refused to make this permanent, and so the franchise was sold to Virgin Rail in 2015, who promised to bring a return of £4 billion within 2 years. In fact, Virgin made a loss on the service. In many places, Britain's franchising system was taken as a guide of what not to do. Nonetheless, suggestions that the system should be reformed fell on deaf ears. But events were coming soon which would turn everything upside down.
In recent years, the network has continued to grow through line reopenings and new projects. In 2022, the Elizabeth line opened, creating a high-frequency east-west rail link through the capital, running from Reading and Heathrow in the west to Shenfield in the east. Across the country, tracks are being doubled, connections are being refined, and all sorts of running systems are being streamlined, making services more frequent and efficient. Many lines are being reopened. One of the most drastic is the east-west rail link currently under construction, which aims to reopen the railway between Oxford and Cambridge by 2030. Not only will it boost communications between the two great universities, it will restore crosslinks to central England, where currently none exists between London and Birmingham. But most prominent in the news is HS2. Buoyed by the success of HS1, the government announced this ambitious project in 2009, designed to provide high-speed connections from London to the cities of the north, boosting the economy of the areas and freeing up space on the existing network for slower stopping services. It could even be linked into HS1 and the West and East Coast main lines, effectively creating a direct service from Edinburgh to Paris. Construction got underway in 2017 for Phase 1, which would run from London to Birmingham. The route would follow viaducts and tunnels for most of its length in order to avoid disruption, and they would be some of the longest ever built for Britain's railways. Biggest of all is the Colne Valley Viaduct, now under construction. Upon completion, it will be the longest viaduct in Britain, 3.4 kilometres long with spans of up to 80 metres, and will weigh 116,000 tonnes. It is built using the same rapid construction techniques employed by high-speed railways in France. More than 1,000 bridge sections are manufactured in an on-site factory. Each section is then raised into place with a 100-metre horizontal crane known as a launching girder, which simultaneously holds the previous spans in place until the span is complete. Upon completion, the girder can then be walked onto the next span. However, HS2 quickly ran into problems. Initial estimates put the cost of the project at $37 billion. By 2020, estimations had added more than $100 billion to this figure. To many, it was becoming a money sink when there were so many other infrastructure projects badly in need of funding. To cut costs, the project scope was reduced bit by bit. The link to HS1 was removed in the planning stages in 2014. The leg towards Leeds was cut in 2021. And finally, in 2023, the northern leg was cancelled altogether. Even the link to Euston is now in question, with proposals to halt at Old Oak Common in London's suburbs. Effectively, this leaves a high-speed rail link running only from outer London to Birmingham, two cities which are already pretty well connected by rail. The government promised that the money saved by cancelling Phase 2 will be used to fund infrastructure projects elsewhere. They probably use much of this funding to fix potholes in North London. An important job, no doubt, but a blow for those who had hoped for better rail connections and stronger transport links for the north. To many, this reinforced the belief that London was getting all the big rail projects. Metro projects in cities like Edinburgh struggled for funding and were ultimately watered down or cancelled altogether. The simple reason this happens is because London is where the money is. Historically, it has been shown that as trains are built, demand and business naturally follow. But most investors want to invest in something which they can see right now, and it helps if this is right outside their office. This all helped to highlight the growing cracks in the franchise system. Supporters of privatisation continued to insist that quality of service and passenger numbers had gone up steadily and rapidly since privatisation. Opponents responded that this was largely due to the franchises being awarded government subsidies at levels British Rail could only have dreamed of, and that if the latter had had this kind of funding they would have been world-leading. Supporters responded that the subsidy per journey has gone down, hovering at around £2 per journey, compared to more than £3 under British Rail. Opponents responded that this is offset by a rise in fares, operating companies having been given very little regulation in this regard, and the average fares have risen by almost 30% compared to the equivalent fares in 1995. For some journeys, mainly standard single classes, the rise has been more than 200%, though fares for advanced tickets in off-peak hours have gone down. Nonetheless, the franchise system has left Britain in the unenviable position of having the highest fares in Europe and the highest level of government spending in Europe. And because most of the companies are registered abroad, much of the funding is being funneled out of the country. And despite this, Britain's railways have no clear advantage in performance over their European counterparts. The system assigned services to a franchise based on which promised the most. This gave franchises a motive to overpromise whether or not they could deliver. In 2018, the East Coast mainline service went into administration for the second time in a decade, Virgin Rail having produced a loss, despite promising a £4 billion return within 2 years. For the first time since privatisation, a major service was placed under a permanent public ownership, with LNER created to manage services on the East Coast. LNER were much more successful, able to organise faster, more frequent and more profitable services between London and Edinburgh. Class 801 Azuma trains were introduced, providing a sleeker and more efficient service. Suggestions were raised that other failing franchises could be handled in a similar way to LNER, creating a new British Rail bit by bit, with little additional cost. But these suggestions fell on deaf ears. However, circumstances would soon force through changes. In 2020, COVID-19 swept the world. After some initial reluctance, Britain was placed into lockdown, with all non-essential businesses told to either work remotely or to put their staff on furlough, and the public instructed not to leave the house unless absolutely necessary. Passenger numbers naturally plummeted to a fraction of pre-pandemic levels. Despite this, the railways could neither halt nor reduce their services, due to the need to cater to key workers. Masks were made compulsory on services, a restriction which would stay in place longer than most places with similar mandates. Even as lockdowns were eased, the public were hesitant about travelling in a confined space with hundreds of strangers, and it would take time for passenger numbers to fully recover. This was disastrous for the franchises. The government entered into emergency recovery measures agreements. Normal passenger service mechanisms were amended, transferring almost all revenue and cost risk to the government, effectively renationalising these services temporarily. In an effort to balance the books, the DMT proposed sweeping changes. They would introduce more driver-only trains and cut back jobs in many areas, which would put almost 2,000 people out of work and compromise safety standards. They would also increase working hours with no overtime pay. Furthermore, they would shut many ticket offices. This did not sit well with rail workers, who were already upset with repeated pay freezes, especially when shareholders had continued to award themselves significant pay rises throughout the pandemic and the cost of living crisis. To protest these changes and campaign for fairer contracts, the RMT, ASLEF and the TSSA voted to implement the first nationwide rail strike since privatisation, a series of temporary strikes which would block the proposed changes from being implemented and generally force those in power to listen. The strikes served as a rallying cry for many other public sector workers who felt they were similarly underpaid and overworked, particularly after having been on the front lines throughout the pandemic. Strikes soon broke out in many sectors. Opponents of the rail strikes insisted that rail workers were already being paid significantly more than a good proportion of the British public, and asked them to consider the impact these strikes would have on many businesses who were trying to recover from the pandemic, not to mention the railways themselves who were trying to win back passengers they'd lost to the roads. Supporters responded that driver pay was a side issue, working conditions and job security were the main problem. Though the disruption caused was regrettable, they had no choice but to call the strikes when they did, to prevent the changes they were protesting against being rushed through. They also claimed the deals they were being offered were repeatedly changed at the last minute to include the driver-only trains, something they were not willing to budge on. Meanwhile, the DMD were equally unwilling to concede, and so the dispute dragged on. This led many to accuse the government of repeatedly blocking negotiations. After all, in Scotland and Wales, where the DMT has no power, deals were reached quite quickly. YouGov surveys showed a 57% union support from the public, a figure which remained fairly constant throughout the strikes. Nonetheless, the government passed new legislation, giving operators a right to demand 40% service during strikes. So far, the operators are yet to exercise this right. Shortly after this legislation was passed, a deal was finally offered which was accepted by the RMT, one which granted them a pay rise of up to £15,000 annually and a 4-day working week with no job losses. But although this deal was accepted by them, no deal has yet been reached with ASLEF at the time of making this video. The other major impact of the pandemic was to make the franchising system unsustainable. Up until this point, if a franchise went into administration, the public-owned operator of last resort would manage services there until the franchise could be sold on. But it was becoming increasingly difficult to find a private company that could handle the responsibility. But now the system was changed so that the OLR would maintain the service permanently. At the current time, 7 major franchises are under the OLR's control. effectively nationalising a significant chunk of the network. In 2022, it was announced that the franchise system would be formally abolished. The public-owned Great British Railways would be created to oversee the railways. Instead of a franchise contract, it would operate as a concessions contract, with operators paid a flat fee to operate services instead of keeping all the profits. It is argued that this new system will restore the central authority previously enjoyed by British Rail and simplify operations across the country. Others have argued that this system does not solve the inherent problem of operators run by shareholders who will make money regardless of the quality of service they provide. It is currently unclear what powers GBR will operate with. For instance, despite initial promises, the current stance is that the operators will continue to have the power to set their own fees, thus doing little to ease the skyrocketing fare costs. The announcement of Great British Railways was soon followed by a period of political instability, with several new prime ministers and one new king in the space of 2 years. GBR was pushed down in the priority rankings, and it is currently unclear when and even if it will be put before Parliament. However, with a general election coming up and a lot of cross-party support for some form of nationalisation, it seems likely that it will happen eventually. When it does, it will likely usher in the next major phase of Britain's railway history. Perhaps this channel will return in 10 years' time to cover the new golden age of rail travel. Perhaps it will cover the rail's complete collapse. Perhaps everything will trundle along as before. This is a story for next time. Thank you all for tuning in for this omnibus edition of my UK Railway History series. Do leave a comment to let me know your thoughts. And also, why not like, share and subscribe to let the YouTube algorithm know you would like to see similar content. I am currently working on further rail videos where I talk about more specific topics. I am also working on a new series where I go along the River Thames and tell the history of everything it passes by, so do check that out. If you would like to support this channel further, I now have a Ko-fi page where you can leave a small thanks, or you can commission a drawing there. I also have further artwork available on my Etsy pages and on my website. Links to these in the description. I hope to see you all soon.